Okay, well, first off, an apology. I was the idiot who set off his phone twice yesterday afternoon. Had my arms folded and I kept triggering to find my phone. So no more watch, probably will lose my phone. So I'm gonna talk a little bit about the Hail camera work that we've been doing the past couple of years. Apologies. I actually closed out my 2018 talk here at the Hail workshop saying, hey, we're going to build a Hail camera. And we did, and I presented it at AMS 2020, and then we went on pause for a couple of years here. So before I get started, just want to acknowledge all the folks that had helped us through both versions of the camera, little legalese down there, and then just a little taste of some of the weird stuff that we saw in one storm in particular that I'll go over a little bit in detail. So if you can't quite see it or can't quite keep track of it, it's kind of a half sphere, but then there's a chunk missing out of it. So there's kind of a twist in it. So as it's falling, it's kind of water wheeling. And then as that rotation happens, it's also rotating on the horizontal. So a little history. I'll start off with some work that was done here at NCAR. Basically, they had a funnel sitting on top with a hail tunnel. They used an etched gridded mirror. And why they did that is if you use some fancy trigonometry between the image in the mirror and the hailstone itself in the image on film, you can work out how big the stone is. What we ended up going with the second version was more like what some folks at the University of Alberta did. And you actually just have two cameras kind of angled in and you let the stone fall through. And then again, using some fancy trigonometry between the cameras, you can work out, and pretty simply, you only need the variables that are over on the right there. You can work out how big stones are by comparing the two images. Sean's done more of that work with the things. I've gone in and found pretty pictures. So, but definitely go to his poster because he's actually getting automated calculations pretty easily. But obviously, you can see between both the very quality images that you could get with camera gear, back in the late 70s and early 80s. So obviously, modern approach, we have machine vision cameras. We have very high resolution at that. Sean's already demonstrated these cameras capabilities before. So I was like, hey, why don't we try to build a Hail camera? And so with the SIMS, it was SIMS back then, through a DDRF, we got some money to build two cameras. I'm glad we built two cameras because on every deployment, one or the other would turn off. So it was good to have both of them sitting there or else we wouldn't have got really any images. We put a 14,000 lumen light above it in a box. And then we also started off with two light tables, I guess you will, that they were like 6,000 lumens a piece. So it was very bright. We thought we needed all this light, and we kind of did. So our very first deployment, the image on the left and the inset as well was some of the images that we captured. So this is a small stone that I think shed off its water shell. That's a large drop ballooning there. Not quite sure what the middle image is. And then the other images are from the last deployment of this particular system up in Nebraska. Very clearly see a water torus, a lumpy stone with some lobes on some of the faces, and then another completely encased small stone, kind of resembling what's over on the left. So when it comes to drop breakup, we figured out this year we have to be really careful in interpreting that because the turbulence that the instrument itself, and especially the truck mounted system, puts on the hydrometeors induces this behavior. So we did a driving example in Colorado, and I was replaying the images going through, and you could draw like a perfect line across where all the drops would start to burst, and it's where it was interacting with the truck turbulence. So here's an image we got from the first system. It was mounted on a tripod. You have to get out. It's wonderful holding metal around thunderstorms, be it aluminum or not. And then we'd set it down. There was a little button on the side. We'd turn it on. It'd run for 15 minutes and then shut itself off. This is in Nebraska. It was a high-base storm, so there's plenty of sunlight. Here you see kind of a lumpy stone. If you look really closely, you can see smaller hailstones and stuff like that. When I got out of the car, it was all smooth stone, so stuff like this didn't really survive the trip afterwards. So here's a picture from the new system. We were in the Black Hills, as you do for hail. And the image on the left is what the image looks like that we take. The image on the right is what I took with my phone. So we were getting really lucky the first system, which was back in 2019, that a lot of the storms we were on, we got a lot of sunlight underneath. We got really lucky this year with the second system because we were like, oh, for memes, let's put all the bright lights up there, and we put 5, and that ended up being enough to sample, you know, be able to see hailstones falling through the whole area that we wanted to keep track of. So how fast do we got to go? I've got the math there, but it's not only the speed of the camera to take the image, it's the speed of processing the image and then storing. So the first version of the camera, we basically just took the raw image format and wrote it to disk as fast as we could. And that worked well, except for after the fact, I had to process those, and it took upwards of 10 hours, you know, to sequentially go through all those images. Our exposure time is also 50 microseconds. So effectively, when we take the picture, it's black. To back the image out, you have to do a gamma correction. So that's 12.4 million operations. So it's a lot of you're gonna need a lot of horsepower to run that. Also, better, safer deployment would have been nice with the first version. So we got a truck mounted system. We get beefier cameras. So you can see in the top left, there's our new one in my hand. There's the old camera. We usually shot around 325 frames per second, basically had a server in there. That was Jeff's idea because he's actually going to use this for modeling afterwards. So you needed a big storage RAID in the front. Hopefully we can get it to where it's not that. Jake was out. Jake is 6'3". Jake is 1.5 inches too tall to fit in this car as it's configured. So I appreciate him coming out and being a sardine in a sardine can for a while. We probably wouldn't have been able to do we actually ordered those new cameras back in 2020, got shut down from the pandemic. We most likely wouldn't have been able what we did that year, because some of the stuff of peripherals going straight to GPU, doing JPEG processing on the GPU was not available until January of this year. So we lucked out a bit there. But basically we do all of our processing on the GPU. The only time the CPU gets involved is to write. We're writing to SSDs. Everything's done on PCIe lanes, so it's very, very fast. So the two pictures that we take, I can get processed in under 3 milliseconds, which is our frame rate to begin with, at 325 frames per second. So I'm going to talk about our Black Hills deployment. The camera deployment's kind of right in the middle. There is a bullseye if you can see it. It's actually a pretty decent deployment, shot pretty fast, 335 frames per second, but it wasn't always that. Usually, most of them are actually around 325. We were at 1266 meters MSL. The beam right here is only about 800 meters above us. So I think pretty good sampling of the radar for what's here. After the hail ended, we went out and collected stones. We have some interesting stones. This one above the tape measure on the far right, there's actually kind of 2 centroids. Kind of interesting structure. You have some with lobes, you have some smooth stones. So this one on the far left below the tape measure is actually kind of more of a hamburger bun than a spheroid. And then you can see spikes and clear ice with opaque centers. These are all features we can see in the camera as it's falling, as we'll show here. Wasn't exactly the most intense supercell. Really didn't have a mesocyclone until about 6 kilometers. Even then it was pretty weak, but it did have deep convergence, and you saw that all the way through until you hit that mesocyclone. It's where the ZDR column was located, a really broad weak echo region above us. And I'll go back here. So we start shooting at 16:25 after the hour. We stopped shooting at 24:22 after the hour. It was hailing when I turned the camera on, but it was very, very sparse. I had to go through, I think, about 3 minutes of images before I found even maybe a small stone that passed through the area. But yeah, so we just had like just random, they were rounder. I didn't get, for some reason we didn't take any pictures of them. We measured them, but they're about 1-inch stones, but very, very sparse. Skip the first one. So as we transitioned out of that sparse rainfall, stones obviously got bigger, and I could see visually some things had lobes on them. And it picked up intensity until 0019. So like I said, it took 3 minutes before we start transitioning. And then it really picks up intensity over the next minute plus after that. Radar data is kind of what you expect. High reflectivity, ZDR around 0, a depressed correlation coefficient, and KDP's not all that high. So here's 4 stones. These are representative. These aren't just the weirdos that I found of the hailfall at this time. We do transition from here into smooth stones, and we'll see that in the next image. So the top right, that was the stone that Sean wanted to point out yesterday, that if you take off the spikes on it, it actually reduces it by almost half of its size. You see, this is probably the top left, the 1929 stone. This is probably the most spiky nature that I've really seen. Usually what you see though is more kind of the one below that, my gnome, as I call them, the bottom left. You get these just kind of weird lobes that come off, or you have like what looks like almost smaller hailstones stuck on the side of larger ones, which is really illustrated in that bottom right. So the hail intensity really picks up. I didn't make an image because there's not a real good way to kind of show that, but you can see in the image there's just a lot of oblate spheroids. They all have water tourists on them. I think they're around golf balls. We didn't do the math on these stones in particular. Some of these were pushing a little over 2 inches. But again, it's everything you would expect when you're in intense hailfall. High reflectivity, ZDR is down around 0, depressed correlation coefficient. We got a little bit more KDP, but some rain came in with these rounder stones. So this went on for, I think, about 2 minutes, and then we maybe? Oh, no. Oh, there we go. Then we transitioned back to where we got a better mix than the first time around of round stones, and then some of these stones with lobes and spikes. So you can see in the top image with the loop, there's plenty of round stones in this image, but then you also see one that goes through that's got like, looks like 2 little arms. Kind of highlighted again in this middle image. Top left, there's a round stone with a torus shell. On the bottom, you have a football. I guess it's the best way to describe that shape. And then we have this weird elf sword, the 2227. I didn't really know what to make of that. It's actually a very flat stone. When it falls and spins around, it's actually a very flat stone. It's mostly just along one axis. Radar data is kind of as you'd expect. Basically, what happens here, all the stuff with lobes kind of disappears, the hail intensity decreases. We go back to spheroids, those slowly decrease in size, and it turned off on a dime. Like there was lots of stuff there in one frame and then it was all gone. So it was pretty fun to watch. So I saved our favorite stones for the last slide here. I'm going with crawdad shaped on this. We got a tail, got maybe 2 little arms. But the big takeaway that we got from looking at all these images is tumbling is very, very random. It is pretty much only random. Similar geometries will spin different ways. Similar geometries will not tumble at all. So that's kind of what I'm highlighting here. This is a very odd shaped hailstone, but the top one, rotating just on the horizontal axis as it falls. The top, or in the bottom one, it's rotating on the vertical axis as it falls with no other stuff. I have some other points on here, but I think I'll just stop and take any questions.
All right, questions both virtually and here in person. Got one there.
A very nice talk, and I saw a lot of like apple fruiter type of donut shape, and also even Oscar statue. So that's beautiful. But I wonder, have you actually think about deploying a like a hail pad at the same time? Then when you look at it and look at how to hit the pad, and actually can provide more information.
Yeah. So that's kind of the bottom one. When I got done and was looking at images, I really wished we had moved the cameras down slightly so we could see the bottom of the truck. We didn't have a lot of time. We got done with perils. I had 2 weeks to program the computer. We had 2 weeks to build the truck after that, while Sean was also building other trucks. And we were debating all sorts of stuff. Do we put down kitty litter? Do we go get sod? Like, because we were also trying to just preserve, you know, the stone shapes without them breaking. So, but yeah, no, some thought went into it. We'd love to do that, to add it to the system, especially if we keep it truck mounted to where it can just be in the back.
Yeah, great capability. Thank you.
Thanks.
I have a question from the virtual realm. How expensive was the camera to build?
There is it 30 total per?
30 total.
$100. Yeah. So like 50K. Yeah.
Yeah, usually.
Amazing talk. I think is extremely interesting. First, it's very interesting that the Hailstone tumble completely randomly. Secondly, like, do you have any idea on why, like, physically, why do you think they tumble randomly instead of like fluttering as some literature?
Why it's completely random?
Yeah.
I don't know, and I wonder, the other thing too is this is near the surface, so I'm like, how much can we bootstrap this back? One thing I didn't notice a lot in any of the images is collisions. Typically the only time we had collisions was with debris from stones that burst apart and hit other stones that fell. So I don't know, at least at the surface, it doesn't seem like hailstone collision is why they're spinning. So yeah, I don't have a great answer for that.
My second question, this might be super naive, but is there a possibility you can actually do this at a higher altitude?
So we're thinking about it. Jeff is kind of the one pushing some of this. Me and Sean are just like, okay, we can try to make that work. Really, the biggest problem at altitude, the best solution we can come up with is it has to be a parachute-borne system, which how long is the parachute going to last? And then the weight. The weight concerns are what we're hitting. Sean's imagers already are hitting the ceiling, and it's 6 pounds. So.
Thank you so much.
Now we've got a virtual question in the back, so I'm going to take it back to Brian.
What is the maximum distance that the camera can capture pictures in the field?
How far away?
Yeah.
So the good field of view started about 1 meter from the camera. We lost light at almost 2 meters. There just wouldn't be enough light to get a clear picture. Really, we were just aiming to get about midway from the truck bed to the tail. So.
Henry, I'll say you guys are.
Yeah, this may seem like an odd question. I'm just curious what your truck looks like. Do you have to have special insurance going out into these hailstorms all the time?
Sure, right?
Yeah, luckily it's U.S. government work, so we're self-insured. But it does have a hail cage, so we try to preserve the windshields as much as possible. The reason we lost the windshield on our truck is I dropped a channel nut on it when we were constructing the rack. So.
All right, thanks, Kyle. It's awesome stuff, and let's give Kyle a round of applause. Thank you. And yeah, some of the same things that Andy, Julie, and I observed in with the big vertical wind tunnel tumbling showed up in some of those images, including the kind of rotor activity of a very oblate stone. So big future there, I think. So our next speaker, we're going to turn it back over to the virtual space. Josh Soderholm will join us remotely. And Josh is going to talk about a little bit of automating analysis of hailstone layered structures. So Josh, if you are on the virtual space, it is all yours.
All right, thanks, Ian. Okay. All right. So today I'm going to be talking about a new method that we've been developing for automating the analysis of hailstone layers. So this is work by myself at the Bureau of Meteorology in Australia in collaboration with Matt Kumjian at Penn State. Cool, okay, it works. All right, so starting off with a bit of introduction, I'll keep it brief since probably many of you are very familiar with these concepts. So what's important for this talk today is hail growth. And we know that inside hailstorms, hail growth is quite variable in response to the conditions. And this leads to different layers inside the ice of glaze and rime ice. So the ice opacity itself, so this glaze and rime ice, it's related to the size distribution and concentration of bubbles which are trapped during freezing. So freezing itself is actually what determines these different characteristics of the bubbles, whereby instantaneous freezing traps many very minute bubbles in high concentrations, which gives us our rime ice. And we call this our dry growth regime. And if freezing happens more slowly, lots of this air is released during freezing, leaving the hailstone surface wet, and we call this our wet growth regime, and it results in our glazed, clear, transparent ice. And as a result of that as well, we can see that the growth regimes, our dry and wet growth, are very sensitive to the hailstone surface temperature. And this in itself is a complex interplay between the environment, the ambient temperature, of course, and the liquid water content, and also the properties of the hailstone itself. So in effect, hailstone layers are actually preserving information about the growth conditions. And this is not so dissimilar to paleoproxies, which we use for climate reconstruction, such as tree rings, corals, ice cores, etc. So what we are possibly looking at is a treasure trove of information that we can start to explore with modern technology. Simulating these growth processes is equally as important because it's starting to open up many new doors for understanding not only hail production processes, but also improving our prediction of hailstorms. We've seen explicit simulations first conducted back in the early 80s and more recently in the 2000s with the availability of increased computing resources, making it possible now to simulate millions of hailstones. However, this is quite a complex problem to solve. It requires many assumptions, such as those listed on the right: force speed, collection, vapor diffusion, thermal balance, different growth regimes, soaking, shedding, ventilation, and of course, embryo size. And many of these are poorly understood. The ultimate assumption, of course, is simulations treat hailstones as spherical particles, while of course in nature, they're much more complex than that. So this is where we believe observations can step in. Currently, these simulations of hail growth layers and hail growth processes lack validation from natural hailstones. And we believe the statistics of measured layers can potentially be used as a source of evaluation. However, traditionally, the approach for assessing measurements of hailstone layers from cross sections has been very tedious and essentially impossible to measure things such as the layer area. So the question now is, how can we do better? So this is where the layer analysis technique steps in. This technique was developed with the intention of filling this observational gap. And you can find a preprint of the paper now. It's up for review in AMT. So like any analysis of cross-sections, it starts off with our preparation and imaging. So for the purpose for this project, we were extracting 2 to 3 millimeter cross-sections using a hot wire tool. And then these cross-sections were mounted on a glass plate for imaging inside a light temp. This cutting and imaging was conducted in a cool room, not a freezer. This makes it a lot easier to handle hailstones and process them. And also we found the water coating quite beneficial for the photography. The only manual process in addition to this is identifying the embryo center and also creating an outline using annotation software. So the next step is where we can begin the automated process. And to begin with, we take the cross-section image and the information from the annotations of where the center is, and a series of radials are constructed around the hailstone radiating from the center. Pixels are then extracted along these radials. So the information in these pixels, we're looking at the lightness field, and this is used to find the opaque layers. So this is our dry growth layers and also the edges of the hailstone. So first we look for the peaks in these layers, and then we can calculate the width. What does that look like along a single transect? So here's an idealized representation on the left. We have a radius on the x-axis, lightness field on the y-axis, and here we're picking out 3 distinct peaks in the lightness field, which are our dry layers, our opaque layers, and also the edge itself. And from there, we can also calculate the width of these areas as well. The next step is the more complicated one, where we aggregate all of these transects together, and we actually cluster them to identify layers across the whole hailstone. From these identified layers, we then calculate their mean radius and also the area. And this information is critical because it allows us to calculate the equivalent circular cross-section, which is essentially what a simulation would see, preserving the layer area and the mean radius. So what does this look like on a real hailstone? On the top left, we have a cross-section image overlaid in red with the annotations, and the blues with the radial transects. Right to that is a plot showing in the azimuth distance space the identified layers across all of those transects, where the opaque layers are shaded white and the wet growth layers, the translucent layers, are shaded grey. The plot C on the bottom left shows us the aggregation process, where we consolidate all those transects up to find the layer centroids and also the layer widths by which the area is calculated. And finally, the equivalent circular cross-section can be generated alongside statistics. So for the purpose of this paper, we used a relatively small collection of hailstones sampled from a 4 square metre area, a hailstorm in Melbourne, Australia, in early 2020. You can see a composite image of all the cross-sections on the left there, with sizes ranging from 18 millimetres up to almost 60 millimetres in maximum dimension. And on the right, we have the representations of their equivalent circular cross-sections using the layer analysis technique. As part of the paper, we briefly looked at some statistics which focus on wet growth contribution, which particularly interested us because we know that that contributes towards the larger sizes. We found, first off in plot A, I've just got a simple plot showing the shape, the axis ratio against the maximum dimension. See, we have a distribution of hailstones, varying axis dimensions all the way from 0.2 up to 0.1, and sizes from just below 25, in this case, up to 60. The next plot across plot B shows us the total wet growth fraction as a percentage of the total area versus the axis ratio, and plot C, the yellow plot, shows us, again, the total wet growth fraction, but this time against the equivalent dimension. So we can see, surprisingly, that the wet growth fraction does not change significantly with different axis ratios or different dimensions across the data set we sampled. Furthermore, plot D shows us the final wet growth fraction, so the outermost wet growth layer, as a percentage of the total area. And surprisingly, for smaller hailstones, we saw, on average, larger final wet growth fractions. So this really points to a conclusion for us that wet growth is important not just for our very large hailstones, but across the whole spectrum of hailstones. The final part of this study, we looked at performing a comparison, more of a first look, against model simulations to demonstrate how this approach could be used to compare bulk statistics. And to do this, we use a collection of simulated stones from the UMax 31 simulation provided by Matt and Kelly in their 2020 paper, for which we selected a sample of 40 hailstones which matched the same size distribution as the observed sample in Melbourne. So of course, this simulation is a totally different storm environment, a totally different case, it's idealized. However, it still lets us look at how we can approach the problem of evaluating hailstones using this data set, and also potentially suggest some early indicators of problems we may have in the simulation. So the statistics we got out from this are shown on this slide here, where on the top, we have on the left, the total wet growth fraction, and on the right, the final wet growth fraction for the simulation, and on the bottom, the same again for the Melbourne collection. We can see for the simulation that there is really excessive wet growth apparent across hailstones of all sizes, particularly the larger stones, both as a total fraction and also the final fraction itself. This suggests potentially, really leaning out there, that there may be a positive bias in the fall speed or liquid water content in the simulation, or potentially it's our spherical treatment of hailstones, which is resulting in a lower thermal transfer. When we look at the same results from the Melbourne collection, we can see our wet growth fractions are much lower in comparison. So in conclusion, this approach provides a new automated way of measuring the area of layers inside a hailstone. We believe this is going to be a powerful tool for assessing growth characteristics and also evaluating our simulations. Next step, of course, is a larger collection of hailstones, ideally hundreds, co-located with intensive observations and also simulations for the case that was observed. And of course, what we believe we've really only scratched the beginning of what can be done with hailstone layers. So there is more information in there on their growth preference, depending on the embryo orientation, and also things like the shape evolution as well. And these could potentially be new tools, new data sets for evaluating simulations of hailstone growth with natural shapes. And I'll leave it there. Thanks for your attention.
Thanks, Josh. Any questions for Josh, both virtually or here? Julian, up front.
Josh, Julian here. Great talk, very interesting.
Thank you.
Just a question about your comparison with Matt's modeling. Was the UMax 31 environment similar at all to the Melbourne sounding? Maybe that might explain some differences.
Yeah, the simulation itself did have a high liquid water content, so it was also more strongly. The bulk shear was also stronger as well. So we would expect there to be more wet growth, but to see a saturation wet growth like that, that may be a sign of something else again. So it was only intended to be a first look at what we can do. And we can definitely see that with a co-located simulation with the observations, we would be able to perform a true comparison.
All right, any more questions? I see a couple hands up in the virtual space. I know Conrad's in there. So Conrad, if you want to unmute, jump in. I think that's Joseph too, but Conrad will take yours first.
Thank you. Josh, great talk. And just quickly, I really hope that this is very important work that should be supported as part of the NSF funded IceChip project. So just one question. At least in one example, it was intriguing that when I used my eye to trace the shapes of the outer layers of milky and clear ice layers, that is dry and wet growth in a bulk sense, it seemed as if the lumpiness or even lobiness tended to grow in the wet layers, and it tended to attenuate or fill in to some extent in the dry layers. And I wondered if you saw any pattern like that, and whether you have actually tried to fit the individual dry and wet growth layers in your observed hail. Thanks.
Yeah, we saw a whole spectrum of remarkable things in the image, which we just couldn't dive into in this paper. And one of the things is the difference in shapes that you get with persistent dry or persistent wet growth. So it's definitely something which we want to follow up on because we know all the information is there within the images. And I agree, it should be something which we can potentially pull out how the shape changes as a function of the regime. Thanks for the question.
All right, we can keep going. I see another one online there. I think that's Joseph if I turn my head and squint over at the monitor, but yeah, go ahead.
I'm not sure if you're calling on me, but I'll go.
Yep, we got you.
Okay, great. Sorry. So this is Charles Jackson. I was wondering if the environments in which this hailstone was formed could be analyzed using isotopic composition analysis. So looking at each of those layers and looking at how the isotopic composition would vary and thinking about the environments within the convective cloud and what was happening there. So I know it's very uncertain, like how that all works, but it's just interesting to have actual samples, right, of the water vapor and or cloud, and having that, basically being able to collect that and analyze it just seems like an interesting line of attack.
Yeah, I definitely agree. It definitely is an interesting line of attack. It requires much more specialized lab equipment than what we use for this project. But we would, as with proposed field projects in the future, we expect that those observations will be taken at the same time as these cross sections. So then we can start to compare both data sets alongside one another.
Is that being considered, or is that just out there too hard?
Definitely in Australia, it's a little bit more difficult for us, but I think within the US, with the facilities available there, it's quite feasible to do.
Thank you.
Thanks, Charles. Sorry about that. I had my bifocal moment trying to read the screen. Any more questions? Andy up front. I'm gonna look back at Brian if there's any in the chat. All right, Andy, go ahead. We got time for one or two more.
I was going to ask exactly the same question. And Matt, from his modeling calculations, could also somehow put in isotopic composition, or at least the temperature at which the condensation and deposition and collection water droplets occur. So that would be a possible way to compare things, as well as, of course, laboratory experiments.
Okay, any other questions? Thanks, Andy. Any questions for Josh? All right, thanks again, Josh. Thanks for joining us virtually. We appreciate it.
Thanks, Ian.
All right, let me see if I can read my own small print again. Next speaker, Anthony Bernal Ayala. Anthony's going to talk a little bit about looking at particles within hailstones captured in Cordóba-Argentina. All yours, sir.
Thank you very much, everybody. Thank you for the workshop to give me the space to present to you the cool research we've been doing in collaboration with the National University of Córdoba and the University of Wisconsin. I do want to start this slide with saying how privileged I have been to study the area that I actually have cut and actually experienced these hailstorms. And, you know, this wasn't possible without the international collaboration of the regional government of the Córdoba province, the National University of Córdoba, and then, of course, the University of Wisconsin, where my funding comes from. There you go. Nope. So the first thing is the research motivation for this project. So Córdoba province in Argentina is a region where the most intense storms of the world occur, right? And the hail occurrence, of course, impacts these damages, increases the damages both in property and agriculture in this region of the world. Now, the challenges of understanding or predicting these hailstorms in this region come from the incomplete understanding of both the internal controls and the leading environmental controls of the hail inside of the cloud. if both the main environmental and storm internal controls of the hail occurrence in the cloud. And in previous studies that we recently published in Bernardo in 2022, we had verified hail collected in the Cordóba region that was correlated back with the GOES ABI satellite imagery, showing promise in satellite-based proxies for detection in multiple environments and different storm modes. And this actually was the base of how this project was born, and it actually is based on my master's thesis at the University of Wisconsin as well. So previous studies that use hail proxies have noted that these deep convective systems in the region are characterized by three main environmental parameters. The first one is the increased humidity provided by the South American low-level jet. The second one is going to be that dry air subsidence at the east of the Andes, which is going to create this cap of the low moist layer. And finally, that sorry, I'm a little bit nervous today. And then finally, that upper level trough that is going to create I missed my thought again. That upper level trough that is going to, and the upper level trough, which is going to be part of this main environmental controls. Now, there's two systems that were focused on the previous case in Bernal in 2022. It was one in December 13-14 case, which was actually discussed already in the last presentation yesterday, which was a hailstorm, a mesoscale convective system, which exhibited all these three environmental parameters. While on the other hand, the secondary case that is focused on Bernal et al. In 2022 is a supercellular convective system that developed on 8 February of 2022 that actually exhibited more local forcing. What do I mean with more local forcing? Upslope flows that actually were assimilated to assess that elevated instability needed for this storm. Additionally, there's research that talks about how the aerosols would impact what temperature ice nucleation can happen in the cloud. And with having that in mind and having large scale forcings in these types of conditions, we start thinking about where this air is coming from and whether that air of that large scale is enforcing aerosols from outside of the country versus more local regions as a supercell in 8 February of 2020 and 2018. So with this in mind, the goal of this research is to identify possible regions, and when I mean regions is whether mountainous versus agricultural settings of particles found in hail sample to further our understanding of hail formation in this region. This study identified non-soluble particles in the hail sample of the 8 February of 2018 supercell, and our main, or the questions that I was attempting to answer before this conference were, are the particles compositions from organic or inorganic origin? And what is the relative contribution to the hail sample? And what I mean with the relative contribution is the particle distribution through the hail sample. So what are the methods that I used to try and attempt to address these two questions? So the first thing was to process the hail. So I had the privilege of using the Laura Levy atmospheric physics laboratory in the National University of Córdoba. We processed the hail at -12 degrees Celsius. We basically took measurements of the hail. What do I mean with measurements? So we measured the lows, we took the height, the weight, we look at the asymmetry. We look at we took the weight of the hail. Once we did all those observations and we took lots of pictures of the hail, we then proceeded to glue that hail to a glass thin section using ultra-filtered overcooled water. And over that glass section, which you can clearly see in this picture over here to the right, we then proceeded to glue that hail to a metal section, which would help us have a grab of the hail to actually go in further and cut the hail. The next step was to cut the hail in half. We used a diamond encrusted disc of a 10 centimeter diameter. with a 22 millimeter width of cutting width. Once we had all the equipment set up, we proceeded to cut the hail. We measured 2 millimeters above that equatorial symmetric plane that I'm showing in the slide. And then we proceeded to cut the hail. We saved one portion of the hail for further analysis, for future analysis that we can do on that hail. And that secondary slide of the hail, we actually polished with a microtome until the desired thickness was achieved. And once we achieved that thickness, we used a solution called FormBar, which is a 4% 1,2, and I'm sorry if I'm going to butcher this word in English because my main language is Spanish, but it's 1,2-dichlorotorian, is 1,2-dichloritano for those of you who understand a little bit better that way. And basically what we use this solution is to actually, it's a novelty. We're still working on this method to be published, but we're trying to trap the particles with this solution. And eventually you'll see how I'm doing this. So once I put a specific amount of droplets, so you can't put a lot of the solution because like I did, you're gonna mess the sample because too much of the solution is unfortunately going to prevent the sample from being analyzed in the further analysis that I'm gonna show in the future slides. Once we pour the solution on that slide of the hail, we left it in a low humidity sealed container with silica gel to let the sample sublimate, and once for a minimum of 40 minutes. And then after those 40 minutes, we then proceeded to do the secondary analysis that we were hoping for. So the first analysis that I was looking for is to use, so again, the very cool thing that I do want to highlight is how the sample actually looked after being sublimated. So this is basically already the hail sample after 2 or 3 days of being sublimated, and that is the FormBar solution that I talked about. Once that is done, we actually are going to do some laser confocal scanning microscopy to create a 2D map along that axis of the equatorial plane of the hailstone that I previously mentioned in the slide before. Once we do that, we actually are going to divide that 2D plane in 46 sectors to pick around 80 randomly picked particles to look at the size, to look at the particle, the topography and the optical properties of those particles. Once we finished the laser confocal analysis, we then proceeded to go coat that sample under a high vacuum chamber to then proceed for the scanning electron microscopy analysis. We did two main things in the SEM. We did SE and BSE imagery, which is secondary electron and backscattered imagery. And then we also proceeded to actually do EDS analysis on the particles, which is, and sorry, there's a lot of acronyms there. So it's the electron dispersive X-ray spectroscopy on those analysis. And what is going to give me the EDS is the elemental composition of the randomly picked particles in the sample. So once we had that information, we were actually be able to start and doing some correlations and actually understand what was present in that hail sample. So what are the preliminary results on that 8 February hail sample that I just mentioned and showed you how we actually processed and analyzed? So the first thing is that particle distribution on that hail sample. So we're finding particles from 20 to 16 microns in size. The average was 37.74 with a maximum size of 169.86 microns, which are huge particles. I mean, we're talking about that. Yesterday, we also talked a little bit about that sister program that went with Relampago, the cacti program. It was a 7-month survey in Austral Spring through mid-fall that actually did a measurements of ice nucleating particles at the surface. It ran from 2018 to 2019 to look at this particle. And for some reason, I had a nice series of Cordóba image to the right, but unfortunately it didn't load up on time. But I wanted to show you that the cacti fields, it was south of where the 8 February supercell develops. And that's going to come into the further future steps of this project, and I will show you why. But going back to what I found in the particle size distribution is that this might be to that cacti only did measurements at the surface, and it did not do measurements in the cloud, which is the hail is going to go as in cloud as possible. But also one of the caveats of this project is maybe that I was skewed towards picking larger particles, because I actually manually picked the 80 particles randomly. But this is going to be addressed in future work on this project as well, and I will show you how would it be. The next thing, and it's actually one of the most interesting things about this part of the project, is whether, what is the population of those 80 randomly particles? So from those 45 sectors along the equatorial plains, only 27 sectors were included in this research because of a lot of things that happened between the analysis and the lab work. But 91% of the particles found in this hail sample were organic, or at least they contain carbon. And this is an example of what I was looking at the SEM. So the images to the top are going to be the confocal and for both inorganic and organic particles. And then I compare that for the SEM imagery, which would be the single or the secondary electron imagery, which is going to be at the bottom of the figure. And you can clearly see also that the differences between them. I mean, we're having differences in angularity, we're having differences in the texture, the roughness of the surface. So we can clearly do these descriptionary observations based on these results. So what are the next steps for this project? And it's very interesting because there's a lot of things to do in order to be completed. So the first thing is we would like to calculate the angularity for those particles due to the role that it plays in ice nucleating particles to form in the cloud. So based on those BSC and secondary electron imagery, we would like to use some previous geological methods that have already been developed to actually look at how the roughness, so how rough or soft the surface of the particles are going to be, both because of the importance on the ice nucleating particles, but because it's also going to tell us the geological history of the particle, so how eroded the particle was before reaching the cloud, or that updraft that I eventually brought to the cloud. The second thing is to analyze the 8 February sample as a whole, to have the full statistical analysis of the particle size and elemental chemical composition, addressing that bias concern discussed earlier. So what do I mean to analyze the sample as a whole? So there is an option on the SEM that we can actually program the SEM to, instead of looking at individual particles of the sample, which is where the bias might come in, we can actually program the SEM to look at the sample as a whole. So it will do the EDS work and the particle size analysis as a particle as a whole, meaning that we're not going to lose any data that might be contained in that particle. So those smaller particles that maybe I didn't cut, or maybe didn't caught my eye, they're actually going to be included in that SEM projected work, and we're going to have the full statistical analysis of that 4-centimeter hailstone. We want to again, so this is going to be repeated for the analysis for the 13-14 December hail, which is an 8-centimeter hail that I wanted to add also, that occurred at 2:15 UTC on the 13th of December of 2018. And why is it important to compare to this hailstorm? Now, this, like I mentioned before, the Supercell, the mesoscale convective system that developed south of the Sierras of Cordoba was actually closer to the cacti field campaign, and it was developed under large-scale conditions versus the supercellular structure, which was developed under more regional it was developed over a regional scale. So we would like to know if there's any differences in particulate. We want to know if there's any differences in maybe also the inorganic versus organic population, but also we would like to know the angularity differences to see if we actually see more biological versus, or I don't want to say biological because we don't know what it is, but I do want to say that it contains carbon. So we want to know is whether if it's inorganic or organic. And our goal doing all this is actually link it back to identify possible source regions from which these particles were transported to continue investigating the hail formation in this region. Again, I want to highlight that this is, again, international collaborations that without the citizen science program called Cosecheros de Granizo, which translates to hail harvesters, was not able to. We have a lot of people that have been involved in this project, both internationally and locally. And I would like to stop here and take some questions.
That was an amazing talk, wonderful stuff. And as a multidisciplinary person, man, that really speaks to me. So well done. Any questions out there from our audience? I think that's Ted back there.
Yeah, what Ian said, fascinating results. So just yesterday, I came across this preprint from a group in Slovenia who did an analysis of stuff in hailstones, and they found like bacteria and interesting thing was the microplastics, the plastic fibers on like 100 microns. I wonder if that's something that you are able to see in these experiments or just haven't looked for it yet.
Up to now, we haven't seen them yet. I am working with local biologists and geologists because even though I do have a background in geology, I do need a little bit of help. So I do have some local help as well. We haven't seen microplastics yet. Up to now, we've seen pollen, very nice pollen. Unfortunately, I didn't want to show it to you today because it's from a different sample, but we've seen pollen. We've seen different indications of biological, and we've also seen indications of inorganic stuff based on the SEM analysis as well.
Matt and Kelly, you guys can fight over who goes first.
Really fascinating stuff, Anthony. I guess my question is a lot more broad about he's finding all this interesting stuff, insoluble particles, whatever. And so are these particles that are in ice crystals that are collected by the hail? Are they passively just in the cloud that are being swept out by the hailstone? Are they embedded in the liquid drops that create the mass that goes into the hailstone? Are you kind of, is there going to be some sort of idea of the chain of processes that gets these particles into the hail? Okay.
That's the next step. So I think the first step is to identify the particles that I'm seeing, particles that can become eventually either CCNs or IMPs, what is available in the cloud. And then the next step is how are these particles actually affecting the hail growth in the cloud? So we're in the preliminary, the first step towards that question.
Yeah, that's good stuff. Yeah, I mean, you can see the wheel spinning of trying to identify where these things are coming from and how that may give us some insights into some of the hail trajectory things we talked about yesterday. So a lot of good stuff there. Yeah, we've got time for a couple more. Kelly, I see you're up.
Can I walk up? You told me to. I was wondering about, did you look at the distribution of sizes across the hailstone? Like, was it random or did you find like a certain size concentrated in a specific area of the growth region or?
Great question. The beauty of this study is that I actually was able to preserve the location of a particle size. So I do have that's why I call it a 2D map. It actually it preserves where the particles are in the hail. I haven't looked at it yet, but it's possible to do. So it's something, thank you. It's actually something that I should consider for the future of this project.
Henry, back on back.
Great presentation. Like a follow-up to a question, how were you able to preserve the hailstones from breaking, from damage, and particles due to melting? How are you able to do that?
Awesome question. I want to highlight that these hail samples are roughly 3 or 4 years old. It's been a miracle that they're still around. It's been very difficult to preserve them actually through either power outages in Argentina or multiple things that have happened. The beauty of the study is that it's not a caveat because I was not trying to preserve maybe the structure. I wasn't looking at the characterization of the crystalline structure of the hail. But in order to preserve these hailstones, first of all, you need an ice freezer. You need like 3 backup batteries. And We use the protocols of as a clean as possible environment, so ultra pure water. We always use gloves. Like there's a paper that we follow to keep those hail samples as clean as possible and not get that environmental contamination, especially because these hails are ultra pure to water. So eventually we were trying to sublimate them, and the reason of that is once that hail passes to a liquid phase, it's going to try to absorb every contaminant out of the air. So that's why we were trying to sublimate it directly into that contained low humidity filled with silica gel. And then from there on, again, everything sealed. We were covered by every part of our body. I can definitely share that paper that we use to follow the clean protocols.
All right, thank you. All right, our next speaker is our last one before our break time. It's going to be David Deline. David's going to talk a little bit about T-28 research aircraft observations of hail. So I'll turn the floor to David.
Okay, thank you. Good morning. Today, I'd like to tell you about a project we're just started in. This is a National Science Foundation funded project. That's a collaborative project between the University of North Dakota, Colorado State, and the National Center for Atmospheric Research. So we're going to go back and look at historical T-28 data, aircraft in situ measurements, so not measuring the hail on the ground, but from aircraft measurements. And then we got observations from polarimetric radar of the hailstorms, and we're going to relate these two. So the basic idea here is that we take these in situ measurements, we call them, of the hail in the storm, and we rate them to concurrent or as close as we can polarimetric observations of the hail. And we compute the polarimetric signatures from the in situ measurements in the regions where we have these in situ observations and compare these signatures to the corresponding radar observations. And then once we do this comparison, we want to do a lot of work to try to understand where we see agreement and disagreement, because there will be disagreement that we will find. And in this assessment, for looking at the agreement, uncertainties is a key element to this. So we want to do sensitivity tests, compute these signatures, and vary the in situ observations within the uncertainties. So typically we have one-dimensional or two-dimensional images of these. So there's uncertainties on exactly how big these hail measurements are. We have measurements of temperature of liquid water, shape and size, some information on density, but there's a lot of uncertainties for these observations. And then we'll compute the radar signatures using T-matrix or discrete dipole approximations to come up with what we would expect the radar polarimetric signatures to be. And address, again, uncertainties in the radar, because the radar is a scanning radar, so there's time and space. It's not always looking right where the aircraft is. It doesn't follow the aircraft. It may not even sample the same location where the aircraft is. So there's going to have to be some spatial and temporal interpolations between where we have the aircraft observations and the closest hail observations in time and space. So there's uncertainties there, but we'll interpolate and come up with the best comparison we can. So a little bit about the uncertainty measurements here. And we'll start with hail observations that were identified in a previous published paper of Field et al. 2019. They have then looked at 18 flights from 1995 to 2003. So this is older data that we're going to be looking at, but we don't have to correct the data. We have it all archived, and there's 300 segments of 10-second lengths of the hail, and it's reported by the pilot. So this T-28 is a single piloted aircraft, and he would record whenever they encountered hail. We also have some windscreen audio recordings that will give us some information if it was wet or dry hail impacting the windshield of the aircraft. And of course, we have optical array probe imagery, which I'll talk about. So we want to expand this initial data set by looking at additional flight notes, audio recordings, and field notes, and go back and look at the imagery. So basically, we want to get the entire data set that's available from all the projects that the T-28 participated in. So this is like not just looking at one flight, not looking at one field project, but looking at the whole all the encounters from the aircraft with the hail. And of course, this has the implication that we're looking at different field projects, different storms, and some of the projects weren't focused on the hail, for example, and they just encountered the hail as part of doing some other operations. So this is a picture, in case you haven't seen it, of the now retired T-28, and you'll see on the left wing of the aircraft here, the old FSSP or scattering spectrometer probe, and then the two kind of vertical probes underneath the ring is a hail spectrometer that I'll show you a close-up picture of. But before I actually show you some information about the probes, I want you to get the idea of that we're flying through the clouds, so in the clouds, not on the ground, but typically they're between 6 and 7 kilometers. And you have the T-28 track that would go through a typical storm here that's producing hail. So this is a view with the horizontal and east-west or north-south view, it doesn't really matter. And then you have the height of the storm. And basically they would penetrate through the cores of these storms and a lot of times encounter the hail on this. So we don't measure every place in the storm, but we hope to get the correspondence between what the aircraft saw and the radar signature. So then you can use the radar to look at the big picture of the storms. And of course, this is to get us now using the polarimetric radar data we have available to infer what you're seeing in the hailstorms. So here's the picture of the hail spectrometer. Below the wing of the aircraft, and I got highlighted here the sample area. So as the hail came underneath, or as the aircraft moved through the air, you would encounter this hail. So this is kind of like what we saw earlier, where you see the vertically coming down and you image them. This is looking at it as the airplane flies through the storm. And unlike the nice images we saw before, you don't have, video images of this. You don't even have a snapshot picture. What you basically have is one dimensions of this, and they move through. So you don't have a whole lot of information, but we do have the size information. And with that, we can take a diameter as best we could from that one-dimensional type of view. And that's what's given here is an example of what kind of data we would have. So diameter here on the x-axis and the number concentration. So typically higher concentrations at the smaller sizes. And then as you go bigger in size, you get less and less of the particles. And you can see on the small print here that there's some maximum diameter that you can fit. You can determine from these penetrations, and shown here is spectrums over a core penetration on the same day, but you get very different spectrum. So we want to compare these spectrums and evaluate them, get the signatures of what we think the radar would see, and then compare that with what the radar has, so we can understand and diagnose that remote sensing radar data. So just some examples of the imagery and the stuff we start with. So we have some work to get this data processed so we have very good observations. So in this example is showing you two-dimensional crowd imagery data. And these are two-dimensional images of particles that are given in the red. The vertical bars are timing bars, so we know when they occur during the flight. And you see that the X and Y, here's 0.8 millimeters. So you're limited to that view, but then you have the X-axis can go on as long as the particle is within the, going through the probe. So you can get these bigger particles like at the end. So we can analyze and look at this data, but there's always some, sometimes caveats and processing of this data. So here's another example of a different probe, newer probe that was available for some of the flights. This is a high volume spectrometer, high volume precipitation spectrometer probe, version 2. And so, you know, we have this type of imagery data, but you see some of these particles here, they're not really round. And you can tell that in this, so it's timing issues of the raw data. So we have to do, we view this data, get it in there, make sure we have all the data as in a clean data set. So that's just the quality assurance that we have to do on the data. Another example from the hair spectrometer where, again, you can see the bigger particles with these, but again, the images don't look nice like we saw with the camera data. So there's some cleaning up, processing of this data. That's the low level work that we have to do. And then, of course, we have the radar data set. This data is all available in the NCAR UL field catalog. We have the various radar parameters, and mostly this data is from the chill radar, and there's some S-Pol data available that we'll be looking at. So just to give you a picture of the chill radar, both of these are S-band radar systems. So we'll get that old data and process that. And again, to show you what we have for the radar data, this is an example of a plane parallel image for one height, looking at different storms, hail producing storms. You can see the light bluish color is you know, above 60 dBz returns on these. So that would be the cores that the T-28 would penetrate through to make these observations. And sometimes they would penetrate multiple cores or go through multiple times. So we have to go and find these segments and evaluate them to compare with the radar. So basically the outcome is we want a quantitative interpretation of the polarimetric radar returns from these hail-bearing storms. We have information on size, shape, density, liquid water content. Look at the hail mass, the total kinetic energy flux for these measured hail, but observe it in the clouds instead of just measuring them on the ground, so we can refer and interpret what the polarimetric radar data is. So with that, just an overview of this project that we're just starting here. So I'll give point out that we have a student positions available to work on this project, so let me know. And if you have any questions, I'll be happy to answer that, and also take any suggestions you may have. And hopefully I come back and talk to you in a couple of years with the more results of this project.
Questions? David? Out there from our virtual folks, Matt. Yep.
Really a big undertaking, David. So thank you for doing this with all the available data analysis. I had a question about the scattering calculations that are planned. Given that you don't really have good sort of imagery of the particles and the shapes, what sort of assumptions will you be doing for the shapes and orientations and liquid water coatings and all that good stuff?
Yeah, so that's the idea is, yeah, we don't have a lot of that. So that's why I think we go back to the uncertainties. So we'll try to vary all that stuff and look at the extremes of all the things we don't know about. So, and then get the uncertainty in the returns and use that variability to get what we would have. And so that's a calculation we'll have to make to determine the uncertainties. And maybe that also help, we can maybe pin down which one of these parameters is most important to determine this uncertainty. So basically, we don't have a lot of data for the details that you could get from the lab or other places. So we're going to just have to take what variability you have and put that into our calculations.
All right, any other questions? All right, well, that'll conclude our morning session. We'll have our 20-minute break. We'll reconvene about 10:10 with our panel discussion. So let's thank all our speakers again.
Yeah.
Welcome to our mid-morning session. We're going to start things off with a panel discussion focused on kind of novel ways to observe hail. We do have a good group of panelists, and will be moderated by one Julian Brimolo, and those of you in the hail world should certainly recognize Julian and all the work he's done. So Julian gets to take this one, and I will turn things over to him to kick us off.
Thank you very much, Ian, and good morning, everybody. And yeah, this is an exciting panel for me because I've done a lot of theory, but I'm also really interested in observations. And as you all know, in recent years, we made huge advances in the technology available to us. So we have tools now that people 40 years ago probably couldn't even dreamed about. Now, the trick, though, is to get these instruments in the field, learn how to use them, and to get good data from them. So this morning's talks were a really good backdrop for what we'll be speaking to now. And we have a panel. Not everybody could make it. Jeff French couldn't make it, but Chandra's going to join us remotely. And we have Henry Regis over here. And not Sarah Bang, but we have Dan Cecil and Kiel Ortega. And I got some questions prepped, but please feel free to ask questions and to interject. I'd like to have a lively discussion. And I have prepared some of my own questions just to get things rolling. So I'll start off just with Kiel because he's closest to me. So in your dream world, Kiel, what data would you have available that would really help advance your research?
What data would I?
Yeah, or collect or have access to?
I just want more hail cameras. Yeah, I mean, really, that is kind of the answer. The case I presented was interesting because we went from, oblate spheroids, albeit they were very sparse, into lobes and spikes, for lack of better terms. Then we went back into all oblate spheroids, then back again to a good mix until it finished off with just the oblate spheroids in the end. So I think having more of those cameras in different positions, I think could really help validate trajectories, like the lobes and spikes that came out on the backside of the updraft that come from the same place as the ones that we were seeing on the front side. It was, when I was reviewing the case, was one of the more interesting. Why did they go away? And it just switched all over to round ones. So I think having more, at least for what I'm interested in and curious about, if I had more cameras to position in more different locations to get images like that would be what I'd look for.
Yeah, it's tough to get in the right place at the right time. The more cameras you have the better.
Less chance of failure.
Yeah. Any thoughts, Henry, from you?
Yeah, we, again, we're not doing a lot of research with our stuff, but it would be great to get more, again, we do hail pads having observers. So getting more folks to actually observe hail and report that would really be helpful. It's a small percentage of our 25,000 folks that do that. And again, we are widespread across the country, so not everybody experiences hail. As you know, there's certain pockets where we get a lot of that. But some way to get more involvement of people to actually, again, some hail falls at night, so they're not out there doing it, but and then find a way to actually, if we did continue the hail pads, to manufacture them and the cost. So it's always prohibitive for us as far as the actual cost. They run about $5 to $7 a pad, and you start adding up when people we put these out and so forth, and it gets expensive. So
yeah, we're using 2-inch XPS in the Northern Hail project, and yeah, it gets pretty expensive.
Yeah, so, I mean, just the labor. We what we do is we have at CSU, we have called hail pad parties, and some of you who have been there at CSU, we order pizza, and then we have a lot of the students come. We get the foil out, we get the tin foil, we tape them, but it is very labor intensive, and you only produce maybe 500 at a time during that, and so then to ship them, there's a lot of expense in that. And so in an ideal world, if we if people could get these at the drugstore and just have them out, that'd be great.
Yeah, we've actually didn't use silver foil for ours. We coated them with thin latex, and we ended up spray painting it, which went really quickly, actually. You just get a grad student, put them in those overalls, and they did a whole bunch of, I think that was 100 hail pads in like an hour.
Maybe we could learn from you guys on that.
Yeah,
that'd be great.
Well, I was trying to do it the traditional way, and that got too complicated. So, and Dan, any thoughts? Your dream data set?
Well, for my part, I'm mostly using satellite data so that we can see different parts of the world with the same instrument, but we're limited to only seeing something up aloft in the storm and not seeing down to the surface. So my dreams go to being able to add the profiling that really gets into the details of what's happening at low levels and distinguishing the large hail versus the smaller stuff. We're not able to distinguish graupel versus hail very well. High concentrations of graupel versus having larger particles with lower concentrations. So things like a longer wavelength with a high spatial resolution, that's been a barrier for us. There's some things on the horizon that might make progress there coming up in the next decade or so. And then Doppler radar, where we could get that difference in the fall velocities. And those things are also coming up in the future, but not together. So to me, what I dream about is having those types of measurements together from the same platform or in the same place, or being able to pull them together close enough in time to really make sense of the storm.
Right. No, it's challenging, and it's a pity we lost the T-28. But I'm going to ask a bit more about aircraft soon. I don't know if Chandra can join us with some thoughts.
Yeah, I've been in the meeting, so can you hear me?
Yes, we can hear you.
Okay, if I get choppy, I can turn off my video because I'm in a low bandwidth location. So I want to take the discussion one level higher, and then to see, as far as rainfall and snow is concerned, it's almost treated like a solved problem, because a lot of us were screaming for particle size distribution. If I heard one common theme in this meeting, everybody said, I need hail size distribution. So and somebody earlier to me said, we need to find this hail that happens at night. So we need to work with private sector to start sampling these in very robust instrumentation that can be bought under $10,000 and not need the act of Congress to purchase these things, or it needs a Henry Pizza Party. We need something in between. And then, because radars have come a long way, where we have this multi-frequency, multi-polarization radar can actually constrain the problem of hail shapes and distributions. Only thing that's missing is a very fine scale, like Dan said, high resolution in situ measurements. And if we as a community, I think, leverage and then make a few devices that can be deployed, I think we are dealing with a low-hanging fruit, and this meeting goes a long way towards making that proposal. So we need a concerted effort, and I think we have a good chance within our lifetimes to constrain this problem.
Right. No, good points. So with the radar, how far away do you think we are, if at all, of being able to discriminate between N and D in the radar equation? So lots of smaller hail versus fewer big stones.
I think if we use multi-frequency, multi-polarization, and Dan Cecil said combined with Doppler, and then I don't want to solve the problem in the panel discussion. There are solutions available that, but only thing is missing is you can come up with all sorts of things, and then immediately people will question the truth. We need to have in situ observations. There are enough multi-frequency. That's the way it was solved. And solved is too strong a phrase in our community. We never solve anything. We make progress. For ice density, 3-frequency measurement was finally seen as a solution. So as far as the polarization response goes, it has a good handle on the hail surface protuberances and roughness. And then we have multi-frequency, then it can give some information on sizes. But I think still dealing with absolute reflectivity, one of the main challenges is going to be this grapple versus hail problem. I myself have been dealing with, like Dan said, because of the density variation, grapple versus hail problem will probably be one of the first problems we will tackle. And then we will probably find a way of parameterizing the protuberances. And then right now, even the hydrometeor classifications are starting to, instead of giving up on explicit size and go small hail versus large hail. These things, because of their fall behavior, like Roland List used to say, put a perturbation, precessing type of fall, we will start understanding this more. So I, again, want to echo something that was said before. We are at a good point where a lot of the technology is available, and then we need a few more coordinated in situ hail campaigns.
Right. No, good point. And again, and a shout out to IceChip. Fingers crossed that funding comes through for us. The one thing we're not going to be able to do in IceChip, and I'll start with you, Dan, is have in-cloud measurements, because we don't have an armored aircraft that can go into the core. So is there any way you see that we can somehow sidestep that using dual polarization data maybe to get a better idea what's going on aloft in storms that might help your algorithms?
I think, boy, if we could get the in-cloud aircraft, that would do so much. But without that, the polarization radar from the ground, together with, if we can get, and I'm hopeful from the NASA side that we might be able to pull in the over the storm top aircraft with downward looking radar, Doppler, and multi-frequency. And I think that would add a lot. I think Chandra kind of likes that idea a little bit. But if we could add that in for getting the Doppler velocities at multiple frequencies and a good resolution with those, I think that would be a huge addition we could make. There's always going to be the uncertainty from not having the direct measurement inside the cloud.
Right.
I don't think we ever get all the way around that.
Okay, good. So would you be able to flash
sorry if
like
I can Sorry if I can interrupt. The cross-pole measurements that come from airborne flying is really valuable for hail.
And mentioning, I should add, mentioning the hope that we can get the over the storm top aircraft and the downward looking velocities, we would still be able to, and we'd still rely on having a good ground-based look for being able to get the temporal evolution in between the times that the plane goes over. Because your plane goes over, you get a great look, and then 10, 15 minutes at best for getting the plane turned around to come come across it again, and things happen very fast in these storms.
Right. No, I agree. Yeah, is somebody pursuing that line of funding to get those data?
We're trying to, yeah.
Right. And going back to surface, you were mentioning the importance of surface. So Henry, right now you're very US centric. I'm sure that wasn't by design, just, word spreads slowly. I see things are expanding in Canada. Another area that I think would benefit greatly is somewhere like Europe. Like, do you think they have any plans in Europe to have a similar program? Do you have colleagues in Europe who might be interested?
Yeah, it's funny. I work with the WMO. I'm on a couple of committees there, and I guess Media Swiss has done some stuff with this. I know in Portugal at the meeting here back in 2018, they were using cell phone reports and so forth. So I think that's getting traction for us. We probably don't have any plans for Europe right now, but I think with the all the hail going there in some of the Alps and other places, that it would be a good model to get more citizens involved in this. So I don't know of any specific plans right now, what they have, but I think it's a great idea. And other parts, again, we're in the Bahamas where there's not a lot of hail. We're in the Puerto Rico, just expanded to Guam. So those are not really hail-prone spots. Canada, we're close on the border. We'd love to get more folks in Manitoba, Alberta, where they do have Edmonton, that whole area and stuff up there where there's a lot of hail. It's funny. I was at a meeting a couple of years ago, and they talked about the Weather Service in Alberta. They said that they had to stop putting out the prediction of hail in their forecast because a lot of people were taking cars out of their garages and putting them out to collect the insurance on that, which I thought was a funny story. But anyway, that's an anecdotal thing on the side.
Oh, yeah, I haven't heard of that before, but I can understand that some people might do it. We joke in Alberta that you can always tell when a car's from Calgary because it looks like a golf ball. And they'll have lot sales after a big hailstorm. So yeah, you can get a good price on a car if you come up to Calgary if you're from like Montana or somewhere. So Keel, your system's great. It's also very expensive. So is there a way you foresee making a poor man's version of it? Doesn't have to necessarily capture as much information as you are, but we'd still get D or D max and the full speed?
Full speed, yeah, a poor man's version, full speed would even be tough because you're probably still going to need close to 100 frames per second to at least maybe catch a stone twice in the image. Is that about right? I was like, we went through the math. I mean, the first imager was fairly cheap. I think you could do it for under 10K. And really what you could do there is just confirm sizes compared to what you were picking up off the ground. Because it does run. It's 12 megapixels as well. The only difference was just the computer driving the camera. The one that we use for the faster frame rate was obviously bigger and cost more. So if what you're wanting to do is have other instrumentation out and just maybe have an idea, then yeah, you could do something like that. It'd be for a few thousand.
Right. I mean, the GoPro comes to mind. They're pretty good on the frames per second, but their exposure is not great.
Yeah, and that's the thing is we were talking before. We did have a GoPro on a mesonet for some intercepts during rivers field project a few years ago. And what I ran into when trying to slow those back down was the interlacing, and they would just kind of destroy the stone. So you couldn't even really see very clearly even what the stone shape was, even for stones landing close to the camera.
Yeah, so I guess you don't have the skill set to hack a GoPro and ramp up the or reduce the exposure.
Yeah, no, I don't. I'm actually not even familiar with how it handles exposures and low light and stuff. But I guess if you also pile in big lights. You know, the lights that we put on are only about $100 a piece, and they're pretty bright. So, so that you could kind of maybe get to a quote unquote poor man's version that way.
Okay. And it sounds like the next step is maybe to try and collect, like build a hail trap to collect the stones to compare with what you're seeing in the imagery.
I think, well, the immediate next step for us is to get automated processing to where like that's going on while we're collecting data, so we don't have to go back and do it again. I think that's really possible with just keeping everything on the GPU. The next step after that, I think, is just a method of collecting stones. Whether that's, you know, if we get a bigger truck, you know, putting a cone like the NCAR setup, you know, that I presented, and then just kind of funneling hail through the vehicle or even through the bed, or putting some sort of soft material in the bed to capture stones, maybe with, you know, some cooling underneath, you know, some dry ice or something. So, but yeah, I think those, at least for the physical trucks and trying to collect hail, yeah, that's probably the next step there.
Okay, so we're about halfway through. So I don't know if anyone had questions. Oh, okay. Okay, sounds good.
It was more on a following comment on that of expanding the citizen science program. So as I mentioned in my presentation, there's a citizen science program in Argentina called Cosecheros de Granizo, which is hail harvesters. They actually expanded to now taking tornado reports, any atmospheric activity that you can possibly imagine. It has expanded, and we were looking into kind of expanding to worldwide to start creating the much necessary hail archive, because, you know, one of the caveats of this is that every country has its own way of reporting it. Maybe they're saving it for their own research purposes, and we would like to kind of start doing that collaborative work. So I do encourage you to look it up. Is Cosecheros de Granizo in Argentina. It's a very solid base, and I think one of the key things is that even me, when I went down there, is going to those schools and actually spreading the word. So I always had rulers on me. I always have pamphlets. I showed people about weather, about hail. I mean, they look at it. For us, a 5-centimeter hail is big. For them, you know, that's very small. The minimum they'll see is 8 centimeter, 9 centimeter, depending on the region. So I think that reaching out, it's going to be the most key important thing to expand a program like that. And I think it would be a good thing if you look it up, and you know, eventually in the future we would do collaborative work as well. It would be great.
Yeah, I really appreciate that. You know, a question I guess I was going to ask for the audience here, or anybody, is what are we doing to educate the public on hail? There may be things out there. I may be ignorant, not knowing. You know, you watch NOVA specials. They have them on tornadoes. They have them on hurricanes. Has anything ever been done on hail? And some of the research in that, or what is, you know, just I think if the public starts learning more about hail, what the process are, they may be more inclined to report it or more engaged in that. And it's probably one of the few things that we don't, and again, you guys can school me on this because I don't know what is going on that, but I think it would really great thing to see what we could do to get this more educational stuff out there.
Just one quick point there. The National Science Foundation with Relámpago actually started creating this campaign to go to schools and actually talked about hail in the region. And that's where it all started, you know, showing the kids how to look at clouds, look at hail, and then it kind of motivate them to report them and to say, hey, Daddy, after the hail report, please be safe, and then collect that hail because I'm going to call the university to collect it. So yeah, it's part of the.
You wonder in places where it doesn't hail if people would be interested. You know what I'm saying? If this is more in the hot spots, that people are more likely to do that. But thank you. Thanks.
Henry, can I add to that?
Yeah. Oh, go ahead, Chandra.
So this is an anecdotal example from India. So a lot of people in India thought it doesn't hail that much there, until they started deploying lots of radars. And then now suddenly people are starting to see a lot of hail. And yesterday there was a presentation from Australia, the first one. And then if you also noticed, a lot of the hail distributions were very close to where the radars were. And as the world is starting to put out more, I think more and more people are starting to see hail. But there is a little bit of downside to this in India. When people see more hail, they're starting to blame it on climate change. Oh, now it's hailing more because of climate change. So I think this hail campaign and then having more instrumentation, I totally echo the sentiment here. Public education is very important.
I think one thing related on this is there's a challenge in different parts of the world, or maybe different cultures, or even just different people. The question of what is worth reporting would come up. In the US, we have this from the Weather Service, there's the standard of 1 inch hail is what they mean when they talk about severe thunderstorms. So if it's smaller than 1 inch, maybe you don't bother reporting it. In some places, maybe any little piece of frozen ice you report as hail. And along those lines, I've heard that in Spanish, there's the same word for hail or sleet or any other type of solid ice. And for that matter, in English, we have graupel, but most people don't know what graupel is. Some people will make the distinction between hail and sleet, some would not.
Yeah, to Henry's outreach point, this is a lot of the work we do at IBHS is trying to, one, engage with folks to get them interested in it, because it often leads them from our standpoint into the mitigation element, whether we're asking for better building materials, things like that. I'll tell a little bit of a story on that note. When we went out to check and see if the Salado hailstone in Texas this past year was close to the previous year's Texas record. The person, the homeowner who found it, she was actually one of the local high school principals, followed all the steps. We had actually put in a PDF guide of how to go do it. And she just happened to be kind of interested in it. And I remember talking to some of the folks at the WFO in Dallas. They were shocked that she followed she bagged it up, sucked the air out of the freezer bag and stuck it in the freezer and called or sent a Twitter message to the Weather Service. And it was very interesting to see the engagement. And I feel like you see more and more, like hail's kind of engaging. It's a new thing. It's maybe we're bored with tornadoes. I don't know, but it seems to capture a bit of the public's imagination. And for us, we try to do a lot of that outreach. So if anybody, we've already talked to Southern region about helping with some of their materials for outreach related to hail. So I just throw the open invitation to come work with us in IBHS if you have ideas of how to reach or want to develop some local programs and things like that. We're more than willing to, one, provide materials, do whatever we possibly can. So,
you know, maybe hail cannons could be the hot holiday gift this coming season. You know, get your dad a hail cannon for Father's Day.
I will tell people, if you're ever having a bad day, you go back in the lab and you go shoot a bunch of hailstones at a shingle panel and you'll feel better about things. So I know we have an online question, so I'm going to go back to Brian back there, and I see John's up at the podium here, but we'll just keep this going.
Sure. This question goes back to the beginning of the discussion. There's two parts to this question. The first, what are the advantages to using hail pads versus other ground-based sensors? And what is the state of the art for current ground-based hail sensors?
So I guess I'll take a quick stab at this one. So for hail pads, it's a cheap way, well, not cheap, but compared to some of the other ground-based sensors that are out there for the average person to have. You can look at them. We can take them back and analyze them. They're nice artwork. You can hang on the wall, stuff like that. But I think the economic piece is helpful for that. And again, when we put the hail pads out, we put north, and so we can look at the angle where the hail fell and get some information from that. But there are, I think I saw out there a new hail sensor that you guys are doing. I know John Lane did some stuff with NASA for we tested some of his acoustic things out there. But again, those are expensive, and to get those deployed in a lot of places, you never know where the hail is going to show up. So yeah, I defer to you guys on.
Yeah, state of the art, I don't know. I mean, Andy's got his hail distrometers, which are really great, and they're actually not too expensive compared to some of the acoustic systems out there. We also have optical, but optical has its own challenges, as Hill can tell you. I've been, this summer we've been trying to use a fancy trail camera, because I don't know if any of you do hunting. I took my daughter to Cabela's and she's still a little traumatized after going to that store, but she's never hunted anything in her life. But I was there for a trail camera that you can use 4K imagery, and you can set it over the cellular network, and it's got a motion sensor on. So the thinking is, well, we can point it at the ground, and you can see hail underneath, and you'll get a message instantly. But even that has its challenges in that we've got lots of pictures of mice, but no hail yet. So, but those are about $400 to operate something like that. So that's one thing we're looking at for the Canadian prairies, if we can prove its feasibility. I think the costs are coming down.
I will have a hail pad at my poster tomorrow, and I'll bring one if you guys want. I've never seen one or held one. You can kind of see how it's made and stuff like that.
John's been very patient.
Julian, I'll just jump in on the hail pad point. Part of the advantage of using a hail pad is that, one, it doesn't require someone to estimate diameter, which is a significant improvement. Yes, it does rely on a well-tested hail pad where you've sensed the impact depth into the foam, so a consistent standard is necessary, but it also gives you some idea of the distribution, and there are relationships you can use to extrapolate more information about hail size distribution. They're incomplete, but they certainly give you a more consistent way of measuring compared to, say, someone taking a bad measurement, right? A good measurement, one that's done properly, I think it's that's a different story, but they're kind of the easiest way to get there without having to spend $50,000 or even more, or a lot of keel's time at least. So, they are a useful way to get at that problem. My comment was going to be regarding the idea of global panel data sets. I've played a lot around with all the different data sets that are available out there globally. And the greatest problem that we face with our data sets is that they are all designed for different purposes. And while it is a noble goal to unify the approach we take to collect global data, you're going to have to get buy-in somehow. And as Henry will tell you, no matter what you do in creating a program like that, it is hard to get buy-in. The reason the storm data is as big as it is that we have collected it for warning verification. And yes, the public can be motivated, as the Swiss example shows, right? They have it, I think it's something like 80% of their population use an app to report hail, or are capable of using an app to report hail. And so they get thousands of reports on any individual event. Maybe that's a good way to start thinking about it. But we have to get everybody using the same platform. So, and that's hard even within a country's sphere. So I think it would be good if we were more consistent about the information we collected between different locations. But there's a lot of work that needs to be done on the ground.
No, those are good points, John. It's a problem. Public outreach is really difficult. And to this day, I'm still struggling to convince people to not hold hail in their hands and take a picture, right? We've gotten to the point now where we think of using machine learning or something to try and get a workaround, just to at least get some, even the error bars might be quite big, but at least we can get some quantified information. I'll get to you in 1 second. You talked about an app. That's a great idea. If that's something we're considering in the Northern Hail Project, people are remarkably keen to help out if they can. There doesn't even have to be much in it for them, except for you to say thank you to them, or to DM them, or something like that. In countries like, I'm from South Africa originally, where the infrastructure might not be the best in terms of radars, nearly everybody has a cell phone. Even places like the Congo, I imagine a lot of those small villages, if you go into Google Earth and you look at, there's a lot of schools and little towns in that area where we're seeing those, I don't know if they're spurious, but persistent signals that there's hail. If you get folks there to report on an app or something, because most of them will have a cell phone, I think we could leverage a lot of data that way. It's going to take somebody to organize it, and that's when we need some leadership and some, like John was saying, some standards. Go ahead.
John Hubbard here. I work here at NCAR. Probably the best way to get more information from a radar, looking at these convective storm cells and hail phenomena, is to look at it with multi-frequency observations. which is nothing new. People have done that in OU and NSSL back probably close to 10 years ago. They had an OU prime, a C-band radar, and the outside KOUN, an S-band radar, and they tried to match these two radar beams to look at a common volume. They had a series of papers that indeed show that you could get more information about the hail sizing and the particles and whatnot. But a fallback of that system was that you've got a radar here and a radar here, different distances to a common volume, and it's difficult to make precise comparisons. Well, what you can do to get over that problem is to have a radar that can both transmit S and C band at the same time. And then if they would have automatically co-located beams, and then you could not only look at, reflectivities and that type of thing, but you could take a look at propagation parameters. And in fact, we at NCAR have been pursuing this idea, and I have a poster. I'll give a shameless plug for my poster coming up. You have a lightning presentation, and we have gone ahead and spent $70,000 to have a CAD design and electromagnetic modeling of it, the scattering calculations to show that this whole thing will work. And so what we lack right now is the money to put that thing into effect. But C-band is dual frequency at C, and S-band is particularly nice, better than S and X-band, because C-band goes into this scattering regime and gets distinctly different from S-band. And you could get a lot more information about your clouds and your hail particles if you could have this dual frequency concept. This afternoon, I'll give a lightning presentation on it. Please come over and take a look at my poster, and I'd love to hear any input you folks may have about this dual frequency idea.
I'm sure Chandra has some ideas. And then we'll take some more from the virtual, Ian.
Chat can answer their own questions.
Oh.
It's actually wonderful discussion going on.
That's great. Well, I think we're...
You mentioned radar. Just quickly, we were down in Mexico City back in 2019. I met with the Weather Service there and the head of the Weather Service. And they recently had, I think it was last year, a big event in Mexico City of hail. They said they have 9 radars in all of Mexico and only 4 are operational. So we are really lucky in the U.S. and some of the European countries and others that we have all that available. There's a lot of places out there that they do get hail and stuff, but there's nothing. And so maybe expanding the radar in certain places could be very beneficial too.
Right.
That's where spaceborne radars are important. So in places that ground-based radars don't work, space can fill in.
Right. Yeah, go on, Sean.
So we've talked a lot about hail observations today, and Kyle and I have talked about the hail camera, obviously, which is surface-based. I believe you mentioned earlier that upper air observations in projects like Ice Chip would be really useful, but those are hard to get. I will throw out a plug that NSSL has a balloon-borne particle imager that's designed to look at microphysics observations inside clouds in a lot of places that even aircraft can't go. But those are mostly focused on, precipitating particles, not necessarily hail. So the question that I want to throw out there for everybody is, what kinds of hail observations at altitude do we need? Are we talking just sizing? Do we need velocity information? Like, what's the goal there? Because I think having answers to those questions, or at least a direction for those questions, will really drive a lot of development for, future observational tools that we might be working on.
Thanks, Sean. Yeah, that's a good point. So there's video sondes, and I don't think any of them are particularly designed just for hail. And it's difficult to get them into the right part of the cloud, but if you can get them up there, they could provide valuable data. So Dan, if you had a video sonde, what would you want it to be measuring for you?
I think I would actually want to defer to one of the modelers on that, and want to know what is most important for them to have the good measurement of.
Right. But if
anyone wants to come to a mic.
But if it could differentiate between, say, grapple versus higher density hail, that would probably help you, because a lot of scattering could be...
Yeah, I was going to say density is one of the most important things.
Yeah, for what we're looking at, our big issues come down to being able to distinguish between having a large concentration of small particles versus having some larger particles that we would really think of as significant hail. So simple size.
Okay. So there you go, Keel. Next project.
Yeah, we'll see.
System. I think we're out of time, Ian. So thank you very much for your interest. And yep, give them a hand, please.
Thank you.
Well, that was great, and something we've been talking about, kind of some back row conversation about next time we do this workshop, to have a panel where we focus on some of the needs of the different sectors that are actually sitting here, and we touched a little bit of that over the last really 30, 40 minutes there, so that was really good. So we return to our speaker program. Monica Feldman's up next in the virtual space, and will present some work on understanding a kind of a in-depth view of both hail and rainstorms across the Alpine region in severe convection. So I will turn it over to her on the virtual side.
Thank you very much. I just want to check, can you hear me all right?
We can.
Perfect. Thank you very much. Yeah, so I will be talking about hailstorms and rainstorms versus supercell thunderstorms, a comparison of severe thunderstorms in the Alpine region. This work is part of my PhD, that is a collaboration between EPFL in the French part of Switzerland and the Radar division of Meteo-Swiss in the Italian part of Switzerland. And I do this work together with Alessandro Hering, Marco Gabella, and Alexis Bern. First of all, I want to start with an example here. Here we see an example of June 21st, 2021, where there was a severe supercell in the northern part of Switzerland passing along the pre-Alpine ridge. And we can see in these different pictures that we are already covering the storm categories that I was mentioning in the title. So we have a supercell, and we can see it produced hail of significant size. And also had really intense precipitation cascades throughout its life cycle. We approached this whole project from the perspective of supercell thunderstorms, as there previously really was a research gap on supercell thunderstorms in Switzerland. We have very little previous research, and we basically began by establishing a mesocyclone detection algorithm for the Swiss radar network. Now, once you have the mesocyclone detection algorithm, the question is a bit, what do you do with this? How do the detected mesocyclones compare with storm types that have been researched previously? So this is how we decided to continue with radar-based classifications on rainstorms and hailstorms, so that we then can compare our detected supercells to these other categories. Yes, as I mentioned, I am using the Swiss operational radar network. Here we have a map on the right-hand side that shows the topography of Switzerland. And we also dissected the observational domain in different regions, ranging from the Po Valley in the south, which is in northern Italy, over the southern Prealps, where the radar division of Meteo-Swiss is located, the main Alps, the Alpine Ridge, the northern Prealps, then we have the Swiss Plateau, and in the northwest we have the Jura Mountains. We have 5 radars situated throughout Switzerland at altitudes ranging between roughly 1,000 and 3,000 meters, and the target is really to cover this complex topography of the Alpine area. The 5 radars have a synchronized volume scan and a range of up to 250 kilometers, with 20 elevations between slightly negative and 40 degrees. With this very large range at C-band radar, we have very low Nyquist velocities, as low as 8 meters per second, which posed really a challenge for the development of the mesocyclone detection algorithm. In addition, in this study, I also use radio sounding data that is from Milano and Payerne. So Milano is situated in the Po Valley, roughly here, and Payerne is in the Swiss Plateau around about here, so that we cover both the sounding from the southern side of the Alps and the northern side of the Alps. And these are performed twice per day. Another note on radar data quality. We derived a quality map of the radar observations that accounts for the spatial resolution, the number of available scans, numerical noise in the derivatives and the minimum and maximum altitude of measurements. This combined map you can see on the right-hand side here. We generally have quite high quality throughout the entire observational domain, as there is a lot of overlap in between the radars, though we do have some compromises in the inner Alpine area and also over the Jura due to beam blockage. It is to be noted, however, that dealing with severe thunderstorms, we are looking at phenomena that are at high altitude, so low-level beam blockage is much less of a problem here than for other phenomena such as quantitative precipitation estimation. And we also performed a narrowly stratified quality analysis where we only selected storms that were observed in a very narrow quality range and overall obtained the same results as when using our entire sample. So coming back to our radar-derived categories for thunderstorms, we came at this from the supercell point of view. So first of all, we have a mesocyclone detection algorithm that utilizes the Doppler data from the radars. We also have a general thunderstorm tracking algorithm for the ordinary classified thunderstorms, which is called thunderstorm radar tracking, or short TRT. Then the rainstorm and severe rainstorm categories are thunderstorms that exceed a 30 or 50 millimeter accumulation threshold. These are also the thresholds used for thunderstorm warnings in terms of flash flooding, et cetera, in the operational chain. And then we have the hailstorm and severe hailstorm criteria that are derived from probability of hail and maximum expected severe hail size at 2 and 4 centimeters respectively. And then, yes, finally, the supercells with the mesocyclone detection algorithm. I processed 6 years of data with this from the latest radar generation. And on the top right, we can see the number of storms that were detected in each category. It is a log scale, so we really go down the order of magnitudes, coming from ordinary thunderstorms over the less severe rain and hailstorms to the more severe rain and hailstorms, and then finally the supercells, where we roughly had 500 storms within the 6 years of observations. Then we also have significant overlap in between these categories, which we can see in the Venn diagram on the bottom right, where we can see that particularly the supercells generally co-occur with another hazard. So basically all supercells are either also a hailstorm or a rainstorm with the accumulation threshold, or both, and rarely present without another radar identified hazard category. So here we have a spatial comparison between all of these storm types. This is now presented as an annual average number, so it is divided by the 6 years. On the right-hand side, we have the quality map just as a context for what we are working with in terms of observational data. And then we can see in the different storm categories that there is a distinct pattern for convection in the Alpine region. We have a clear hotspot in the southern prealps throughout all storm categories in this polygon here. And then we generally have a secondary hotspot of activity in the northern prealps as well, and we can see a clear minimum in the main Alpine ridge. In the ordinary thunderstorms, we can see a little bit the quality artifacts from the radar network. This is largely because ordinary thunderstorms that just come from the general thunderstorm tracking of Meteoswiss can be very small and also short-lived, so they are more affected by the beam blockage of the radar system, because a very large, very severe thunderstorm will generally still be visible from another radar if one is shielded. But if you have a rather weak and small thunderstorm, this can then indeed be missed. So first of all, I established a life cycle comparison of different intensity variables for all of these different thunderstorm categories. For this, we needed to center the life cycle of each thunderstorm around a certain time of interest. For ordinary thunderstorms, this T0 is the time of maximum intensity. For the rainstorms and severe rainstorms, this is when they first cross their accumulation thresholds, respectively. For the hailstorms and severe hailstorms, this is when their first hail detection of the relevant size was first made. So for the hailstorm, the first mesh exceeding 2 centimeters, and for the severe hail exceeding 4 centimeters. For the supercells, this is the time of first detected rotation. And we can see that the definition does impact how the life cycle presents. So for example, the rainstorm and severe rainstorm categories tend to peak before T0, as this is an accumulation threshold. So the main part of the thunderstorm event is taking place in the time before the threshold is met. Then for the supercells, we can see that we have a very prolonged peak after the first detection of rotation. So the storm is still intensifying when we detect the rotation, and then remains intense for a very long amount of time afterwards. For the hailstorms, we can also see a very pronounced peak, though this is rather really at the time of hail detection. And it tends to be shorter than for the supercell thunderstorms. So for the hailstorms, we rather see a short, pronounced peak right around the time of hail detection. Then, as we are at the hail workshop, I wanted to take a closer look at hail. In supercells, we see that rotation usually precedes the initiation of hail. We also found this interesting to see that this relationship still holds true in this region of very complex orography. And then also, if hail is already present, it tends to intensify subsequently with the onset of rotation. As we could see in the Venn diagram, however, we have a large section of hailstorms that do not present with rotation. And here we made use of the sounding data to investigate why this might be the case. And in the bottom right plot, we can see 3 categories of storms with the respective deep shear from 0 to 6 kilometers in the atmosphere. We have severe hailstorms that can also present with rotation. Then we have the supercells. And then we have an additional category of severe hailstorms that do not present with rotation. And we can see that the deep shear on days where we have severe hail but no rotation detected is distinctly lower than on days when we have supercells. I would also like to add to this that CAPE remains similar for all 3 scenarios, so we still have sufficient energy in the atmosphere to build up a severe thunderstorm. Then we also took a look at regional intensity differences. So here we have 4 intensity variables for the thunderstorms in the different regions that are denoted in the map on the right-hand side. And first of all, we can see this clear intensity difference that particularly the supercell thunderstorms are really on the most severe end of the spectrum. As the mesocyclone detection algorithm is purely velocity derived and does not have any other intensity threshold, this is also a nice confirmation that we are detecting the right category of storms with this algorithm. So we can see that generally the severe rain and severe hailstorms are more severe than their respective weaker counterparts. And then we have the supercells that really present the peak of the spectrum. In addition, we can see in these severe storm categories that especially the upper percentiles of the variable distribution show a dependency on the different regions. We can see that the maximum possible intensity for these thunderstorm types is somewhat limited the more complex the orography is. This really mainly affects the upper percentiles, as, for example, a weaker supercell can and does occur in any part of the domain. However, a very severe supercell that presents with large hail is really much more likely in the flatter parts, such as the Po Valley or the Swiss Plateau. So then we also took apart some more variables from the radio soundings. Here we can also see a bit better the differences between the southern side of the Alps and the northern side of the Alps. For example, Cape tends to be quite a bit larger on the southern side of the Alps, where we have more Mediterranean influence. Precipitable water also tends to be higher. And then another interesting thing that we found was in Switzerland, we have an almost equal split of right and left mover supercell thunderstorms. And this is due to the fact that basically all of the shear present in the atmosphere is unidirectional speed shear. There is almost no component of directional shear. With this, I come to my conclusions. First of all, we wanted to identify here that supercell thunderstorms do occur regularly in the Swiss Prealps. This was also surprising to many forecasters at Meteo-Swiss, as this was previously underestimated. With a systematic detection over 6 years, we were able to characterize the situation a bit better. And then in comparison with the severe rain and hailstorms, we can really see that these storms do present the most severe and long-lived fraction of storms. Then also with a surprisingly high number of severe hailstorms without rotation, we see that they occur in lower shear environments with still equally high values of CAPE. And then finally, in the regional decomposition, we can see the influence of terrain complexity on the overall intensity of these thunderstorms. With this, I am at the end of my presentation, and I am happy to take any questions. Thank you very much.
All right, questions for Monica? I see Henry back there first. We got time for one or two.
Yeah, two quick questions. Could you tell us is there a month that we see more of the severe thunderstorms or the supercells, and also what time of day? So do you see these like around the 4 o'clock, the 7, is it late evening? So those two questions.
So for the first question, we look at an extended convective season here, which goes from April to November. And with a 6-year data set, we really run into sampling issues when slicing this up by month. So depending on how many years were in the data set, there was somewhat of a bimodal distribution for the early and late parts of the summer, or it kind of smoothed out with more years of data to just have a peak in the middle of summer. So I would say there were not quite in the range yet that we can make a robust statement on a monthly distribution. Then the other question with the time of day, there we saw an overall peak in the late afternoon / early evening. However, it is to be noted that in the south of the domain, to the south of the Alps, there is less of a dependency on the time of day, and there is a higher probability to have severe convection at any time of day.
All right, Matt, one more question.
Hey, Monica, really interesting work as Matt comes in here.
Thank you.
The bullet point number 4 there, severe hailstorms without rotation, was that in the absence of any azimuthal shear in the velocities, or just did not trigger the mesocyclone detection algorithm? And if the latter, what's the lower bound on that for triggering? Thank you.
So this is rather, it did not trigger the mesocyclone detection algorithm, which has a number of thresholds, all of which are range dependent. So it is mainly oriented on the common thresholds of having 10 to the -2 in the vorticity field that is radar-derived. But then I also relax this threshold the further we get away from the radar. Additionally, I have a threshold on rotational velocity, object depth, and then also time continuity. So if any of these are not met, then it would not have been classified as a supercell thunderstorm.
All right, thank you. Thank you, Monica.
Thank you.
Our next speaker will stay in the virtual space, Matthias Gergely. Matthias is going to talk to us about C-band radar observations from a supercell in Germany.
Okay, hi everyone. I hope you can see my slides and hear me okay. I'll just get started. So I want to talk about a new observational method that is not really new in itself, but the application to analyze the precipitation processes of a hailstorm is probably rather new. And in this presentation, I will show our first results for a case study of a supercell, which you can see in the image on the left. Basically, the image shows the supercell 5 to 10 minutes before it moves over our meteorological observatory and the radar tower. Two of the structures that you can see in the center right of the image. And in this talk, we'll kind of work our way through to the interpretation of profiles of Doppler spectra that were recorded with this vertically pointed C-band weather radar while the supercell moved over the radar. So this talk should kind of tie nicely with part of the discussion of the panel just a few minutes ago. So, but first we look at some basic background information. So, in spring 2021, the German Meteorological Service introduced a new vertically pointing birdbath scan into the operational radar scan strategy at all of our 17 operational radars. And the locations are kind of indicated on the map on the right. So the new birdbath scan was introduced to also record Doppler spectra instead of only the integrated moments. And so far, the new radar scan, or the new birdbath scan specifically, just as the old scan, is only used for monitoring the calibration and quality of polarimetric variables. But we've started to look at whether we cannot use this information also for meteorological applications to complement our polarimetric observations. And the red dot on the map on the right, just north of the Alps, indicates the location of our meteorological observatory and research radar of the German Weather Service, where our case study takes place. So on the left, we'll see a little webcam video looking from the east towards the west as the supercell forms and moves across our observatory and radar tower. And that should happen any time now. And on the right, we see the aftermath of this supercell storm with hails of diameters of up to about 2.5 centimeters. At least that's what I measured by hand afterwards. Before we get to the Doppler spectra, we'll first take a look at the time height plot of the radar reflectivity that was recorded in a sequence of those radar birdbath scans as the hail cell moved over the radar. So essentially, what we're seeing here is a cross-section of the supercell at a temporal resolution of about 5 minutes. And the hail cell in this image moves from right to the left. And the maximum recorded reflectivity is around 60 dBz. And already in this image, we can see some of the typical features of a supercell. For example, the front anvil cloud at high altitudes. Then we get to the core region of the storm, which is marked by the dashed light blue rectangle, where we could see some strong convective precipitation at the ground, and where we would expect strong updraft to be present. And behind the core, you can see that the radar image and the precipitation also calmed down quite a bit and moved more towards a stratiform rain. Although in this case, we don't really see a very pronounced bright band yet, which would indicate a clear melting layer. So we'll take a closer look at 3 birdbath scans in particular at 3 different points in time within the core of the storm. The first one will be at a time where we have observed no precipitation at the ground yet. The second one will be while we have observed only rain at the ground, and the third point in time and the third Doppler spectra we will look at will be when we finally get our hail shower and simultaneous rain. And we hope that we can kind of explain the hail and rain processes a little bit in more detail. As you can already see that there's quite a lot going on just by looking at the reflectivity data that you can see here. So let's start at the point in time when we have no precipitation at the ground yet. So essentially what we see on the right is a profile of Doppler spectra from one of the polarization channels recorded by the C-band radar while it is looking upwards vertically. At each height, we can see one Doppler spectrum. And each Doppler spectrum essentially decomposes the single value of radar reflectivity into a wide spectrum of radar echoes, which are specified by their respective Doppler velocity bin in the x-axis. And the Doppler velocity specifies the relative movement of the precipitation to the radar. So essentially the particle fall velocity plus the vertical air movement. And what we can see is essentially two regions of strong radar echoes, which I've labeled A and B, which are two different precipitation regions. Looking ahead a little bit, the region that I labeled as A will result only in rain at the ground, and the region that I labeled as B will then be our hail shower, which lasted only about 5 minutes. What we can also see is at positive Doppler velocities, which indicate movement upwards, in contrast to negative Doppler velocities, which indicate falling precipitation downwards towards the ground. So we can see also a significant radar echo region at positive Doppler velocities, indicating that there's a strong updraft present, like the precipitation particles there move upwards with a velocity of up to 10 meters per second. Now, what is also striking is that this uplifting area pretty much extends from the top of region A to the right side of region B. So we could speculate that this is actually where the hail growth takes place, which we obviously cannot really be sure about because we're only looking at a small atmospheric column and not looking at the entire 3D structure of the storm. But conceptually, the idea would make sense to have precipitation particles moving upwards, hail growing until no more hail growth occurs, and hail particles fall down in region B and with much higher fall velocities. So one interesting feature, or what has also been talked about in the panel discussion, is that Doppler spectra can actually separate individual precipitation particle populations at the same height if they occur simultaneously, based on their different fall velocities, which is seen here in the region between about 4 and 7 kilometers, where we see both rising precipitation undergoing hail growth and fast falling hail particles. So this is the data from the birdbath scan that we recorded 5 minutes later. And here we can see that only region A has reached the ground, and our in situ sensors have shown that this precipitation is only rain, or seems to be only rain and no hail yet. And what is also interesting here is that we cannot see this connection between region A and region B anymore within the positive Doppler velocities, so that there is no more hail growth occurring, would be at least be our interpretation. And finally, another 5 minutes later, the profile of Doppler spectra that we see shows intense hail and rain precipitating simultaneously. And we can nicely see close to the ground the separation of hail and rain based on their different fall velocities, with rain occurring probably around 10 meters per second fall velocity and hail between 15 and 20 meters per second. Another interesting feature here is that little dark red line, almost horizontal, that seems to connect the hail mode to the rain mode, which we would interpret as melting and shedding of rain close to the 0 degrees Celsius temperature within this hailstorm. And again, here we don't really see any more strong updraft or hail growth or region where hail growth would be possible. And that kind of fits our in situ observations, which showed that the hail died down really rapidly after this this birdbath scan was taken. So just to give a very high-level summary of the hail and rain process based on the data that we collected, particularly the Doppler spectra that we can interpret. We see two distinct trajectories for our precipitation inside the core of this supercell that both originate somewhat in the same region of the storm. The first trajectory simply takes the precipitation down towards the ground and ends up as hail, as rain only, no hail. And then we see a second trajectory, which is first characterized by uplifting precipitation particles, or uplifting of precipitation particles, which then rapidly fall towards the ground and which are essentially our hail shower that we observe at the ground. So, well, what are our next steps with this analysis? Well, we obviously want to do a more quantitative analysis than just this qualitative phenomenological interpretation that we have presented here. For that, we will probably look at processing algorithms to separate simultaneously occurring precipitation modes at the same height and then estimate the reflectivity of each mode individually. Taken to the extreme and given the different radar echoes in each Doppler velocity bin, we should be able to retrieve some kind of estimate for a hail size distribution, as long as we can assume a reasonable relationship between fall velocity and hailstone diameter, and as long as we have some kind of adequate scattering calculations available, which I've seen that a lot of you, or some of you at least, have already done some excellent work on. And again, would still like to get a much more complete picture of all of this storm that we investigate and other storms that we might encounter in the future, and combine this analysis of this, let's say, new observational method for hail with more well-known or more classic observations. One way to go is obviously to look at our operational polarimetric radars that are located around 50 to 100 kilometers away from our observatory. Another way would be to kind of look at the thermodynamics that we can derive from our operational weather forecasting model. But this will still be a little bit in the future. Yeah, and with this photo of our observatory and radar tower in slightly more pleasant weather, I would like to thank you for your time and also acknowledge the contributions of my colleagues here, Maximilian Schaper, Friedrich Seeger, and Michael Frech, all at the German Meteorological Service. And I'm happy to take any questions or hear any comments that you might have, either now or you can also contact me by email anytime if you want to. Thank you very much.
We do have some time for some questions. All right.
Yes, I do.
Oh, this is Ivan Arias from the audience. So does dual polarimetric would make sense for this Verbots scan? Will provide any information?
Sorry, can you repeat the question? I couldn't quite hear the question.
Oh, like, does dual polarimetric spectral would provide like any information, like would make sense for this Verbots, or it really doesn't make?
No, it would make a lot of sense. Obviously, we would like to have not only the Doppler, the autocorrelation spectrum, the power spectra, basically, but also the cross spectra, essentially, which provide the polarimetric variables, the spectral resolution. Unfortunately, so far we haven't been able to get any reasonable information from our cross spectra that we have measured, what we interpret as our cross spectra. But if we were able to do that, I think that would still provide quite a bit more information, which is actually what I'm interested in one of the following talks. It might actually be the next talk, I think, where somebody might present spectral polarimetric analysis of hailstorms. So I don't know if you are the one presenting that talk, or if not, then this might be an interesting talk to look at to see what additional information you could glean from spectral polarimetry.
A question, Andy, up front.
Things, very nice talk. First, I think you probably could get some information on the particle size distributions from the Doppler spectra. And second thing, though, is you're only looking at 2D, whereas particles can go in and out. And so the interpretation of the motion of the particles is not clear from the imagery that you showed.
It's true, it's not unique. Just as the hail size retrieval would not be unique, exactly, right? So, but that's all the data we have, and we have to do the best that we can with that, and yeah. But we'll definitely keep at it, and the one way where we hope that we can resolve some of these non-unique effects that might show up is by looking at the storm from with multiple different data sets, right? So what I presented here is only let's say one dimension, right? Where we focus on the fall velocity and the differences in fall velocity and the effect on the precipitation particles. And here we only have the data from this very small atmospheric column right above the radar. And then we will complement this with polarimetric measurements from our scanning radars and hope to see or resolve some of those non-uniquenesses that you rightly talked about.
Okay, all right. I hope everyone got what a great kind of global feel we had throughout this morning session. We'll go ahead and move on, and our final speaker of our morning half of the program, Howie Bluestein, is going to talk about using RaxPol mobile radar measurements to understand hail processes. So Howie, all yours.
Well, good morning, good afternoon, good evening, depending upon where you are. I'm going to talk a little bit about RaxPol. This is a radar, rapid scan, expand polarimetric radar that we've been using for over 10 years. And we've been using it mainly to look at tornadoes. And most of the tornadic supercells that we scan also have large hail. So I'm going to talk a little bit about that. And talk a little bit about some new applications that we have been pursuing. And let's see, can I control this myself? No, okay. So the question is, are rapid scan radars needed to study hail processes in convective storms? Why do we need a rapid scan radar? If the update time of the radar, the volumetric update time is 2 to 4 minutes, as it is with WSR 88D, and a hailstone falling at 35 meters per second will drop 4 to 8 kilometers, more than half the depth of the deepest convective storms. If the update time is 20 seconds or so, then a hailstone falling at 35 meters per second will go about 700 meters, which is within a distance between scans if the vertical resolution is around 1 kilometer. If we have an update time of just 5 seconds, then a hailstone falling at 35 meters per second will go only 175 meters, which is not very much different from the radar spatial resolution. So I think we can conclude that rapid scan mode is needed to compute hail trajectories with the best accuracy and the best portrayal of the evolution of the hail within the storm. Next slide, please. And if you could, it should animate, it did yesterday. Just want to show you the antenna spinning around once every 2 seconds. Okay, it's going so fast you can't even see it spinning right now. Okay. It mechanically can scan as rapidly as 180 degrees per second, and radar is scanning around at that rapid of a rate. You can't collect enough data to get a good signal. So what we do is we frequency hop about 11 times. So it's like having 11 radars at once. And so we're thus able to, even with mechanical scanning, get good enough data. Usually the volume scans up to about 20 degrees, and elevation angle will take about 20 seconds or so, assuming we scan every 2 degrees. And you can look at Andy Pasmani et al. In 2013 JTAC to see more of a technical description of the radar. Next slide, please. Just want to show you the capabilities of this radar. This is a tornado. In the upper left, you see the tornado spinning around the reflectivity. In the upper right, you have ZDR. In the lower left, you have Doppler velocity. In the lower right, you see rho HV. And each scan here is every 2 seconds. So you're looking at a scan every 2 seconds of the evolution of this tornado. And you can see that at this elevation angle, we're so low that you don't see a weak echo hole, that you're actually seeing the effects of the radial inflow into the tornado. You can see the low ZDR and low rho HV, the spiral bands, which are associated with the debris. So we mainly have been using RaxPol to look at the debris in storms. We haven't really focused on hail. So if you can go on to the next slide, please. Now, what we're going to look at is some spectral analysis of the polarimetric variables in hailstorms. And this was suggested to me by my co-conspirator, David Schwarzman, who's at OU, a new faculty member. The polarimetric spectral densities show the polarimetric variables as a function of Doppler velocity within the radar volume. So we're looking not only at the spectrum of Doppler velocities, but we're looking at the spectrum of Z and ZDR and rho HV. For high elevation angles, the spectra can link dynamics and microphysics via particle size sorting, since the Doppler measures a higher component of the particle terminal velocity. We'll look at that in just a second. The hailstones generally have higher fall speeds than raindrops owing to their size and weight. And identifying hail signatures in the spectral domain could be a way to separate hail from rain and use the hail-only spectra to improve hail size estimation. So you can take your spectrum, filter it, and get a better look at the hail. Next slide, please. Okay, there's the radar. You can click again, please. And click again, and click again, click again. Click one more time. Okay, now here you can see a graphic representation of how the terminal fall velocity can project onto the Doppler velocity seen by a beam at some relatively high elevation angle. On the far right, do I have the ability to point over here? I guess is there a cursor? Can I use the trackpad? I can use the trackpad, except that this is not being cooperative. All right, on the right-hand portion, you can see on the upper right, you can see spectra of the Doppler velocity. Underneath that, you can see spectra of ZDR. Underneath that, you can see spectra of rho HV. And under that, you can see spectra of VDP. So this is just a sample. Next slide, please. Okay, there you see the rain portion of the spectrum. One more time, and you can see the hail portion of the spectra. So on the right-hand side, where you see the rain, there are positive Doppler velocities, and for that, you can see that rho HV is relatively high. ZDR has a little peak at that point called B. And if we look at the hail, you can see that rho HV is relatively small. And we go up to ZDR, and ZDR is also relatively small. And you can see how that varies among the different Doppler velocities. Next slide, please. I'll go through this very, very quickly. Just focus your attention on the lower portion from Morgan Schneider's thesis. These are from highly idealized numerical simulations, but we originally using the spectra to differentiate between debris and hail. Between debris and raindrops. So the reason why we do this is when you look at a tornado right near the ground in the boundary layer, you get a lot of frictional inflow, which is what you would expect. But when you look at the Doppler radar data, you often see divergence. And what you're looking at is the effect of the centrifuging of the very heavy particles, heavy raindrops, at least compared to air moving radially outward, okay? And you'd like to remove that. So you can see in the lower left, you have the spectrum of Doppler velocity. If you can separate the debris from the raindrops. In the middle, you see the ZDR. You see the part of the spectrum that has relatively low ZDR. In fact, it's negative over here, and that would be the debris. And then the high ZDR part of the spectrum would represent the rain. And you look over to the right, we have the same thing for rho HV. You can see the low rho HV part of the spectrum represents the debris, and the higher rho HV part of the spectrum represents the raindrops. Next slide, please. Okay, so here are some vertical cross sections. We're going to look at some hail signatures, and we just started to do this. This is from last October, October a year ago. And this is a vertical cross section through a supercell, which produced a tornado west of Oklahoma City. In the upper left-hand portion, you can see some echo overhang and some relatively high Z values, about 57 dBc. Go down to the lower left, you can see region of relatively low ZDR, right around a half to 1 dB. And then over in the lower right, you see a region of relatively low rho HV. So we think that that represents hail. Next slide. Okay, now we're going to look at that again, but we're going to look at that also looking at some spectral plots. Next slide. There we go. Okay, you can see slice 1 goes through the lower part of the storm, and in the left hand, let's just look at the right-hand part of that thing labeled 1 at ZH, and you can see that ZH that spectrum is relatively narrow. It's negative for Doppler velocity, and we have mostly relatively high values of ZH. Okay, next. Number 2 looks higher up through the hail signature, and you will notice that in the lower right-hand portion, we see that the spectrum of Z is a lot broader where the hail is. In fact, you can see it goes from slightly positive Doppler velocities all the way down to -20, and believe that that represents a lot of the fall velocity of the hail. Next slide. Okay, now let's look at the spectral densities of the polarimetric variables as a function of range. And we have 2 of them. Look in the upper left, one at 25-degree elevation angle and one at 28-degree elevation angle. Both are going through pretty much similar parts of the echo overhang at the top. And if you look at Z, you can see that there is one area which has around 13.5 kilometers in range, where we have a lot of reds, a lot of very high reflectivities. But there's also a region with 0 Doppler velocity, or where Z is a lot weaker. Look at ZDR, which is the next column over, and there you see some high values, some red at around 13.5, and then at 0 you see very, very low values of ZDR. So we think that may represent a separation between the hail and the rain. And then you look at rho HV, we can see something similar. We have some relatively high values of rho HV, some reds next to some yellows, which are a lot higher values of rho HV. You look at 28-degree elevation angle down below, we see that there's a region of strong ZH around 13.5 kilometers, very low values of ZDR, and very low values of rho HV. So that's probably not a mixture. That's probably all hail. Okay, next slide, please. We also did some hydrometeor classification, and we used the functions that Jeff Snyder, my former student, has worked with. And we used those, but we used, instead of looking at the moment data, we looked at the spectral data. And over here, let's see, the second from the left, we have ZH, and that we have a region of very high Z, and then we have the region to the next panel to the right, is relatively low ZDR. The next panel to the right is relatively low rho HV. And the hydrometeor classification, it gets purple and brown, which is in the heavy rain and rain hail mix, which I think is supported by our bimodal spectrum. These are very, very preliminary results, like a week old. So we'll be doing a lot more work with this in the future. Next slide. Next, here we go. Now we're just going to look at a PPI through the supercell. This was after it produced a tornado. The long story is we collected a lot of data, and then you get up and move to the next location and storm tornadoes while you're moving, and then you have to take what you get. But in the upper right-hand portion, you see this region of relatively low ZDR, and then a relatively low region of rho HV. And I think that's pretty unambiguously hail. You can see the values of ZDR and rho HV listed up there. Next slide, please. Okay, and this is a no hail versus hail look. We have slice number 1, slice number 2. In slice number 1, we just see a very, very relatively narrow spectrum of ZH. When we look at ZDR and rho HV, they're kind of noisy, but the rho HVs are relatively high and out at about 7 or 8 kilometers. About 7 or 8 kilometers in range. And the ZDRs are relatively low, but also noisy. But look through slice number 2. Slice number 2 is different. We still get a relatively narrow ZH spectrum. It's a little bit broader than in 1. But if you look at ZDR and rho HV at about 8 kilometers or so, you can see that we have a region of relatively low ZDR, but more notably, a region of relatively low rho HV in there. And at farther ranges and at closer ranges, we have higher values. Next. Next, please. Okay, I think I'm going to skip this. This is some other data. They're a little bit noisy. In the interest of time, let's move on to the next. Okay, so here is some summary of some of our preliminary results. We've successfully collected raw IQ data in supercell hailstorms and calculated the dual polarization spectra that seem to make qualitative sense. We've implemented a spectral classification algorithm to support our analysis in identifying spectral hail signatures. And I just want to note that although these are preliminary results using existing HCA algorithm as it is, they are promising and show, I think, potential for supporting identification of hail in the spectral domain. I don't know if anyone has done this before in the spectral domain. So this is a new frontier. Next slide. Future work. How can RaxPol be used to compute rapid scan polarimetric Doppler spectra? Now, what I showed you were not rapid scanned. And it turns out that with this radar, to get rapid scanning, you need to frequency hop. To actually get enough samples to compute a good spectrum, you have to turn off the frequency hopping and do relatively slow scanning. Well, okay, we've done that. Been there, done that. Now, how fast can we scan without frequency hopping and still compute polarimetric Doppler spectra without excessive noise? We're sure we can scan more rapidly than we did. Number 3, can we compute rapid scan polarimetric spectra with frequency hopping by averaging individual noisy spectra from each frequency? David Schwartzman has ideas on how we can do this, and we're going to be trying that out very, very soon. And I must add that we have collected raw IQ data in 2 tornadic supercells, but the radar operator, 2 different radar operators whose names I won't give you, I think they were given the wrong instructions, really, forgot to turn on the frequency hopping. So we have a lot of spectra, but they're very, very noisy individual ones. Next slide. Finally, radars have been designed and built at the ARC at OU, such as PAIR, which is the Polarimetric Atmospheric Imaging Radar. That's a C-band imaging radar that's hybrid electronically scanning and mechanically scanning, which will have a little bit less spatial resolution, but a lot better temporal resolution, and we'll also be able to get spectra in rapid scan mode. Also, there's HORUS, which is an S-band electronically scanning radar, polarimetric radar. Its spatial resolution is not really very great, but it's S-band. And so that's going to be out there. And there's a picture of the antenna being put on PAIR. Thank you.
Questions from Howie?
I'm having trouble hearing in this room because of the echo, so.
Okay, can you hear me there?
I can hear you.
Cool. Yeah, I have a question about the hydrometer classification with the spectral. So I guess my question is if you perform like attenuation correction to the
Yet done.
Okay. Okay.
I don't think David did that on this.
Please use the mic.
I don't think that David did that on this, did any attenuation correction. If David's listening right now, shout out whether you did do attenuation correction. I thought that we haven't done that yet.
Yeah, thanks.
Yes. But for X-band, that's very important.
More questions? Matt?
Great to see you doing hail, Howie, instead of tornadoes. There's lots to learn here. So this is absolutely fascinating. I love the fact that we're getting these spectra. I didn't see any of the propagation, so any spectral phi dp or separating spectral like backscatter differential phase, and even maybe looking at the spectral differential attenuation, for example. Have you looked into any of those kind of propagation spectral densities?
Yeah, that's a very interesting point. I haven't thought of that. Yeah. Yes.
All right. Any questions out in the virtual space? All right, let's thank our speakers again for a great first half of today. Couple of quick announcements. Let's see, since we are in a now post-frontal air mass outside, it's a little more chilly. There is extra dining room seating upstairs if anyone wanted to spread out more here at lunch. We will reconvene at 1:20. We actually had a talk with drawn from the workshop a couple of weeks ago, so it spread us out a little bit more in lunchtime. So 1:20, we will reconvene, and thanks for a wonderful morning, and let's go have another nice lunch. Thank you. So to start us off this afternoon, Tabea Wilke from the German Meteorological Service. Come on, Ian, read your own typing. We'll talk a little bit about insights into hail distribution over Germany. She's on the virtual side, so we'll start there. Thank you.
Yes, thank you. Hi, everybody. I'm Tabea from German Meteorological Service. I'm currently working on climatologies on rain and hail, and because we are on the hail workshop, today I will present you my current results for the hail distribution over Germany. I will take you by the hand to show you which data I used and which methods I used to come to my results. And then what's my plan for the future, because it's not the end, I will show you today, and what you can take home from my presentation today. Then we are on the next slide, please. Thanks. First of all, I will present you which data I used, because there are more sources than one. First of all, there's the German so-called Warnwetter app. It's an application for mobile phone users where they can receive warnings for their specific region and also give reports about the weather. So for example, hail or rain or sunshine, cloudiness or the temperature. Then I use, for hail, it's relevant that they can only report sizes like smaller than 1 centimeter, 1 centimeter, 2 centimeters, 3 centimeters, 5 centimeters, and larger than 7 centimeters. So they are not free in their decision what to report. Then I will also use the European Severe Weather Database. There the reports start at 2 centimeters. And then it's free for the user to say how large the hail was. But the large positive thing from the ESWD is that it's more quality checked than our own Warn Weather app data. And last but not least, I have the radar data from the German radar coverage. Here you can see how it is. We have 17 C-band radars, and I will take all those data I received from that. Then the next slide, please. I will show you what I have done with the radar data. So we have the volume data. So we have a 3D data cube, and also the ERA5 reanalysis temperature data set, so that I can receive the severe hail index from that together, and from that the maximum expected size of hail in mesh. We have also more or less directly a mapping from the 3D data cube to the vertical integrated eyes, so the VII, and those both algorithms are more or less programmed by Markus Schulze, so big thanks to him. And we have large information for the mesh algorithm from Joshua Soderholm and Jordan Brook. So thanks for them. And yes, so I will, in my presentation, I will refer to mesh and VII, and also to the severe hail index. And the vertical integrated eyes and the mesh are both in millimeter or centimeters measured. So we come to the results on the next slide. Thanks. So here you can see results for 2021. So I said I'm at the beginning of my research. So I have started with the last year, and that's not much for climatology, I know, but I will present you the first results for that. On the left side, you see the results for the VII, the number of hail days last year. And on the right side, you can see the number of hail days for the mesh algorithm. Here, I must say that for the VII, we had the threshold for a hail day that there is in the pixel at least 0.75 centimeters measured by VII. And for the mesh, we took 1.5 centimeters. And here you can see, I hope you can see, I'm not sure if you can see it in present also, that they are more or less very the same. There are a bit differences in the north, but not that much. And you can also see that in the south, there are more hail days than in the north. And in total, the highest number of hail days in Germany was last year from the radar data, 9 days. Yes, then at the next slide, I will show you also the maximum of the hail size. On the left side, you can see it from the mesh, but it's more or less the same for VII. It's a bit higher for the VII, but in total, it looks more or less same. You can see that the highest number of pixels are green or blue. So as you can see on the right side, the distribution shows it's log distributed. So the largest numbers are very, very rare, and the smallest numbers are the highest occurrence. So you can see on the right side the maximum of 1 day for 1 pixel. So if there are different sizes of mesh for 1 pixel in 1 day, I took only the highest one. But you can see also that there are very high probabilities for also mesh sizes larger than 5 centimeters. So you can see there are more than 1,000 occurrences for that. Yes. Then, thanks. Another two examples. Here you can see the mesh and the crowdsourcing data. So from our Warnwetter app on the left for the 21st of June last year. You can see the orography from Germany and also the mesh data and the crowdsourcing data. So they have the same color bar. I hope you can see it, but it looks very good. The region and also the maximum of the hail size are very close together. But then there's the right side. It's the 5th of May. You can see only crowdsourcing data. And that has a reason, because our mesh didn't perform anything. And also the VII didn't perform anything. We had a look into that, and it seems like that there was a cold temperature processes on that day and in May typically. And that's the reason why I left the May completely out of my further results. So on the next slide, you can see only observations from June to September from last year. And on the x-axis, you see the severe hail index, and on the y-axis, the observation from the Warnwetter app. I took the maximum of the SHI from the pixel of the observation around 20 kilometers around the observation, and from the time step from the observation behind 1 hour. So I can be sure that the cell which produced hail is into my data point. And then you can see here in the plot also the fitted curves from Witt et al. And Murillo et al., the 75 percentile and the 95 percentile. And you can see the interquartile range from the Warnwetter app data and the median. And here you can see that the SHI for our data is much higher than for the Witt et al. Paper, but it increases similarly to that. Yes, and you can see probably that the 7 centimeters observations are a bit crowded. Well, that has a reason, because maybe people can't estimate very well how large the size is, but also maybe they are at the wrong position or something like that. But I think you know all the problems with crowdsourcing data, so I must not tell you what could be the problems for that. Yes, then at the next slide, please. I have also insurance data, so big thanks to the GDV. On the left side, you can see the number of hail days in sum from 2013 to 2020. Here you can see that more or less over all of Germany there are hail days. Only in the north there is a bit of more or less non-hail days, and in the north of Bavaria there's also an area with very small hail days. And in the south there is a large area where very many hail days. On the right side you can see the sum of damaged, so it's the euro which are damaged and which were insured, and the quotient between them. And there you can see the hail tracks for some events, like in the south you can see clear tracks of the hail events. Yes, next slide please. Then what's next? So my goal is hail distribution over Germany and climatologically basically. So I need to extend my recalculation. I hope to get easily back to 2013 But to get back further, it will be a bit problematic because of the volume data. Then I want to validate the crowdsourcing data with the lightning data. Then I hope it is much better quality checked. Also, I want to compare my results with the insurance data. So my first step was only to look at the insurance data, but I want to also check the size of hail and the loss and compare that. Then I want to look again into the MAIC from last year. So you have seen that there's nothing for mesh and VII, and there are the most number of crowdsourcing data, so 550 crowdsourcing data at this day. That hail wasn't that large, but there was much, so there must be something. And therefore we want also to try to try using other moments like CDR, ρHV, or something like that. Yes, then on the next slide, I hope you can see that it's a very tough problem to come from radar to the hail size, but you know, obviously. And you should have also seen that 2021 was a very hail rich year in Germany, so there were very much hail events. The south is more likely to be hit than the north, but it's not that clear if you can see on the insurance data. Then high SHI does not necessarily lead to large hail, because it's very large. SHI can also produce very small hail. Small hail is most likely in Germany, but significantly severe hail, so larger than 5 centimeters, are also reasonable. And the crowd data quality is sometimes doubtful for the very large hail sizes, but it's nevertheless good for comparisons. And I want to thank Katharina Langfeld for her help as my project leader. Thank you very much for your attention.
Sabia, thank you very much. Any questions out there? I have enough time for a couple of questions. Anyone in the virtual side? I do have one, and for someone who sort of works in the insurance space, how well did some of the insurance claims data actually line up with the radar-based assessments? I know you kind of had the side-by-side comparison, but if you did kind of a difference plot, did you feel the radar-based climatology was kind of overdoing relative to damage, or were you seeing more damage than you expected relative to the radar-based climatology?
I have only insurance data for up to 2020, and I started with the climatology in 2021, so I couldn't compare those yet. So that's my next step, to go back with the radar data to 2020 at least, so I can compare them better. So for now, I can't answer this question. I'm sorry.
Well, I will just say that it's very good that you have the ability to do that, because here in the United States, we don't often get that kind of information. So that is my one knock, and I felt I could throw that out there. So thank you. Oh, do you have a question back there? I think that's Amanda back there. Yep.
So on the same realm of the claims data, when I looked at that map side by side, did you ever try to overlay that to say where we predicted hail, there were claims 60% of the time, 75% of the time, to try to give an estimation of how often the hail actually translated to damage? Or would that
No, not yet, because our Warnwetter app started in 2020, so we haven't an overlap also for this.
Gotcha. Same thing. Thank you. Appreciate it.
Well, one, it's going to be great work, so we're looking forward to that comparison too. That'll be really interesting, and I'd love to be able to do the same thing here in the States to see how things look different, because so here tomorrow we have a different roof cover type that we like to use here in the US, so I would expect some differences. I saw Brian back there. We had a question from the virtual space.
Yes, it says, can you please elaborate on how you computed your severe hail index?
Normally, like in the paper, I would say, from Ritt et al. So I have done, or more or less Marcus had done, the 3D data cube. And then we took the temperature limits and integrated over them.
All right, any more questions?
Yeah.
All right, thank you, Tabia.
I think there is one more question, I'm sorry.
All right, our next speaker will be Jordan Bell talking about creating a Hail Swath event database and its applications.
All right, good afternoon, everybody. A couple quick things before I get started. I know a couple of you saw a talk similar to this at the previous AMS. This builds on that talk and it's got some new cool stuff to show. Also, like Dr. Giacini's talk yesterday, all the figures in here have not been peer reviewed yet. We are finishing up a manuscript on that, so I just wanted to caveat that. Still going to show you some pretty cool stuff. Oh, cool. All right, so what is some of the motivation behind this building an events database? One thing that I did, and I noticed for my master's thesis working at Marshall Space Flight Center, or working with Marshall Space Flight Center at the time, was that each warm season you have like this great big green, luscious vegetation in the agricultural Midwest, Great Plains. And then you get like this giant hail streak, hail damage swath through it. So I wanted to study those more. Problem is there is no record or database of them. We don't keep track of them. We see them in satellite imagery, but we don't have like a tornado database of them. So why not? Also, how often are they occurring? What's the spatial extent of them? Again, we don't have a way, we see them. There's peer-reviewed publications on individual swaths, but we don't have a database to know about the temporal frequency or the spatial extent. And then we want, that's part of the motivation, but also what are the annual impacts from these hail damage swaths, these large damage swaths to the agricultural areas over the agricultural Midwest and United States each year. So we created a hail damage event swath database using open source data. Let's see here. There we go. So I just wanted to provide some quick background on what was in the literature. That's one of the first things we did was how far back were these denoted? The earliest paper that I could find on these was in documentation from E.M. Frisbee over 10 years in the late 50s, early 60s in South Dakota. Like I said, he noted about 10 years worth of these hail damage swaths in different regimes that occurred. So that was really cool to see. He was starting to put like the orientation of the swath with the type of synoptic pattern. And then in the 1960s and 1970s, Chagnon from the University of Illinois did extensive amounts of work on hail and hail damage to agricultural regions in Illinois, Midwest, et cetera. And then there was more recently bringing it forward in the late 1990s and through the 2000s. So there's been a lot of papers that have been published on individual hail swaths using satellite remote sensing because you can see these from outer space. We've got papers using GOES, MODIS, NDVI, and most recently I've started using synthetic aperture radar, which allows us to see the swath at night and during cloud cover where optical is limited to denote and map some of these damages. There we go. All right, so how did we build the database? I'll acknowledge my co-authors at the end, but how we started is we started going through daily SPC storm report maps and using MODIS imagery. MODIS goes all the way back to 2020, or not 2020, sorry, 2000. That's when Terra came on board. Aqua came on board in 2002. So we got 2 views over the agricultural Midwest and Great Plains twice a day. So what we do is we'd go through the SPC storm reports. If we noticed a cluster of storms, we would denote it. We'd go to the satellite imagery. We would use the NASA WorldView online data portal, which allows you to see and compare before and after imagery. And if we noted any of that imagery or noted a spot which we might be a hail damage swath or an area of interest, we would go ahead and catalog it. And we cataloged it in using Google Sheets so we could all work. And did it not go? There we go. This may go one more time. Yep. Sorry about that. It's lagging. Anyway, so we cataloged all these hail damage potential, I call them potential hail damage swaths, in a Google Sheet. Oh man, that is not cooperating. Can we back up one, please? I'll just start calling them out. Anyway, so in addition to denoting where they were, we copied the NASA WorldView link that showed us an image of it, but we also collected some additional metadata. the swath date or the estimated swath date matching the SPC storm reports, when it first appeared in MODIS, and then the best date that that swath or that potential hail damage swath appeared within 15 days of the actual event occurring. Generally, we went with 2 weeks because some previous work we had done, we had denoted 2 weeks is about what a farmer or agricultural company will give it before they see how much of it rebounds before the farmer has to make a decision whether to, just knock it all down or completely take their losses. So in addition to denoting all that in metadata, we also provided confidence intervals from the analysts that went ahead and found it. Generally, some of these were very easy to say, hey, yeah, that's a 9 or a 10. We have great confidence that's a hail damage swath. There were others that were more in the like 3 to 6 range. Yeah, this could be 1, but I want a second set of eyes. And so for all those ones that were more in the moderate range, we had an additional set or 2 pairs of eyes to provide their input on that. And then for ones that didn't meet it, we just threw them out. For those that went on, we went to the next step, which was next. So we went from about 2,000 down to about 1,800. And then what we did is we went back to NASA WorldView, copied out some geotiffs of each of those potential hail damage swaths, and we generated a geospatial outline of each of those hail damage swaths using ArcGIS, QGIS, whatever. So now we have a geospatial record of potential hail damage swaths. We also, in addition to that, copied over all the metadata into the shapefile. So for each swath, you can bring up the attribute table as well. Next, please. And this is where we got to then utilize other data sets. Archived severe thunderstorm warning, archived tornado warnings, the SPC storm reports in a geospatial format, and then archived radar data also. And how we did this is for each swath, we would generate a box, and then we would plot all three of those around it. So this is the same swath. I have other examples if you want to see them later. But as you can see, we denoted the swath. Those are the hail and wind reports from the same day that we initially said this was a swath that occurred. So as you can see, yeah, that makes sense. There was. This also allowed us there may be several days where you have cloud cover. So a swath has occurred because 5 days after the swath occurs, you see it pristinely in the satellite imagery, but you're not entirely sure which day it was because of some of the regimes. So you have storm reports. So this process allowed us to confirm storm reports. We may have had where we denoted a swath on like August 4th, but this severe thunderstorm warnings all occurred on August 5th, but we had 3 days of cloud cover. So this allowed us to correct for those and, really verify that these are the days they occurred. Next, please. So what we did, so I just wanted to show this real quick because this is a diversity of the swaths that are included in our database. So you can see some are pristine, very identifiable over highly agricultural areas. I don't think I denoted this, but we went 2000 to 2020, and we went May 1st to August 31st on searching for these. And then some of these were also harder to see because of the land cover types, especially early in the season before a lot of the vegetation is growing, or in certain parts of the country where they're swapping out vegetation. Early May, they're knocking down winter wheat or finishing up the winter wheat harvest in Kansas before they get ready to plant. So we just have a diversity in there of different types of damage swaths. So I wanted to just put that in reference for you. Next, please. So how many swaths did we end up with? We ended up with 1,641 swaths over the 21 years. And this is a map of all of them. We went from Montana all the way to Illinois, Missouri, Kansas, all the way to the Canadian border. So do you want to note that you see many long swaths, you see many short swaths. We have a huge diversity of size and shape in here. Also, some of the swaths we had longer, you could tell they were one supercell or one type of thunderstorm, but they cycled. You could tell they cycled like a tornado because you had a swath here, then you had a break, then you had another swath. And what we did is we treated each of those as its own individual swath. Next slide, please. This is then broken down by month. And as you can see, July was the highest month that we had the most swaths over the area. This actually sort of relates back to some previous work that Shinong did, denoting that corn or at least corn crops are most susceptible to hail damage due to the amount of hail that could be produced, as well as just the corn crop itself in July. So that was really cool to see that, we had the most swaths in July, but that's also when some of the agricultural crops might be most susceptible. Next slide, please. So this is a breakdown by year. As you can see, we have great variability in the years. The leading state was also South Dakota. South Dakota had the most, followed by Nebraska, and then Montana. We're still trying to figure out if there's any correlations between any bigger atmospheric events. We're finishing that up right now, but I will say years that had drought makes sense that they had less storms to occur for various reasons. So 2012 and 2006 being the notable, those were years where drought was more prevalent in the area. It makes sense that you have less moisture for potential less thunderstorms, less hail risk, et cetera. Illinois, Missouri, Wisconsin, they were the states that had the most. They had a combined over the 21 years between the three states, they had 17 total swaths. Next slide, please. One of the other things that we're doing is trying to determine and help end users and stakeholders leverage risk. So what we did is we took the database and we gridded it to a 0.25 degree grid over this region. And as you can see, we have some hotspots, Northeast Wyoming, parts of the Dakotas, especially as you're coming off the Front Range or the Rocky Mountains, where you get a lot of those thunderstorms during the warm season in July and August, and then more or less so as you get further east. Nice thing about sort of the work, also working with my colleague Sarah Bang, is, we can break this down by month, we can break this down by year, et cetera, and do all this. So it's really cool to see this potentially provide leverage for risk assessment stuff too, especially when you start adding in more years. Next slide, please. This graphic literally came to me this morning from my colleague, Dr. Andrew Moulton, who has been playing around with our database as well. We're trying to provide ways also to analyze it as we're finishing up this manuscript, because the manuscript is really hard. You can't just say, this is how we found a database. They want, some analysis as well. So we're looking at the day one convective outlooks at 20 UTC and for related to each swath. I don't have any counts on this. Like I said, this came in this morning, but it's pretty cool to see that it looks like slight risk may have the most apparent on there. And I could only find one day of a high risk that produced a hail damage swath. So we're going to go back, when I get back to Huntsville, finish this up and look at this some more and get some more data on this as well. We're also breaking this down by hail, the percentage from day one, 20 UTC, hail risk and wind risk as well. Next slide, please. So what are some additional applications that we're working on with this database? I'm going to acknowledge one of our co-authors who put in a ton of work on this. She did this mostly manually, going through each SPC storm report day and then comparing it through MODIS imagery. So working with a group at NASA Impact, we're at Marshall Space Flight Center, we're trying to leverage if we can do this through machine learning. Using this database as a training and validation data set, results aren't awful, but we are producing way too many positive or false positives. And we're doing that because we're literally reading in true color imagery only. So just a simple RGB. And a lot of the features on the land surface are also triggering hail damage swaths. So we can't remove a permanent feature on the land surface. So we're trying to figure out ways to mask that going forward. And so that's one thing that we're working on. The other thing that has piqued my interest and sort of continues to build off my master's thesis is how to map these. So you get a hail damage swath. I know the insurance agencies and companies, they're like, yeah, that farmer's there, but is there a way we can leverage the amount of remote sensing data we have now to create a satellite agnostic map? So let's say a swath occurs, I'm going to watch it for 2 weeks and I'm going to collect all the satellite imagery that comes in for those 2 weeks. Using this mapping methodology, I could have data from EcoStress, which is a thermal sensor aboard the International Space Station. I have Sentinel-1, which is synthetic aperture radar. NASA will have one up in a couple of years, but I have Landsat, I have some MODIS data. Is there a way that I can map all this in the 2 weeks and produce a final product that says, yes, we're fairly confident these pixels are damaged, but these fringe pixels on the outskirts may not be as damaged as much as in the middle. So that's our next goal, hopefully this winter, to start prototyping some of that. Next slide, please. So I'm going to wrap up. I may have flown through that. I don't have a timer up here, so apologies if we're way ahead of schedule. But again, we know you have, during the growing season, you have these threats from wind and hail on the agricultural crops. Sometimes these thunderstorms leave behind very large hail damage swaths. So we're trying to derive a events database that allow us to see and better understand the temporal and spatial frequencies of these phenomenon. This work was done using SPC storm reports and MODIS true color imagery for the months of May, June, and July. theoretically, we have early September as well, but I don't have a full month of September because a lot of times those areas are harvesting rather quickly and it gets really hard to see. So we're just focusing on May, June, and July. As I mentioned, I'm finishing up a manuscript. I'm hoping I can get this out this fall. We're working really hard on that. And then continuing to work on additional applications, collaborating with you all, but also we're probably going to be looking at trying to get a NASA intern or another UAH student to help us to add in 2021. It is my goal to try to update this every couple of years, every 3 to 4 years if we can, to keep it rolling just because they're not going away. Next slide, please. I wanted to give a shout out to Emily Wazinski. She was I'm trying to do the math now. Yeah, she was a freshman when she started on this project. Her and I met late February 2020. We met about 2 or 3 times in person before we all had to go telework. And I was not allowed in the building. Her UAH transitioned to online schooling. So she was a freshman. We had met just 3 times on starting this project. She took it and ran with it. The 2 years that I was out of the building, she was still working on it. So I give all the kudos for her for going through the amount of data, SVC storm reports, and satellite imagery, while also becoming a Holling Scholar and then a Goldwater Scholar as well. And she'll be graduating this fall, or I'm sorry, not this fall, this spring. So I'm really looking forward to see what she does in our field going forward. My other 2 colleagues, Dr. Andrew Moulton, Dr. Christopher Schultz. And with that, I see the Twitter icon moved over my email address, but that's okay. If you have any questions, feel free to take them or I'll talk to you all after.
Victor, start us off.
Gordon, that's a very unique data set. I think we could all agree on that. And kudos to whoever had to go digitize all of those by hand. Satellite. Mike, did you do any comparison to mesh to see, right, what values or any sort of radar-based analysis on top of the satellite?
We would love to do that. I don't have a full mesh archive, and I don't know where to get a full mesh archive. So I will say on some of can we go to the next slide, please? Nope. Forward. Nope. It's after this slide. It's toward I believe I had a couple extra slides at the end. So we would love to do mesh because one thing we could do is, back up to, sorry, one more. Yep, this one. So what we did is when we pulled in for the validations with the warnings, these are the mesh sizes from the storm track IDs in the archived radar data that we pulled from NECI. So we've started that work, but also I only have where like the center of the cell was being tracked from. If I could get my hands on a full mesh data set, we could do a lot more.
One other very naive question. Are you able to see any changes in like NDVI over densely forested areas from large hail?
Sort of a loaded question. The answer could be yes, but we would need how thick is the forest? Just knowing NDVI, your spatial resolution is going to play a huge factor in it. Theoretically, you could, yes, but there's several other outlying factors. Spatial resolution, how much hail and how much damage did the forest take on from a pre to post event? Like, is it enough to change it? Are 2 of the big things that stick out at me. So I'd love to talk to you more about that after if you wanted. And I'm going to have to stew on that a little bit longer.
Jordan, thank you. Very insightful talk. I sort of have a 2-pronged question for you. Okay. So first, how robust kind of is your general feel for this data set? Do you feel like it's kind of almost provides a climatology of hail in a sense? And then the other piece of that is, are there certain types of hail events that maybe depending on where they occur may not be picked up by the MODIS satellites or or even the SPC data that may slip through the cracks here in your event set?
Yep. Yeah. So good question. So the answer is yes. We feel confident that we estimate 80 to 90% of the events that occurred. There are going to be certain events that we could not pick up because of MODIS' spatial resolution, which in true color is 500 meters. We had daily Landsat imagery, which we're getting close to having every 3 days with the United States satellites and the Europeans, again, clouds. We feel like that number could be higher, and plus your spatial resolution would be able to resolve that better. So that's one question. Sorry, what was the other half?
So I guess it's what types of events may slip through the cracks? Like,
oh, the smallest, more localized events where those are the ones where it could be like this field or 2 had the hail damage and the insurance companies can see it, but I can't see it in satellite imagery.
these hail swaths are?
I would love to talk to somebody that maybe knows a little bit more on that. We feel confident, especially in the ones that we could see from MODIS true color imagery, that we got 80 to 90% of those.
Becky, then I saw Amanda's got a question back there. And we'll
Thanks.
Go from there.
Yeah, really interesting data set. Fantastic. Very curious, have you been able to see any sort of information about how severe, how impactful the damage was from the characteristics of the hail swath?
No, that's something we'd like to do, because this sort of goes back to a question that with the NDVI and the Victor brought up. If you have a pre-event that is very green, very lush before one of these damaging storms come through, NDVI change could maybe tell us some of that. We haven't been able to get into that yet. You theoretically could do the same with the forested area, but we haven't even touched that yet. But that's a future application that we'd love to look on. Now that we know where we have a huge data set of which events to go look at, the amount of data and access to data is getting easier and easier that we could go, automate like downloads and look at that. So,
Amanda, probably have time for one more after.
So my only question is, I think this is really great. So right now it's focused just on that little section of the country. Is there any plans, like once that's all worked out, to expand countrywide?
Yes. So we were hoping the machine learning would be better than it is at this point, and that would allow us to expand it to the full CONUS, but also get into places like Canada that sees lots of these as well. South America, I want to say maybe Europe and like South Africa and Australia as well. That's the goal. I just don't want to have to pay a student to sit there and go through that each imagery each day for like that long. But that's the goal. That's what we're hoping that the machine learning can help us. And yeah.
Right, time for one more. Brian, we have anything back in the chat?
Look over the sandstone and grass. Or the black.
It's tough. Those, I will say, those were the areas where we had most. There are some events that you can actually see, like, oh yeah, that mowed down whatever the vegetation was there. It's easiest to see right there. There were a lot of questionable events, and that's probably gonna be the area that is the most hardest to tell, or that we'll say that we maybe threw out too many events, just because, yeah, the vegetation goes from great green to lush green to brown, and it's very hard to see. But we were able to find quite a few out that way.
Julian, do you have one? Yeah, we'll finish up with Julian.
Great stuff, John. Just two quick questions. Do you have any statistics on the length and width of these swaths? And the other question is, are you using edge detection to identify the swaths, or was it all done manually by eye?
Okay, so for all the polygons, Emily was awesome. She was the one that drew all of those by eye. Now that we have them, we can now theoretically go back, get the data, and start applying more and refining the actual swath data from edge detection, calibrating like NDVI, where there's a sharp departure and NDVI change between the two. So that is one thing that we want to do. The first question I have an answer, but I forgot what it was.
The width and
the width and the length, yeah. So we have preliminary data. Width is the hard one, because if you look at the swath on the right, I don't know how to measure the width on that one. On the length, what we did is we used Python to basically put a box around each of the swaths, and we calculated the long axis. And so I do have preliminary data on that if you wanted to see on it. Majority of these swaths were 0 to 25 kilometers long. Width, we're probably not going to even touch width in the manuscript we're working on, because unless I sit there and measure it, so I don't know how to say that how wide that swath is. If anybody has any ideas, we would love to hear it.
I know we've got a question from the chat, so we want to get to that.
Yeah, they asked, will the output of your results be available freely online?
Yep. So once we get the paper in publication or get it into peer review, we're going to start working with NASA Impact, and who's a group at NASA, as I mentioned, that's helping us in machine learning. They also have extensive knowledge in preparing data sets for public release. So yes, that data set will be freely available to anybody that wants it. And then they'll also help us figure out the best way to update the data set as we add more and more years.
Mark, quickly.
Yeah, I don't care what that swath is. I want the summary statistics of all your swaths.
Okay.
What are the mean? What's the median? Because this is really groundbreaking work. There's not a lot of information informing a lot of models and tools out there around the actual shape of swaths, and this is going to be a big gap. So it's very important that you give not just individual but summary statistics that statistical model could be implemented or built upon.
Noted. Yeah, that's great feedback. Thank you.
I feel like I had to get to Mark. He's a member of the company and it's part of my salary. Anyway, it is really good stuff. And to me, it harkened back to some of the stuff Stan Shangnon did very manually, looking at swath characteristics. There's some great stuff in there.
Yep.
So on we go on the swath topic. Nick Guy's up next. Going to talk about advances in radar-based swath detection and how to relate that into the damage space. So Nick, all yours. We'll get going. Hello, thank you. And I just wanted to kind of point out a couple of my co-authors are here. Scott Ganson and Tori Farney made the trip with me, but Joe Boomgard, Zagrodnik did a lot of this work too behind the scenes. So I just want to make sure that he's recognized before I get started here. Let's see if, oh, here we go. Okay, so just kind of a quick kind of rundown of what our product is. So we have a Respond Hail product, and just an overview for this. It's a geospatial post-event hail data set. It's proprietary, so it's kind of behind a paywall, which I know a lot of you don't like, but that's okay. Data updates every 5 minutes. It lags real time by 10 to 15 minutes, so it's a near real-time pipeline. We process about 144 radars at all times as they come in, and we put that data out within about 15 minutes of receiving that data. And then we aggregate it into both hourly behind the scenes and then daily views for customer distribution. And we provide outputs in vector, i.e. shape files, or raster netcdf files. It's delivered via multiple channels there that you can see, including an API going forward. And it looks like there's a delay, so sorry about that. Oh, wait, hopefully. Okay, so what is the problem that we're trying to do? So one thing I should also note is this is a completely radar-based product here. So nothing else besides radar we're going to talk about here. So if you look at these two swaths, just kind of let's go through sort of a little bit of a thought experiment. What we would like to see here, and what we'd expect, is that you have these two cases, and maybe you have some LSRs that you believe you've QA'd them, they look good. A bunch of 2-inch reports there. You have some swaths that line up relatively well with them, and so you get 2-inch reports on the ground. You get 2 inches from your estimate, and then you have a moderate high in both of those cases. So in reality, we will see in a second, I hope. Wow, this is really slow. That's what I'm hitting. Yeah. So what do we actually observe here, though? Case 1, case 2, same thing overlooking here. We can actually see damage rates that can be low or they can be high. They can be somewhere in between. You never quite know what you're going to get. We see a lot of variability in here. So how can that happen? We go, as we've heard throughout this, the hailstorms are very complex, right? So ignoring non-meteorological factors, so how many roofs are underneath that swath, other things like that, what kind of damage could actually be potentially had, you can actually look at some meteorological factors in here. So duration of event, the quantity of the hailstones falling, distribution of hail sizes, density of those hailstones, velocities, shapes, all those kind of things, right? Things that we've talked about so far. So we kind of took this to heart and realized with that differentiation, maybe we could create something different, something new, a product that we could pair with our hail size, maybe replace our hail size. And we developed the hail impact energy to address this specific issue, leveraging our existing hail algorithm. And we'll wait again. And so I'll take you through a couple cases just to kind of show you what those are. So one other note I should make about our Hail algorithm, which is a little bit different, is that it's a fully polarimetric solution. So we do use existing peer-reviewed literature, and then we've extended it in-house to give discrete Hail sizes. And fully polarimetric, we don't use mesh anymore, but I will show some mesh up here. We do compute it, but we don't use it and serve it to customers all that often. So the first case we're going to be looking at is in Texas. So the 11th and the 12th of April, 2016, this was the Dallas-Fort Worth area, and this was a pretty big event here. So the Insurance Council of Texas estimated this whole entire event, which not only spans this Dallas-Fort Worth area, but is also down into San Antonio, as a $2 billion plus event. The special interest and really the area that we'll be kind of focused in on more here is the Wiley, Texas area, which is right in the Dallas sort of metro area, and I'll show you where that's at in just a second. And there was a really widely distributed loss there. Up to 80% of the houses were estimated to be affected in some way in Wiley, and $300 million damage alone just in that little small area. Just sort of for note here, in 2016, Texas ranked as the top hail getter, for lack of a better way to say that, and really kind of ranks among number 1, number 2 almost every year going back. They do everything bigger there. Oh, wait, they moved off me. Okay, so here, that's where the area of interest is for us, in that red box over showing you in Texas where we're at. That little tiny X that those arrows are pointed to, that's where Wiley is. And over on the right-hand side here, you can see some of the pictures on social media of the massive damage that occurred. So, I don't think they actually build houses like that normally. Those are from hail coming through the roof. That's not a feature, that's a bug. And then you can see solar panels were damaged, and just huge hail was accompanied in here. But one thing I'll kind of note out there too is that behind that guy with the giant softball in his hand right there on the left hand side, there's a lot of small hail sitting there right behind his hand, right, too. So just kind of make note of that. And this one just kind of cracked me up. So I think this is the first time I've ever actually seen someone compare their hailstone to a cat. So I just want to put this in there because I thought that was really unique. But also on the right-hand side there too, they did take another picture that actually helped me out here too. Then shows that not only are you getting these gigantic hailstones, but you're getting a lot of small stuff too, and a lot of things in the 1 inch and 2 inch range, and probably even down to ½ inch in this case. So on the left-hand side here are the claims, and so you can kind of see right there where that sort of dark red is to the northeast of Dallas. That's over the Wiley area, and that's where the biggest density of claims were. And then off to the west there is another sort of central location of claims that was a little bit higher as well. So just kind of keep that in mind as you roll through here. This case I'm going to be talking about is a total of, I believe it's 5 or 6 hours. I think it was from 19Z to 2Z, if I remember correctly. But the samples over on the right-hand side just kind of show you what the output from our algorithms are, and just to kind of take you through sort of historically, what we've kind of gone through here, reflectivity. And then you have a mesh algorithm there on the right-hand side. And then our respond hail size is down the lower left here, which is the fuller polarimetric solution. And notice one thing here is that you have a lot more granularity. You have a lot more, sort of fidelity really with that polarimetric size solution than you do with mesh. On the bottom right-hand side then is our impact energy. And sort of note, this is just a 1 hour sample. So kind of keep that with a grain of salt when we combine things. And are you moving this, or is it just moving on its own now? Okay. I don't know what's happening. So, but it's keeping up with me. So I guess that's good. So this is a accumulation of the full case. So 5 hours worth of data kind of coming through here, zooming in on just one swath right here. And so your eyes are going to be kind of drawn, and I did this on purpose. I drew them intentionally to those blue rings where you really see those really kind of dark spots here. And that's where the largest hail sizes are occurring. But then there in the middle, you also see one, and you'll see in just a second while I have that just in dotted line. There we go. So if you were to, kind of look over on the left-hand side, you'd probably say, well, there's some pretty big areas where that hail size was. That's going to be a pretty substantial spatial distribution of there. If you actually overmap the claims onto here, and I use kind of a darker green, so the darker greens here represent just sort of higher claims, going down to white, lower claims. So, I think I cut it off around 10% or so right there. You'll notice that, it's much more discrete like that. And there's only a few really big pockets where you have really, really high claims in here. And they line up reasonably well with the hail size, right? But then you have that little section in the center. Why would that be unaffected? Well, that same section got hit at least twice, probably once the month before, once the year before as well. So likely there were some new roofs there. And that's the non-meteorological factor that I referred to at the beginning of this. And so those are probably a little more resilient. And so if you're looking at this though in general, you'd say, gosh, well, those hail sizes are big. They're probably going to cause damage right there. So if we compare that then with the impact energy that we are computing, and I'll kind of toggle back and forth and hope that this works with the delay. So you're gonna get a really good view of this. And then it's gonna toggle, oh, it went forward. That's great, thanks. Okay, let's see if I can go backwards. Come on. You got this. Okay, can you go backwards one, just toggle back and forth between, yeah, just toggle back and forth, like forward and backward, and just maybe a little slower. So you kind of just see the changes and distributions here. And so you can really see that it's much more widespread on the higher ranges in hail size than what you see with the impact energy here. So this impact energy actually allows you to really kind of isolate in on the areas that are probably going to have more potential for damage. And so that's kind of cool, right? I mean, it's kind of neat that you can actually cut out that big swath and really kind of make it much smaller, much more discrete, and kind of be able to kind of focus in on that a little bit. And so now you can kind of come forward and just leave it. And so again, just putting the claims on top of that, you see that you know, this lines up really well as well. So, you know, hail size lined up pretty well. Hail impact energy lines up really well. Hail impact energy just allows you to kind of get a better picture of where the hail damage might occur. And interestingly enough, the impact energy not only, you know, in that middle section also had sort of a lower impact energy too. So you had those new roofs, but you also had a lower impact energy that was associated with it. So kind of a double whammy on not getting claims there. Excuse me. So if we look at it as a frequency distribution between those two variables, you actually see a bimodal distribution here, which is kind of cool. So, you know, you actually see two kind of discrete bullseye sizes here. So larger hail, larger impact energy. You see a smaller hail size. And that impact energy, though, really isn't that much smaller. So you have a pretty large amount of those small stones probably falling and actually giving you an almost equal amount of impact energy there. So it's kind of neat. And you see how that sort of goes up to the right there. So you have a big tail that's going off there, but that also is associated with just having sort of those large stones, but also just not having a large number of them, right? So that's what that really kind of equals out to there. If we take that then and kind of break it down into discrete bins of hail energy and hail size, and we kind of look at that together, we can map that against what the mean damage rate is if we just combined all that data together. And so what that figure on the right-hand side is telling you, though, is that as you have higher hail energy and higher hail size, you get better and better relation to your damage rate. Case 2. So I pulled this one in here because 4 years ago, we got here and there was a big old case right before we got here, and it was kind of the talk of the town as we got here. So this one I just want to kind of pull just for sort of more, I don't know, nostalgia, I guess, more than anything, but but it's also a pretty big case in terms of its economic impact as well, right? So the Rocky Mountain Insurance Information Association provided some stats on this. An insured loss of $300 million, impacted several car dealerships, and so this actually resulted in a higher than normal amount of commercial claims that came in too. This is ranked as among the top 10 costliest in Colorado of all time, and you'll see that for that year, what you would have seen if it was stayed. Apologize for all these technical issues. The Colorado then ranked third in the of all the states this year in the number of sort of larger hailstorms and amount of hail events that occurred. Texas number 1, right? Of course, and they would tell you that anyone from Texas in here would tell you the number 1. Okay, so again, here on the left-hand side, this kind of gives you an area of the zoomed in part that we're going to look at for this study. One thing I will note is that, notice I'm staying kind of the Denver metro area. Anyone familiar with this area? As you go east, it used to be that there was less population. I think that's kind of spreading and continuing, but at this time, there was a little bit less population out there now. So really concentrated kind of on this metro area a little bit. Again, social media kind of shows, a different view of different hailstone sizes, some pretty large hailstones in there, but also note that there's some smaller ones as well. And a headline that I found that I particularly enjoyed, if it will come up, from the Denver Post, was Monday's storm in northern Colorado produced baseball-sized hail and larger. So normally, you lead off with the largest hail and you say, and there was baseball, but it's kind of worded funny. And then this kind of reminded me of one of those prescription, commercials where at the very end in very small print, they say slices of stones varied from town to town. Yes, thank you. Yeah. And one thing that I think is really interesting here is that if you look at the distribution, that the 2 and 3 inch stones fell primarily to the east. So you did get some 2 inch stones that did fall within the Denver metro area. There were a lot of pictures of busted out windshields, things like that. But if you really look at like where the big distributions were, that was farther east, and it was actually smaller stones that really fell in the Denver area mostly. So again, we'll kind of show a couple swaths very slowly. Oh, I'm sorry. First, first, again, just showing the claims real quick. And I wanted to point out one thing there. One of the big notes on this was that it hit auto dealerships, and which is why it made it such an expensive event as well. Right there is a sort of a location of a Lexus dealership. Those aren't cheap, and about 250 cars had shattered windshields. Police cars were also affected in this area, and it was a pretty large impact in that specific place. So over on the right-hand side again are sort of your different representations over the years. You start with reflectivity. You can compute something like a mesh in there, and then go to a respond hail size and a respond impact energy. And one thing that I failed to point out too is just do note on the mesh and the respond swath sizes that the response swaths are actually much smaller, so they're much more contained. We don't get quite as large of a footprint as you do get with mesh in there too. So something I wanted to point out there. And for the keen-eyed person, where I'm pointing to the dealership does not correspond with the hail impact energy right there, right? Different hour. This was a 29-hour case, so it was quite an event. I think there were actually 2 storms that rolled through here in two different time periods, and I just chose a kind of a random hour to show this distributions on the right-hand side. So here's the hail swath again. The circle then represents where that dealership was located, right along I-25. And we'll see if the claims show up here. Here we go. And so if you map that against the claims, the claims kind of line up reasonably well again with the hail sizes. And you'll see that, going out 76 there also, there were quite a few claims kind of going out that highway. 76 is kind of the one that goes to the northeast right there. 25 goes straight up north. For those unfamiliar with the roads around here. And you just sort of see, kind of a larger spread of claims around the Denver area. There were lots of cells that kind of came through, lots of different morphologies. It was kind of a really interesting event meteorologically. So we look at the impact energy, and would you toggle this for me again back there? Because I'm afraid it won't work up here. So again, you can see quite a difference here between these two distributions, right? So right in that sort of circled area, you do see kind of an advanced amount of impact energy right there. Right where that sort of bullseye just to the east side of highway or Interstate 25 is, that really corresponds right to where that Lexus dealership was. So they were in the worst place you could possibly be for this event. And then interestingly enough, as you start to go out east, you really start to see that impact energy start to really ramp up. And right there is right where your 3-inch stones are really starting. So that's where a lot of these reports of really large baseball-sized hail were coming from about right there. Interesting thing, if you sort of really stare at this for a while, and I know it takes a lot of staring. I stared at this for probably 2 weeks before this, so I have an advantage here. But if you really look at where those high claims are, they really line up a little bit better here. And if you look at the correlations between the two, legal doesn't let me put the numbers down, but believe me, it's a lot better. So unfortunately, I wasn't able to do that. But if you go on to the next slide for me too. We can again look at the distributions versus one another. I swear that there are distributions versus one another. Here we go. And so notice that this event does have a distinct kind of representation here that's different than that other event here. So you didn't see as many of those large stones within our domain. So you actually only get really a unimodal kind of distribution here for the frequency that really pops out right there. And that corresponds really well with an IBHS front range report that they did that said, 1 to 2 inch stones, really hard stones, are really prevalent along the front range. And that's exactly where that little bullseye sits right there. Again, if you do the same kind of analysis with binning the impact energy and the hail size, you'll see that as the two increase, it corresponds with damage rate very, very well. So the conclusion to this then is that hail impact energy and size are both really well correlated with claims. So if size does do a good job, impact energy does a good job. When you put them together, they do a really good job. So using those two in conjunction with one another produces a much better product than what you have by just using hail size alone. We did capture some of the missing meteorological processes from there, so either directly or indirectly, and that's sort of a list of the ones I had up front. Each one of those is somehow captured, like I said, directly or indirectly within the algorithm itself. And then kind of moving forward from here for us, we're going to look into hail trajectory a little bit more, kind of do a little bit more with the 3D velocity field, and also refine our damage rates with this new information. So thank you. I'll take any questions. One question, we'll wait for Nick. Going once. Anyone in the virtual side? One of our batteries dying. All
hey,
right.
hello. Can you hear me?
Nope. Yeah, go ahead.
I had a question. So how does the product correct for or account for kind of the scan height versus ground level impacts?
I can't really go into that too much because that's part of the secret sauce, to be honest.
But it does. I guess more importantly, it does.
It does. We have physical models that do corrections behind the scenes. That's all I can sort of say. I'm sorry.
Okay, thank you.
Yep. All right, thanks, Nick. We will move on. Just a quick programming note. After our next talk, we will start our lightning poster sessions so those presenters just be aware of that. Caitlin Fons is up next to talk about more on the Hail Swath product side from Athenium Analytics. Caitlin, it's all yours. Losing battery.
All right. Hi, everyone. My name is Caitlin Fons, and I'm with a company called Athenium Analytics. We are an insurtech company, and we've got a wide range of products, but today we're just going to talk about the Hail products. So within the company, I work as a product manager, which means I kind of sit at the interface between our clients and our internal science teams, our internal development teams, and our internal business teams. So I sent my talk over to our marketing team after it was complete, and they said the talk looks good, but it needs a better title. So this is now the marketing approved title, and I figured it was too good not to share. But the general outline for the talk today is to first introduce our company and then spend a little bit of time on kind of the insurance hail problem, introducing that, and then dive into 3 different products that we have at Athenium Analytics with regards to hail processing. I'm going to introduce those products and talk about kind of the science behind them and the data that powers them, but I'm also going to try and address how our insurance clients use that data to kind of bridge the gap between the scientists and the insurance personnel in the room here today. So to start off with, who is Athenium Analytics? Our company was founded in 2012 under the name Weather Analytics. And as the name implies, our founders felt like there was kind of a gap in the market with regards to severe convective storm processing and insurtech products. So we had software that specialized in hail, straight line winds, and tornadoes. From there, we kind of expanded into all natural hazard perils. And then in 2018, we acquired and merged with a company called Athenium, who brings to the insurtech market decades of experience with something called insurance QA. So it's essentially like an internal claims auditing process. So we combined, rebranded as Athenium Analytics. Now we've got expertise on both the internal and external side, internal and external risk for insurance companies. So after working with insurance companies for a decade plus, we've all kind of come to the same conclusion that insurance companies are not a fan of hail. And if you really think broadly about the geographic distribution of natural hazard risk across the United States, for insurers and for companies that are willing to write along the Atlantic and the Gulf coasts, for a large portion of the year, their dominant concern is going to be tropical cyclone risk. For carriers that are willing to write out west, for a large portion of the year, again, a growing portion of the year, their dominant peril concern is going to be wildfire. That leaves this huge region in the middle of the United States, a region that we've seen in these talks is shifting northward. It's shifting eastward to some extent. And for that whole region, the dominant peril concern is hail. So to kind of put it in terms of numbers, if we use the NOAA Billions project, looking back to 1990, the annual average costs associated with damaging hail and severe convective storms was around $1 billion, or just under $1 billion. But fast forward to the 2020s, and that number's jumped up to over 20 billion. So this right here is why the insurance personnel are in the room today. And it's a problem that we're all kind of trying to work together to solve. So at Athenium Analytics, we have 3 different products that kind of address different angles of the hail problem. First product that we'll talk about today is our Dexter Hail, which is predominantly used by claims teams. So that's post-event a verification tool that can be used to handle those hail claims effectively and efficiently. Up next is our daily GIS layers, which is used for modeling. We worked with a data partner there and built out an event set to run their CAP models. And then third product to discuss today is called our Gauge Hail product, which is predominantly used on the underwriting side. So that takes a statistical understanding to looking at historic risk and uses that to create a probability of future risk. So we're going to dive into these one at a time. Up first is our Dexter Hail product. So as I mentioned, Dexter Hail is predominantly used by claims teams. This tool provides hyperlocal post-event verification after an event has moved through. So we have data latencies of about 90 minutes after that event and a resolution of 1 kilometer over the CONUS. And our insurance clients use this data in a couple different ways. So first off, right away after an event has moved through, again, like 90 minutes or so after that event, say we're talking about this event that moved through San Antonio, an insurer would be able to come into our product and basically overlay their book of business on that product and get initial estimates of their exposure to that storm. So it's kind of like a first estimate of potential losses and can be useful for resource allocation right after that event. So that's before claims have started coming in, so kind of even prior to that first notice of loss. And then once claims do start coming in, then this data can be used essentially at the address level to verify whether or not a location experienced hail, and if so, what was the estimated hail size at that location. We're able to help with claims processing, make the process more efficient, more effective. Since the whole goal of this product is to kind of determine which locations experienced hail, there's also, you can look at it on the flip side and say it can help with protect against fraudulent claims, because if you know where it did hail, you also know where it didn't hail. So this product got a complete revamp in 2020, and we now have 3 patents pending on the overall analytics here. So there are some of the data sources that we use in the product. This is the overall analysis methods. I'm going to keep this at a pretty high level, but in general, the goal of this algorithm here was to apply a hydrometer classification and hail size discrimination algorithm in as close to near real time as possible while making it computationally effective. So to do that, we start with the MRS mesh layers, and we co-locate that data to the NextRad radar domains. And then from there, we adjust the mesh data using HER-based sounding data. And then slide 5 sub-graphic number 5 there kind of shows the distribution of the mesh data pre and post adjustment. So you can see we're really kind of correcting for the underestimation of the mesh data. That graphic number 6 just basically is recombining the adjusted mesh data. And then number 7 is where we take all of that data and plot it onto our 1 kilometer geodesic grid across the CONUS. And then at that point, so that algorithm runs, the data is available in our product within 90 minutes, and we don't go back and change those. Those are set and finalized once they make it to our product. And then another feature that we kind of have in that product is that as time goes on and the SPC reports do come in, then we allow our clients to overlay those SPC reports. And it's kind of a way to show confidence in our data and allow clients to verify those hail swaths. Oh, and if you have any questions about this, my coworker, Jonathan Fairman, is attending this conference virtually, and he has a poster on this process, so you can ask him all the in-depth questions. So just a couple of quick pictures from our Dexter Hail Tracker. The first one is the hail event that moved through Minnesota earlier this year. There was a couple that went through the Minnesota area. And then the graphic on the right is showing an event in 2018 in Texas, or in Colorado here. And I just thought it was interesting to see the different ways that our Dexter algorithm resolves those different storm motions. So that's the historic, or the post-event perspective. Now moving on to these daily historic GIS layers. So as I mentioned, these are used for modeling applications. Back in 2020, we partnered with Aon because they were looking to build out their CAP model. And so we worked with them to create the event set to kind of feed that CAP model. Our goal was to come up with an event set that was temporally and geospatially consistent and accurate with data back to 1950. I was told the goal here is to make sure we get every SCS event back to 1950 with complete CONUS coverage. So you can kind of see the breakdown there. We broke it into 3 different categories depending on the data available for that analysis period. The time period on the left is, the oldest data. We were more reliant on observations. And then the most recent data is once mesh came online. MRMS came online. So kind of just talking in broad strokes here, for the category on the left where we're most reliant on observations, we start with those observations and then essentially link them using storm motion tracking algorithms from gridded data, and then grid that information. For the middle and rightmost columns, we're essentially starting with calculations of mesh and then adjusting that mesh data before applying the storm motion gap filling algorithms and gridding that data. So the column on the right, it didn't exactly use that language, but it's essentially the Dexter Hail process. We'll go back now, do a level of post-analysis on that data. So you can kind of see how the products fit together here. A couple quick conclusions to come from that work. The graphics on the right are showing a reconstruction of a hail event in 2003. So the hail swaths on the top and then validated against the SPC reports on the bottom. And then the graphic on the left came out of that work and just thought it was interesting. It's not something that I've seen throughout this conference yet, but it's showing the average number of hours of hail per year. So caveats there are that it's looking at hail sizes of a ½ inch or greater and considering the time period from 1995 to 2019. So it's pretty interesting to see. Of course, we see that big bullseye over the center of the United States, but it is surprising to see how far east that hail activity extends, pretty much right through that I-95 corridor on the East Coast. So those are the daily GIS layers for the modeling application. And then last up is our Gauge Hail product, which, as I mentioned, is predominantly used by underwriting teams. So Gauge Hail takes a statistical approach to looking at historic risk and uses a probability of future risk. So it's kind of perfect to talk about Gauge at a hail conference like this, because I was told that when Gauge was originally developed, it was because one of our insurance clients came to us and whatever hail map they were using at the time, they just weren't happy with, and specifically with the hail risk assessment over Texas. And they came to us saying our claims data does not match up with whatever map they were using at the time. So we originally built out a new tool. At the time, it was a new tool showing hail risk over Texas. Now that's, of course, been expanded to the full CONUS and a variety of other perils. But that's really kind of the inception of Gauge. Moving forward, Gauge actually just especially Gauge Hail just got a revamp earlier this year. And we actually used a lot of the data from the event set that we built for the modeling applications. So again, all these products kind of feed into each other. So using that event set as kind of the base history for the statistics. And the output here is a relative hail risk score. And it's a union probability considering the two types of events listed down on the slide here. So we're really getting at both sides of that more frequent, less severe, and less frequent, more severe coin. So the final output here is a risk score on a 1 to 10 scale, where 1 is obviously going to be a lower risk and 10 is going to be a higher annual risk. And these are just kind of some screenshots from the gauge product. So we're obviously returning that 1 to 10 risk score, but since this is an underwriting application, we know underwriters want a lot more information. So we're including that annual hail probability. It's kind of an output during our statistical analysis process there. And there's a variety of other stats included in that product as well. On the right, kind of showing that distribution of hail risk across Colorado, but everybody can guess where those mountains are. And then if we ever needed another way to kind of pose this hail problem for insurance, I think the graphic on the bottom right would be a good example. So this is showing a screenshot broadly of the Dallas metro area. And so this is a region with a ton of homes, obviously a lot of homes that need to be insured, a lot of businesses. There's a lot of people that live there. And over what is a fairly small region, we see a pretty high or a pretty wide range in hail risk scores. So this is why insurance companies are trying to understand this, trying to make sure that they're pricing their products accordingly. So in conclusion, we've talked about 3 different products that Athenium has, 3 different hail products Athenium has that fit into different parts of the insurance workflow. Athenium has expertise beyond insurance and even beyond natural hazard perils and natural risk. But I hope it's been apparent through this talk that understanding hail is really fundamental to who we are and something that we're going to continue to work on with our clients. And it's something that we're going to continue to invest in and hope to continue advancing. So with that, I can take any questions. Thank you.
Thanks, Caitlin. Questions? Questions? Anyone out there? Not. Matt?
Kind of a silly question. The last product gauge, is there a reason that they're hexagonal cells, or is that just a kind of fancy?
Ooh, yeah. So I've been told that the hexagons solve the global gridding problem. So it's a way to keep all of our grid, actually pretty much all of our grid cells within our company are that hexagon shape, and it's just so they stay consistent across the whole globe.
Any more questions? Brian, we have any in the chat? Okay, thank you, Caitlin.
Thank you.
All right, I guess I should come up with some kind of big like sports announcer voice for our lightning poster session. So here we go. Let's do it again. Up first, we'll get those queued up. David Deline will start us off. Chris Sanders is second. So you guys head on up here and then we'll follow an order that's on the program. Remember, 1 slide, 3 minutes. I'll tackle you if you go over. Actually, we were all like super fast in session 1, so we'll see what the group in session 2 does. And we do have a few virtual presenters, I believe, that are as part of this one as well. So David, all you.
Okay. Sorry. I have a poster presenting some work from one of my graduate students that graduated in December. And this is analyzing the effectiveness of the Calgary hail suppression project. So they do an operational project to try to reduce the risk of hail. And we, from the analytical side of looking at the radar data, try to come up with ways that we can assess the effectiveness of an operational program. And it's a statistical analysis. And the big problem is that there's no good controls to compare with. You don't know what would happen, and they try to affect all the cases. So we looked at times before seeded with what was done for the treatment of the crowds and came up with a methodology. But we have limited data that we've analyzed so far with 2017 data, and we hope to apply this to our entire radar data set to see if the initial results hold through. So if you want to talk about that, please come and see me at the poster or catch me sometime.
Thank you, David.
So everybody knows the IT guys back there hated me because my slide has 2 videos in it and was, I think, larger than all the other slides combined. But what I'll be talking about at my poster session is a newer roofing product called stone-coated metal that is starting to come onto the market. I'll talk about what stone-coated metal is, how we were impacting it, what size laboratories hailstones we were using, the damage that we kind of expected, and then also the damage that we found that we did not expect, and some of the issues that could go into that, as well as some cost information on that. So.
All right, thank you, Chris. Yep.
God, I don't think I can beat that. So my title of this, you can't read it, but it's about S-Pol and about how to enhance the measurement capabilities of S-Pol. This thing advanced and it wasn't supposed to. I'm not doing well. Can you take it back? So the first picture, how to advertise S-Pol, better than just taking a look at these beautiful RHIs. On the left is Z, on the right is ZDR, and you take a look there at the ZDR column and how you can define all these readings with polarimetric radar. If you're interested in that storm, you can go to that BAMS article up there in 2018, so come to the poster and I can tell you more about it. High resolution, oversampling, low cross coupling, LDR, I'm reading on the green, high data quality, superior calibration, and S-band non-attenuating, and there's no radome, that's important. Next slide. So the second part is about, well, we got a great radar, but how can you make it even better? Well, what we want to do here is turn it into a dual wavelength radar, and we're going to do that on the top right-hand side with a dual wavelength feed horn. If you take a look close there, there are S-band ports, H and V, and C-band ports, H and V. Here's an example of so this has been modeled and physically designed, and we're just waiting for the check to come in the mail so we can actually cut this. And so on the left-hand side are copolar patterns, both S and C band. You can see how they lay on top of each other. The x-axis goes out to 2 degrees. There's about a 1 degree main beam on them, so they match up beautifully. The cross-polar coupling is way low on them. On the right-hand side is the difference between the ZDR numbers, and you can see we're under 1/10 of a dB out beyond a 1 degree beam width. And so the important thing here is that it's coming out of the same feed horn, going into a parabolic reflector, and the far field, these are far field beams that are matched, almost perfectly. And so if you want to know more about that, come over to the poster. And if you'd like to use a dual wavelength S-Pol, express your opinion to NCAR, NSF, and me, because unless you come out and you demand these instruments, the money's going to go into chemistry and airplanes and those types of things. So you guys have got to speak up and say, hey, this is what we want.
That was perfect, John. Thank you. Program and absolutely. All right, one of our fearless leaders, Becky, you're up next.
All right. And luckily, this is not about chemistry, so phew. So this project, I want to point out all my wonderful co-authors here, particularly Tim Supine, who's an FV3 guru. So this project really started off as us attempting to implement CAM Hailcast instead of in WRF, implement it in the UFS, which has the FV3 dynamical core. Got it working. We wanted to validate it to see how good it was. And it quickly became apparent you have to have a discussion about what good is, and for that matter, about what a hail forecast is, which apparently is quite different. After having some talks at the HWT, it became apparent hail forecast to some people can mean like an output from a cam, a nice little hail swath containing exact inch sizes, or it can mean something like a large probability of a large area with a probability of 1 inch hail or 2 inch hail, more like the SPC day one outlook. So depending on which type of forecast you're looking for, your definition of good can vary too, by time, by location, by hail size, et cetera. So yeah, this just goes into different ways we verify, different ways we try to determine goodness. And then if you really want to know how it performed, you can come see me. So.
So I've been advised that I should take over 3 minutes so I can feel the wrath of you tackling me.
Should know, they came to the field with us years ago as a student, and
it's been a while. Yeah, so my poster is on a parameter that was developed in the 80s called the Hail differential reflectivity. It's just a simple ZH-ZDR relationship. So there's a lot of drawbacks with it, but we figured with the availability of the severe hazards analysis and verification experiment data set or SHAVE data set, that we could use it to very quickly verify maybe some just quick stats about size, if we can glean any size information, or just possibility if there's hail actually contained in that volume. So some just quick stats about the SHAVE data set. What we used for this study runs from 2010 to 2015. There's over 443,000 observations that we used in this, from over 48,000 cases, distinct cases. We use single radar polarimetric output from the MRMS suite of algorithms and then use that to compare. And so in case anyone's wondering, I didn't want to throw up the math to scare you away from my poster. So the relationship is given by this line in the figure in the bottom left. So if you want to know the relationship, if you're really a mathematical person, feel free to come over and see that. And then just some quick output from it on the right side, comparing it to the hydrometeor classification algorithm, and then just some of the size data that we had within the SHAVE data set. So if you guys are interested, come on over and see my poster.
Well, on the vertical, Jeff, and how I saw you looking there in the radio folks.
Jeff, I don't think, you might not have been able to hear me. I think I see you over there in the Hollywood Squares boxes.
Yeah. I'm here.
Gotcha. All yours.
Okay. Do you want me to share my screen? Oh, I thought you were just going to show the presentations.
See, I'm looking at Kelvin back there, but if you can go ahead and share your screen, or though they're working on it in the back. There we go.
Okay, awesome. All right, thanks. So back in the Severe Storms Conference in 2016, there were 3 papers that were given that involved some aspect of updraft width, one by Warren, one by Cumgen, one by Trapp. Hopefully all of you at the workshop are familiar with the Dennis and Cumgen paper published in 2017 and the follow-ons that basically proposed a relationship between hail growth and updraft volume, which is going to be also represented in terms of an enhanced area. So we were also looking at updraft area, but within context of tornado intensity. But also in this paper, what we did was to explore a relationship between the width of an updraft core at mid-levels and its imprint at storm top, or in other words, its overshooting top. So what we found within this set of simulations that explored a range of updraft areas is a pretty robust relationship between the area of the overshooting top and its corresponding mid-level updraft area. So now bearing in mind that satellite applications involving hail typically involve some aspect of updraft speed, we asked this question, does hail size relate to overshooting top area? And so we wanted to explore this. So we piloted this idea through Max Grover's thesis at Illinois. Max used NCI hail reports, GO16 IR brightness temperature data, the OT identification algorithm, essentially by Betka, and then the overshooting top area algorithm by Marion, which basically looks at radials emanating from the center of the overshooting top in brightness temperature, and finds basically the inflection point and calls that the edge of the overshooting top. So we use this data, and basically Max showed at least some promising results that distinguish small size hail with larger hail. But this data set was fairly limited, only about 6 months, and it only used the 5-minute data. So what we're doing right now is exploring this with a much longer time series, or essentially the entire GOES-R series, using the 1-minute mesoscale domain sector data. And this is using a new OT algorithm by Yuan Hong. But most importantly, what we're doing is retooling our overshooting top algorithm, area algorithm, such that we're not assuming a circular area, which is what we did in the Marion study, but now evaluating this as a polygon, which will allow us to evaluate characteristics of the area, including the major and minor axis, going back to the Dennis and Cumgen work. So I'm obviously not there in Boulder with you, but if someone wants to talk with me at some point about this work, I'm happy to set up a time to do that. Thanks.
All right, thank you, Jeff. I believe we're on to Tobias Schmid. I don't know if I see you in the squares. If you're there, hop in.
I'm here.
Oh, there you are.
Can you hear me?
Yep.
Okay.
Yeah, we got you.
Perfect.
All yours.
Okay. Hello, everyone. I'm Timo Schmid, a PhD student at ETH, and I'm happy to present to you guys the SCCLIM project, which is the seamless coupling of kilometer-resolution weather predictions and climate simulations with hail impact assessments for multiple sectors. And behind that long title, there's a 4-year interdisciplinary project led by ETH, University of Bern, and Agroscope Switzerland, which has started earlier this year. And the aim of this project is really to model this full model chain. So starting with sub-project, so it's structured in 5 sub-projects, with Project A leading this kind of co-development and stakeholder engagement, and building the impact platform with the open source probabilistic risk modeling framework Climata. Then in sub-project B, that's where all the climate modeling is happening. So there we run high-resolution climate simulations with the hail diagnostic Hailcast for current and future climate with a pseudo-global warming approach. Then in C, it's more the observational side of hail. So it will focus on validation of radar-derived hail size estimates using crowdsourced observations, as well as testing new approaches with polarimetric radar data and identifying drivers of past interannual variability. And then D and E are at the end of the modeling chain. So that's where we really go towards the impact, with D focusing on developing time-dependent vulnerability functions for different crop types that account for phenological plant development. And sub-project E focusing on modeling damages to buildings and cars, also going towards impact-based warning systems. And yes, on the right side, you can see output of a first version of the model that estimates the number of affected buildings of an extreme hailstorm in 2021 based on mesh. And yes, so if you're interested in that, please come see the poster. There's a bit more details on each sub-project, as well as some preliminary results focusing on the 2021 hail season, which was an extreme hail summer in Switzerland.
All right, Timo, thank you. And to close us out is Jonathan Fairman from Athenium again.
All right, so yeah, if you can just click play on the video. So to take advantage of this, I sort of wanted to show the actual Dexter portal that we have developed at Athenium, sort of, live presentation with a nice little screen capture. That is, if the video loads, and if it doesn't, then I'll just give a little bit of a preview to the talk. So the poster will go over in a little bit more detail about the actual processes that we put into for Dexter Hail. Caitlin will be standing next to it, and if there are any more detailed questions about the exact processes that and the reasons why we did what we did, she'll be able to either send me a text or Teams me, and I'll be able to video in and chat with you guys. But our overall objective really was to try to enhance the probability of detection from a mesh-based layer, and to increase the accuracy in terms of the total hail size. So our Dexter Hail product is actually about a 7-year history. We go back to June 1st, 2015, and through up until 3:00 p.m. Eastern today, 1:00 Mountain. And within that, you can actually select individual days, and each individual day throughout that entire process. And the algorithm is the same for the entire length of the record. And we have applied that dual pole hydrometer classification algorithm and size distribution algorithm to raw radar that we have discriminated and been able to be computationally efficient by using the NSL mesh as our base layer. 4 years ago, some of my colleagues with Athenium did present some of the Dexter Hail data in the initial version of that product, and this is extended based upon that. But come see me and talk to me again. Thank you very much.
All right, thank you, Jonathan, and thank you to all our lightning poster speakers. For those posters that are here, it's right next door, one room over. Please go peruse them, have a look. See, our formal poster session will be tomorrow morning, but we'll have the traditional kind of poster, as I call it, the most awkward hour in science, but that's just me. But we're about 10 minutes ahead, so we'll go ahead and take our afternoon break, but we will reconvene back in here to start our afternoon session on field campaigns at 3:20. So 3:20 back in here to start that, and I'll turn over session sharing to our fearless leader, Andy Heimsfeld. So thank you. Well done today.
Okay, I think we'll get started for the final session today, and it'll be on field campaigns, ongoing, ones that have recently ended, and ones that are planned for the future. But I do want to emphasize that everyone who's giving a talk tomorrow, presentation, please upload your talks as soon as possible. And if you have any difficulties, you can talk with Shelley, who's out in the front greeting people. So our first talk will be by Julian.
Thank you all for hanging out to the late afternoon session. I know usually by now this is my sleepy time, so I'll try and stay awake. Yeah, thanks, Andy. So I'm going to talk about a project we did this summer as a pilot program for doing field work. Probably the first field work in Canada on hail in about 40 years. So we're hoping through the Northern Hail Project to do some great stuff. So I've got a few slides here that are just give us the details. If I can find the right key.
Left or right keys?
Yeah, I couldn't tell you. I should be able to tell you, but I can't. Oh, it's really slow. Okay, so if you don't already know, what is the Northern Hail Project? And just so you know that we're not doing this work in isolation, we have some great industry partners and academic partners. We're working with the Institute for Catastrophic Loss Reduction in Canada. We're working with Instant Weather. And of course, we have our great friends and colleagues down south with IBHS, who we've been working with closely with, and other groups like WeatherLogics and the University of Manitoba. So with the Northern Hail Project, we want to have a data-driven approach with tangible outcomes. So both theoretical, but also things that we can apply directly in the real world. So the bottom tier there, you see the data that's going to feed into the higher tiers. And I won't discuss all of them, but you'll see this, it's quite ambitious what we plan to do in the coming 5 years should we secure funding. So we're going to be looking at hail characteristics. We're going to be looking at hail fall speed and aerodynamics. We're going to be looking at rural and urban hail damage surveys. And all this is going to work towards feeding into a National Hail Event Archive climatology, catastrophic modeling, and numerical modeling. So what we want to do basically is advance the meteorology, climatology, and impacts of hail in Canada. And the outcomes we're hoping are going to be beneficial to Canadians, municipalities, businesses, and other stakeholders. And I also want to say at this point, we've got funding in through NCERC, and hopefully we'll get it. So we have funding for as many as 10 PhD students, 7 master's students, and approaching 50 interns. So if anyone is considering starting a master's degree or PhD or wants to work in the field and do some really neat stuff, please come speak to me. Okay, it might take a minute or two. Oh, see, now it's gone too far. All right, so we're a very small group. The Northern Tornadoes Project is much bigger. We are where the NTP was circa 2019. So there's me, Simon, who's my research meteorologist. And then this year we had Francis, who was the field ops leader. We had 2 summer interns this summer. They stayed in Red Deer and were kept very busy, but they assured me they had a good time, even if they did both work very hard and probably much harder than they thought they were going to be working. And I'm going to be sharing some of the results from our first pilot field program. So ultimately what we want to do is reduce impacts. Impacts are obviously very expensive, but there's also a social component to this. Any of you who have had water damage to your house, flooding, or hail damage to your roofs or siding, it's very disruptive, it's costly, it's stressful. So we're also going to be engaging social scientists to help us work through this and to better understand that aspects of things too. We're also wanting to understand impact drivers much better and receivers such as buildings, infrastructure, vehicles, and such. And we also want to determine damage thresholds, so making note of things that break and also importantly things that don't break. And more climatology right now for Canada. If you look at the latest climatology for Canada for hail, if you could even call it that, it looks like one of those papers that was written in the 1950s or 1930s by hand. It's quite embarrassing, and we can't do a good job of mitigating risk with such a poor understanding. So that's very high on our priority list. And we also want to reduce damage by documenting and assessing the impacts of hail and ultimately improving building codes. So something a little exciting that we were not expecting this summer with our first field program. My boss, Greg Kopp, I asked him, so what are your expectations for this summer? He said, if you collect 1 bag of hail and freeze it, I'll be happy. So that was like, okay, that's a pretty low bar, and we far exceeded that, I'm glad to say. In fact, we set a new record for Canadian hail, and this wasn't the largest hailstone that day that we collected. One of the interns was running with one of the hailstones and he dropped it, but he assures me it was bigger than the one that we ended up measuring. So yeah, but this area, Markerville, is just southwest of Red Deer, north of Calgary, and it's no stranger to hail. This top scene is not in winter. This is on a 10th of August, 2006, and we had a devastating hailstorm that day. Golf ball hail, wind-driven hail, and you can see the siding on that building is just, shredded. And below, you can see the trees were denuded, and even some of the bark was damaged on these trees. And that's another thing we're going to be looking at, in fact, with the Northern Hail projects. It's not just crops, but trees too. So our team was out that day, thank goodness, and this is so slow. Maybe I have to press really hard. Or twice. Oh, there we go. So this is just an event overview. That photograph up there was taken by a storm chaser, and it was at about that time, when that photograph was taken, it was about the time when the hail was falling, the record hailstone.
it was a lot of people out that day chasing that storm. But when you looked at the synoptic setup for that day, everyone was expecting, a possibility of supercells and severe hail, but nobody was expecting a record. And similarly with the Calgary hailstorm, there was a risk of severe hail that day, but again, nobody was expecting $1 billion hailstorm. So these forecasting extremes is difficult, right? Because you're arraying the tails. And I'm just going to speak onto the slide because it's insisting on staying up there. So the top left panel there, we've got the mesh, accumulated mesh map. We used mesh a lot this summer to help direct our team who are out there in the field. Remember, there were just 3 of them. So there was the driver, the navigator, and the person in the back doing comms. They were in direct contact with either me or Simon or both of us, and we were guiding them. That black line there is the route they traveled. The black circles are where they sampled hail and where they collected hail, bags of hail. And we had a portable freezer that was powered off the car. It was -18. And they filled that freezer on this particular day. They collected 14 bags from 6 locations, and they tracked the storm for about 100 kilometers. And you can see in the bottom right-hand corner here, where we have those pink colors, that's where the storm crossed Highway 2, which is a major artery between Calgary and Edmonton. And that's where some of the cars stuck on the highway sustained incredibly bad damage. It was very traumatizing for people who were stuck on the highway that day. And then below that, we have our record hailstone. So it's about 12.3 centimeters across, just under 300 grams. And but using the bulk density from the 3-dimensional scans that we got from IBHS, they very kindly sent their crew out. I think it was their first international gig. And we were more than happy to let them come and scan stones for us. So there we go. So that's the hailstone there. And you can see, as many hailstones, it's got strange protrusions on it, lobes, very interesting surface texture. And it looks like some parts may have broken off. They found this under a copse of trees, and we think it maybe, some of it broke off when it was hitting the branches. So I'll try and go to the next slide. So how is the Northern Hail Project addressing some of these knowledge gaps that I referred to earlier? And we're doing that using a multifaceted approach. Obviously, this year, we couldn't do everything we would like to do. A lot of it was just developing operating procedures, learning what we could do, learning how to do things properly, making lots of mistakes. There was some colorful language at times. But, if you're not making mistakes, you're not learning. The important thing is to learn from your mistakes. So I'm sorry, I'm having trouble advancing these slides. Maybe could you guys at the back do that, please? All right, next slide, please. Keep going. All right, so one of the big things that we're looking at is data collection methods. And we're going to draw on a whole suite of possible options here, everything from surface-based to space-based. And we're also going to be going out doing damage and impact investigations. We've got a bunch of engineers on the team, and they're more than keen to go out there and collect data. And we did our first damage surveys this summer, and I'll show you some results from that. We had hail report and remote sensing monitoring. We also drew extensively on social media, trying to get out there and educate people on how to report hail properly. And that had some success. We were slowly growing our number of followers on the Twitter page where we asked people to report. And we were focused in Alberta because that's where we were guaranteed the best success. Given the climatology, and it didn't disappoint. We had the field operations, like I said, this pilot study where we're going to actually sample hail swaths. And we also were drawing on remote sensing such as radar and satellite and special sensor networks. So one of the grad students this summer in that center panel on the right, we have a continuous waveform radar. It's the size of a credit card, runs off a Raspberry Pi. We were able to use that to establish the threshold for hail that it can detect, and then the sampling volume, effective sampling volume. So that can detect down to about 15 millimeter diameter hail. We're using ice spheres dropped from UAV. And by 5 centimeters, you're looking at a sampling area of about 25 cubic meters. So that's substantially larger than a hail pad. So we've been doing some exciting work like that. Hopefully down the road, we'll be able to have a portable test bed with a dual polarization C-band radar from the old Canadian radar network. We'll have meso network cameras, hail pads, lightning mapping array, and mobile soundings. So we're just going to get bigger and better, hopefully moving forward once we secure some funding. But what's very important is, obviously running a pilot program is very expensive and very time consuming and very labor intensive. I mean, it's not sustainable for a long time. And if we're going to go across Canada, we're going to have to rely on remote sensing. But we need the ground truth data to improve existing algorithms and develop new algorithms and have the confidence in them that we can apply them nationwide. And like I said, this requires investing in collecting reliable ground truth data and also documenting hail damage to infrastructure. Next slide, please. So just a summary from this pilot season. We had a team of 3 in the field for 2.5 months. They had a good time. They learned lots of skills. The goals were to test concepts, develop operating procedures, and collect high quality ground truth data. This team went on 20 sampling missions during that time. They sampled 38 hailstorms at 272 locations. Every time they were at a location, they had a iPad that had cell capability and an app. We worked very closely with the library at Western University, and they built us some really neat GIS-driven data maps, and we could enter all the information in there. I haven't shown a page here, but including damage indicators, percent of ground covered, largest hail size, things like that. And they drove almost 20,000 kilometers to sample the storms and maintain the hail pad network. Maintaining the hail pad network was very intensive, labor intensive. We had 35 hail pads out there, and one location was hit 3 times by different hailstorms during the summer. And we collected 55 bags, it's over 100 kilograms of hail, and now that's all safely stowed at the Canadian Ice Core Laboratory in Edmonton, and we just need a student to volunteer to start looking at those data. We'll keep you warm, I promise. We'll get some warm clothing for you. But we learned many valuable lessons this year, and we plan to expand the number of personnel in the field next year and maybe even go as far east as Saskatchewan. Next slide, please. Just before I forget, that map you saw there was just the routes they took and all the sampling points. So I spoke briefly about the hail pad network. So we had 35 hail pads. That's what I figured back of the envelope was sustainable. And they were separated by 3 kilometers. That's pretty much the farthest you want them to be apart. And they were a little farther separated in the east-west direction. We had excellent buy-in from farmers. So long as we didn't say anything about being federal government, they were happy to accommodate us. And, even without us asking, they would text us when it hailed, and they even collected hail samples for us. So people are really happy to help, and that's great. We had 93 hail pads hit, and like I said, one location was hit 3 times. We also deployed hail pads ahead of hailstorms, and some of them we mounted a very cheap action camera. It wasn't a GoPro, it was about $50 action camera. Cheap being because we weren't sure if it was going to survive being hit by hail. And to help analyze the hail pads, for those of you who've tried to do it manually, it's very labor intensive, it's subjective, and we want to make it as objective and quick as possible. So one of the students wrote some CNN, convolutional neural network code, and you can see that on just below the hail pad map there. And we already have a few classes like wind-driven hail, bird pecks. Birds seem to take an interest in our hail pads sometimes. So the code has trained, and it's done a pretty good job, but we want to expand that. The bottom left there is just one of our hail pads. And if I can can somebody get the movie going? So the top right is just a movie taken near Rocky Mountain House. And I sped it up here so they can see the interest isn't the hail hitting the hail pad so much as, the hailstones that landed on the hail pad, because when it's raining, you can't see it very well in this particular video, but you can really see how quickly the hail melts. It's incredible as the smaller hail, how quickly it melts. And oftentimes, even after deploying the probes, you arrive there 15 minutes later, the hail pad's dented, but there's no trace of hail. And if you just click on the bottom right image, when IBHS was over, they also did a 3D scan of one of our hail pads. And it's actually helped because the raw hail pads are quite noisy. And by doing a 3D scan, it actually smoothed out some of the noise, and I think it's going to make it much easier to interpret the hail pads, what was happening with them. So next slide, please. So how are we addressing societal risks? So next slide. We did our first damage impact investigations. Ponoka, which is north of Red Deer, got hit by a really bad hailstorm this summer. And our engineers went out and did a detailed forensic damage documentation, looking at failure modes, looked at what broke, what didn't break. We saw lots of shredded vinyl. Vinyl does not like hail, and it doesn't like wind. So is this the best material to using in this particular part of the world? I'll let you figure that out. We also interviewed people, and you know, people will talk your ear off, but you get some really helpful information about the storms and event sequence and duration. And what we want to do is develop a SOP for conducting hail surveys in rural and urban environments that can be applied across North America and elsewhere. And you'll see on that top right image there the role of wind. So the right-hand side there, you can see the vinyl shredded, but to the left by the barbecue, there's no damage at all. So the hail here was clearly wind-driven, and it made it that some surfaces were, you know, exposed surfaces were destroyed, whereas others were completely protected. And next slide, please. So this is another day. This is in Saskatchewan. Again, we got the radar mesh map. We found that mesh was very good in helping direct the team, but it was by no means a guarantee that they would find hail, because they could be out of position by 1 kilometer or less. But we're hoping to improve on this in moving forward. We've got to find something better than mesh and allow for hydrometeor drift so that we get to the right place at the right time. Our goal is to get there within 20 minutes. This year, our average was 24 minutes to get on at the site when after the time we thought the hail fell, but we were as much as an hour late and sometimes, and that's just way too late. So we were hoping to get down to 15 or 20 minutes after the hail fell. Anyways, so this is, again, we saw lots of pictures this summer of shredded siding. And next slide, please. And Jordan earlier was talking about hail swaths. We have a contract with Planet Lab. They got a whole constellation of satellites up in space, very high resolution, spatially and temporally. And we're also starting to document hail swaths as identified by the Planet Lab. We're using optical here, of course. So we, you know, as Jordan pointed out, there's certain limitations with cloud cover. But this is one particular hail swath over Alberta that we identified this summer. Next, please. And here you can just see the arrows pointing to where we did some post-storm crop surveys. And you can see even the bottom right was taken, the photograph was taken several weeks after the hail swath was caused by the hailstorm. And you can see the vegetation hasn't recovered. It's still looking pretty sad. But what we're hoping to do in the future is to do flyovers using fixed-wing UAVs equipped with thermal imagery cameras immediately following the storm, and then to do revisits. We're hoping the thermal imagery, the technology is much better now. We have much better resolution than we used to have. And we think that thermal band will help us identify hail on the ground, and then we'll do revisits using multispectral cameras attached to UAVs later on. Next slide, please. And this is just this is more illustrative than anything. So this is, obviously we don't have any results to show really from the first summer, but this is where we want to head, where, you know, we have 3 images here and we have progressively worse damage going from left to right. And so on the left, you know, there's some damage, but it's fairly scattered. Then in the middle, we have some significant loss of vinyl siding. We're noticing that not only was the vinyl siding getting damaged, but the vapor barrier was getting damaged too, and even the foam insulation. And if you have water, if your envelope when the building's compromised, not only during that storm, but subsequent storms, you're going to have problems. So this problem just escalates with time once your envelope is compromised. And then on the far right here, you can't really see it because the quality is not good, but the double glazed window was also broken. Next slide, please. So just an overview here. We did field operations this summer. We had very ambitious goals and a very successful pilot season. We have more data than we know what to do with. We did identify some failure modes, and we're already identifying materials particularly vulnerable to hail impacts. We're working on improving our climatology. We're going to continue to engage people and the public and do some outreach and education. We're trying to link weather to impacts and understand the kind of conditions leading to damaging hail, and that's when we'll be releasing sondes ahead of storms in future years once we have our portable network set up. And we're going to be developing risk reduction measures, identifying materials that don't perform well and materials that do perform well. Thank you very much.
Yeah, thank you, Julian. So questions for Julian? Yeah.
Yeah, hi. In the hailstorms you're collecting, I think you showed density measurements. Are you're measuring density for every hailstone that you're collecting?
Mass divided.
The stones that we could scan using a 3D scanner, yes.
Okay.
Mass divided by volume.
Yeah.
Pardon?
It's the mass divided by the volume from the scan.
Oh, I see. Okay. Okay. So it's computed. I'm just wondering what the variability of the density is for the.
Well, we scanned 30 stones when IBHS came out. They varied between about 700 kilograms per cubic meter to over 900, but the mean was around 870. Yeah.
Other questions? Yeah.
I had one online, if I can ask.
So you mentioned the government playing a small part in this. Is there any other collaborations with Environment Canada, or them helping you guys support you, or working side by side on anything?
Where we will be collaborating with ECCC is on the modeling front and also on the radar front. So yeah, they're the proprietors of the radar data, and we'll be working with Jason and others to improve the modeling using these validation data that we're collecting in the field.
I think we had Isabel online there, if I see that correctly.
Yeah, thank you. I would love to know a bit more about, you mentioned like a sort of Twitter campaign to try and get reports. Like, how did that go? What did you do? What sort of response did you get?
It's mixed, and it's very time sensitive. You really got to ride the wave after an event when there's a lot of interest and a lot of eyes. So what we've been doing on big hail days is we've been sending out a tweet just as the storms start to develop and intensify and the first reports come in, because that's when we find the like if using a particular hashtag, the number of hits increases. The reports have been mostly good. People are not necessarily as good at following up. So the more people you can engage without having to follow up by direct messaging or anything like that is really good. But if you have a dedicated hashtag, that'll help a lot, or a dedicated Twitter account.
Other questions? I have one. Do you have a reasonable way of going from hail pad, hail dent diameter to physical diameter?
Yes and no. We're still using the energy matching method when you drop a steel ball.
Yeah.
And I'm not a big fan of that. So what we're hoping to do now with the UAVs is deploy an array of hail pads, because we noticed this summer that when we drop the hailstones, even though they're perfect ice spheres, there is quite a bit of drift. Even without winds. So, but we can go up to, with the current limitations on UAV altitude, flight heights, we can go up to about 3.5 centimeters and attain terminal full speed. And hopefully we can get some special permission to fly higher to go up to about 5 centimeters. And then I think that's a better way.
It's a good way to do it. Yeah. Any other questions? Yeah, thanks, Emily. Yeah, so our next speaker will be Michael Kunz, and he will be talking about Swabian Moses, a multidisciplinary field campaign to investigate severe convective storms and hail. Michael?
Yeah, hi Andy, hi everyone. I hope you can hear me.
Yes.
Okay.
Yes, we can hear you.
Good. Thank you for the information. Thank you for giving me the opportunity to present here our project. Swabian Moses, which was a multidisciplinary field campaign to investigate severe convective storms and also hail. I want to acknowledge my co-authors, with whom we have jointly coordinated also that large-scale field campaign, which took place last year in Germany. And in the background, you can see here a supercell, which directly moved over our main site, where we installed most of the instruments. We had a bunch of partners. KIT was the coordinator of that campaign, but there were a bunch of different partners, mainly all of them from at least during that campaign from Germany, most of them from the Helmholtz Association. There is the control. So our core of that, the nucleus of that field campaign was actually a targeted hailstorm operation project and strategy. This was a proposal we submitted to the DFG in Germany for funds. And this proposal was written by Silke Dronner from the University of Bonn, myself, Joshua Soderholm, Matt Kamjan, Martin Hagen. Our idea was to go out to do a survey of hail. Our idea was to have different people in the field, different groups in the field. One group with automatic hail sensors, aerial photos, hailstone collection, to melt the different layers of the hailstones to learn more about the dynamics and the physics within a hailstorm, using swarm zones and drone operations to estimate the size distribution of that. One team who measures profiles and one team also a general team, public team, crowdsourcing to get information from several people about the dimensions of hail, about hail diameters. Unfortunately, we did not receive any funding for the project. Hopefully, we will have that dedicated hailstorm project in Germany next year and in the year after that. But anyway, we already had that idea of having let's say a joint project, and we compiled that together with Moses. Moses stands for Modular Observation Solutions for Earth System. And this is a concept of the Helmholtz Association. Helmholtz Association are the large-scale research center in Germany. And that systems are flexible and mobile observations that can be applied or put elsewhere in the country. The idea of Moses is to more or less holistically investigate the processes, different processes over a large range of scales, processes related to extreme events, and to create synergies as best as possible by working closely together also with people from different disciplines. And the idea was to study the convection from the triggering to the life cycle of severe convective storms, including hail, to the runoff, to the damage in case of hail, and to pollutant transport into rivers. And the other process change was the idea was that we also would care about heat waves and drought because they are somehow related to severe convective storms. We see that the events are usually driven by the same large-scale weather patterns like blocking events. But it turned out we had in Germany, we had a severe heat wave 2018, 19, 2020, this year, 22, but not in 21. So we had to skip the research for the heat wave. Anyway, there were, despite of all that caveats and all that problems, we went into the field. And we went into the field in an area where we, according to radar analysis, we have done before, using an adjusted mesh algorithm, including a tracking, where hail occurs most frequently in Germany. This is the area of southwestern Germany. Here we have the Black Forest, as I'll show in a second, here on the left-hand side. So we have here the Black Forest. This region is the Rhine Valley. In the Rhine Valley, we have moist air masses, usually moist air masses. We have also from the surrounding mountains or low mountain ranges. We also have their wind shear, but almost no thunderstorms and really a low number of severe thunderstorms, as you can see here on the right-hand side. Our idea and our hypothesis is that, and we have seen that also from the model, I'm going to show you that in a second, that the flow do not directly move over the Black Forest mountains, rather go around, meeting here downstream of the Black Forest before this, in front of the Swabian. You are creating a zone of horizontal moisture flux conversion. And this is what we also see in the model. Here on the right-hand side, you see the horizontal moisture flux convergence from Cosmo DE over a period of 5 years, over 6 years for different hail streaks, or at least severe convective storms determined from radar tracking. You see here in red color here the convergence zone, and it fit quite well here with on the previous slide was the area where most of the hailstorms, according to the radar analysis, have occurred in the past. So of course we had more than 30 people in the field. So the scientific questions are, we had several different scientific questions also from the different disciplines, but the central questions are, why is the investigation area a hotspot for severe convective storms and hailstorms? Of course, we have seen the hypothesis, but it's a hypothesis, and it's shown by the model, but it's still not that clear. A model is a reduced reproduction of the reality. It's not the reality. This was the idea, to go into the field and really to measure the flow regime and the deviation, and finally also the convergence area. And the second question is, with all that partner, how to best assess and model the event chain from the triggering of the events to their maintenance until the impact of the events. We had a bunch of instruments, of state-of-the-art instruments, remote sensing instruments in the study area. 5 different radars, including X-band and C-band radar, very new cloud, FMCW radar. We had 6 different LiDARs, different HUD pros, different in situ instruments, soundings. We have a cloud chamber, or different cloud chambers to observe the CCN and INP concentration, cloud condensation nuclei, and ice nucleating particles, several dystrometer, and also hail sensors. We built up a network of 10 different hail sensors. And finally, we have had also a mobile system, or mobile systems, 3 different aircrafts, which were in the air for over a period of 10 days. We had a mobile cosmic ray neutron sensor to estimate what is going on in the soil, and finally a storm chaser team releasing swarm zones. There is no picture actually there, but I'm gonna show you in a couple of minutes a slide on that. We had different observation sites that were equipped with the modern instrument, one Supercell, as you can see here, equipped with different, with one radar, with different, with 2 LiDARs, with different sounding, one stratospheric sounding, ordinary radio sounding, and also the cloud chamber. And in addition, 28 additional fixed sites, as you can see here on the figure to the left, and also the mobile team. And we installed that observation sites and the instruments in the area where we, at least according to the model result, we experienced the highest flow conversion, and also where severe convective storms have their maximum. So the campaign had a duration between May and September last year. The decision on intensive observation, so it was a period of three months, but we had single days with intensive observation periods, as is usually the case with such observation campaigns. And the decision on an IOP was done one day before in briefings with video conferences. In total, we had 7 IOPs, which meant 21 days, a huge number of days, and 12 days came up with hail with diameters up to 6 centimeter. And actually, we only missed one day with severe convective storms. We captured all the events, but unfortunately, one very interesting day was missed. The interest by the media was very high, mainly for our storm chasing activity. So there were more than 30 news reports in the newspaper. We had several interviews given in the radio, and I think 6 or 7 documentaries on television, mainly about our storm chasing activity. And this is, for us, it's quite good, because we can explain via the media contact, we can explain how scientists are working, how research is working, about what we know and what we do not really know, to tell the people about the progress we have received, especially in the context of severe convective storms and hailstorms in the past decades. An example shown here, this is IOP 4 and 5, lasting for a period of 13 days, almost 13 days, or 2 different IOPs. Quite interesting if we look for the first line. You see here the cave, and the cave had values up to almost 4,000 joules per kilogram. But very interesting, on the day, nothing occurred. There was actually no thunderstorm. We had a forecast. We were directly on site, and we were waiting. And at around 10 or 11 o'clock, there was the development of first convective storms. But in the end, no convective storms occurred. This was quite a surprise. And then we had in that period of time, we had two different supercells producing large hail up to 5 or 6 centimeters. So let's start with the first example here, the day with no thunderstorm. We have installed, as I told you, aerosol measurements, and you can see here probably one reason why convection did not occur on the day. On the top right, you can see again the cape here, up to 4,000 joules per kilogram. But as you can see here in that figure, we had on that day a high concentration of Saharan dust. And presumably that high concentration of Saharan dust prevented convection actually to occur. So there was kind of cloudiness throughout the day, but no convective storms that have developed on the day. Unfortunately not, because we were all on site and very excited. And then a couple of days after that, we had a damaging supercell. You can see here, I hope you can see the animation that shows you, on the one hand side, a radar reflectivity, on the other hand, storm reports from the European Severe Weather Database, and this here actually was the supercell, which directly, as you can see here on that figure, directly moved over our instrumentation. Damage was around $150 US, not too large, but also not too bad for such a campaign. Large accumulation of, in that case, of only small hail, and we observed at one hail sensor actually a huge number of hailstones. We registered almost 1,400 hailstones that fell within a couple of minutes, only within 8 minutes. You can see here the spectrum at 2 different sites, and the spectrum looks like almost the same, an exponential spectrum. And we are highly interested in that spectrum because it's required. We have several projects with the insurance company, and for that we need to have better estimates of the spectrum. Okay, maximum hail size was not that large, only 2 centimeter, not really producing damage. What we see here on the left-hand side, and this is also quite interesting, is soil moisture, but sorry for the typo, soil temperature. You can see here on that day, this was the day with the hail which hit here the ground. You can see a sudden increase of the soil moisture. but you can also see a sudden decrease of the soil temperature at different levels, at least at the 5 centimeter level. And this is quite important and quite interesting because that also, the abrupt changes here also affects that the water that can infiltrate into the soil. So the abrupt change of the temperature increases the infiltration, and which means that of the high precipitation, the surface runoff is slightly reduced. People from the UFZ in Leipzig will try to quantify that. And as I told you, our idea was the LIFT project, and we did not receive any funding, but we tried to do a kind of proof of that concept, going out to do storm chasing. You see here San Amor directly within a thunderstorm, within the inflow layer of the thunderstorm. These are the sons we released there and tried to move them to get them into the updraft. You can see here 2 examples, quite interesting. Here was actually the Hailstone and the trajectory, and this was also the direction, the movement direction, and also the direction of the large-scale wind speed, and the trajectory where they're directed here into the updraft region of the Hailstone. On the right-hand side, we see the potential temperature, and interestingly, whereas we have in the speed, significant changes, the equivalent potential temperature remain almost the same, which means we actually, or at least it's an indication that we met, or that we moved or met Lagrange, kind of Lagrangian trajectory. So I have to speed up a little bit. From our aircraft observations, we were able, on one aircraft, we have implemented a new 3-dimensional scanning LiDAR, which enables us to estimate or to quantify for a larger area the wind field, which is shown here on the right-hand side. And from that, it's not yet done because it's really complicated. You see here the wind vectors. When we look very deeply, very closely here into that figure, we see also a strong wind shear. But from that, we can also, at least for that flight patterns, we can also estimate the horizontal flow convergence. So my last slide plans for Swabian Moses. Next year there will be a second campaign. Hopefully we will receive funding for LIFT, for a shorter, smaller Hail lift experiment. At least the reviews were overwhelming and very positive, but overall the costs were too high. We want to improve the linkage between observations and numerical model by data assimilation, by directly assimilating our online assimilating the data we will gain from the campaign. So for that, we have already established a collaboration with German Weather Service. Then we want also to scrutinize the reason for bad forecasts. We had several forecasts, at least last year, which were almost perfectly, but also some forecasts which completely failed. And important component, if we go more for hail, is the reporting of hail sizes by the public. Improving instruments and integrating new partners, new instrument, maybe you're interested to join, feel free to contact me at every time. So we are very open to that. And my really very last slide is a promotion for our fourth European Hail workshop, which we will have in Karlsruhe, presumably in spring 2024. And again, thank you, your North American Hail workshop. You do really a great job. Thank you for your attention.
Yeah, thank you very much, Michael. Very interesting. In the interest of time, we're going to pass on questions. So our next speaker will be Katja Friedrich, the Colorado Hail Accumulation for Thunderstorm Project, also known as CHAT.
Okay, good afternoon, good night, good morning, whatever. Okay, so I'm talking about the Colorado Hail Accumulation from Thunderstorm Project, and I gave a similar almost the same talk at the first workshop, but I thought a little bit of a refreshment is probably good for all of us. Okay, so this is a project that was initiated by the Weather Service, and you have Bernie Meyer and Nasset Riddell, Paul Schlutter, and they actually contacted me, I don't know, about 8-10 years ago, and they said, you know, we have these hail accumulating thunderstorms in Colorado, and the Weather Service is not supposed to warn them or anything. And we get then these calls from people, and they say, you know, we need to bring the snowplow out, and they said, we have no clue what's going on. Is there a way that we can use radar data to, at least for us, have an idea that some thunderstorms might accumulate to hail or not? So in the meanwhile, I had two students working on that, Bobby Wallace and Evan Kalina. Bobby's actually in the audience, thank God, so he can answer all the questions. And I'm just giving you some of the results that we collected. Okay, click to advance. Okay, so can you start the movie? Just to tell you what I'm talking about. Just start the movie. Oh, okay, maybe it's not. Okay, I think you get the picture. Okay, so this is what we're talking about. We have hailstones here that basically accumulate a foot of hail in the middle of the summer, when also Colorado doesn't have snowplows out, or people have winter tires, and then they have to get these front loaders or snowplows out to clean the road. Again, this is a big impact because it also clogs the drain, so there's a lot of flooding involved with that. And again, this is the extreme events. Okay. So then we thought, okay, we got 4 cases. We analyzed those 4 cases, and but then we wanted to go a little bit further. Now I can advance. That's good. Okay, good. So we started this chat project, and of course we gave it a good name so we can remember it. And so the goal is to study the characteristics of hail accumulating thunderstorms. And in order to do that and go beyond the 4 cases that we actually had to collect improved and more frequent hail depth report. And that is basically has been a really big challenge because hail depth is usually not reported. And people also don't really know what to report there. So the desired outcome was, first, just really identifying storms that had accumulated the hail, or maybe even develop an nowcasting algorithm, and then maybe advanced going forward saying, okay, is there a way we can maybe predict days where hail accumulating thunderstorms are occurring more, or maybe we can use numerical modeling. But this is really out in the future, and I'm not even sure whether I will be part of this. Okay, next one, please. Okay, so hail depth reports. Okay, so we started with 4 cases, and then I was telling people about this, and they said, oh, this is really a Colorado thing and not really so important. But then I was actually looking through the news, and the more we worked on that, all these news articles came up in Omaha, and God knows, but in Mexico, in South America, and it's like, and so we were collecting all those reports. And then we also started to initiate this hail depth collection project here in Colorado, and we worked with the Weather Service, so they made it part of their chaser training. We worked with CocoRAS, we worked with a lot of news outlet, and they were hammering on that concept of, okay, we also need hail depth. And so this is just a schematic here about the hail reports that we got across the country, the hail reports that we got in along the Front Range, and you see that this really varies depending on the year. We do have a hashtag, actually, hashtag deep hail. So if you go on Twitter and you have any kind of actually depth, and I'll come to this in a second, helps, just send it on Twitter, and we analyze that. We also have a verification algorithm, which is in the lower right-hand corner. Basically, again, the problem with Twitter is we get a tweet, we don't know, is that the time where the hail fell or what? And so we usually verify that with radar, and if we can't figure it out, we usually throw it out. So this is I don't know whether it's rigorous, but we have a QC algorithm on that. So that usually helped. This project is really funny because it's just so basic, or we're really starting from zero. So I was trying to get NSF funding for that. And then of course, everything came back and said, oh, where are your hail depth report? I said, yeah, thank you. It's a chicken and egg problem, isn't it? Next slide, please. I got funding at the end. Okay, so we are trying, So we're trying to develop first thing an hail depth accumulation algorithm so that we at least have a starting point. And we're basically using this on the idea of precipitation depth. On the lower right-hand corner is an equation. That's the only equation I have in the talk, so no worries. So you see we have ice water content. We're using Andy's algorithm where we can relate reflectivity to ice water content. We need to have fall velocity. We're using MASH for that. I know there's a lot of like uncertainties in those. We need hail density. And then what we did, we used basically 60 hail depth reports that we had. And we were training an algorithm with, I think, 40. And then we were trying to verify those with the other 20. And then this little epsilon is basically our nudging factor, something that we learned from modelers. Okay, so get the reports and the accumulation close by. So we're using this nudging factor. We think this actually works pretty well. We don't really know how it works in other areas because we probably have more melting and some things might be a little bit different. And again, there's uncertainty of the hail, diameter, fall velocity, and then density, of course. Okay, so here are some examples from 4 different hailstorms. These were really deep hail accumulation storms, and where you see where we have reports. Next slide, please. Okay, so we just start doing this for the Front Range, and while we were doing that, and again, the Weather Service was interested in seeing the results, but didn't really want to put in a lot of effort. But anyway, we got all these requests from the Weather Services. Oh, can you run the algorithm over the summer? So we've been running this algorithm for, I don't know, 5 years. Finally, actually, the Weather Service picked it up, and hopefully they will implement this. But you see, we're running it basically for all the radars that you see in the image. We also actually now running it for New Mexico. So again, if you just need to shoot me an email, and we can just include another radar. So if you go to clouds.colorado.edu deep hail, you can see there are, right now you can't see anything because it's not the season, but usually we start in May. And then if we have an event, you can click and you can actually see the images and the entire movies. We're also starting to develop a archive. So actually you can look at individual pictures so you can see what are the hail accumulation days. And then what you get is basically an image on the right, where you see the radar in the center, and then you have hail accumulation, and then we're also plotting other stuff like vertically integrated ice and these hail size reports. Okay, next one, please. Okay, so now we started to look a little bit more into and trying to do, because we have this rich data set, I'm trying to do a little bit more research on that. So the first thing we did is, okay, what is do we have more supercells that producing more hail, or is it the non-supercell storms? And here you can see this. Actually, I don't need to turn around. You can see this here, that again, supercells have the majority, but again, we get a lot from non-supercell, and that's pretty important because along the Front Range, thunderstorms often are not really well organized. We have this mesh of stuff. Okay, next one, please. Okay, so we also looked at the environmental conditions and storm morphology. Again, you would think, okay, these storms, they slow down and then they dump the hail and then they speed up. It's not always the case here in the middle. Okay, I thought I had it down, but no, I don't. You see mean storm speed, 6 meters per second, 8 meters per second. Sometimes we have pretty fast storms. So it's not really a good indication whether you will have a hail accumulating thunderstorm. The interesting part is also you think, oh, maybe these are the hailstorms that have small hail sizes. They're not necessarily warned, but that's not the case. We also have storms that are warned. We have also tornado warnings in these storms, and they still accumulate a lot of hail. So there's really, again, not a really unambiguous result on that. Next slide, please. Okay, so then we looked at the environmental conditions. Again, everything that you need to do that. We're trying to do this a little bit in more depth, not just using the soundings, because again, the soundings are not really ideal. We were trying to use numerical model output to get at the storm environments. See, maybe that's what determines the storm accumulation. We couldn't really get a really unambiguous result on that as well. Next one, please. Okay, so We also looked at the dual polarization data. So again, these are 4 storms. On the left, you see radar reflectivity, which is a plane view, and then differential reflectivity. Again, the white crosses indicate the areas where we have a accumulation, or where we have a report. Again, that's where we have the highest reflectivity. CDR is interesting because we have a lot of 3-body scattering. So you see this dip in CDR. Again, this is in some of the more severe storms we see that, not in all the storms. So differential reflectivity could be an indicator, but operation, and again, we're just working with operational data. It's sometimes really tricky because you saw we have a ring. We usually use just the data in the 50-kilometer range. We have a lot of problems with attenuation, and so it's not really always easy to use the radar data. Next one, please. So then we were moving into, okay, is there a way we can do some forecasting or nowcasting that we can maybe say a hail accumulation is imminent? So what we did, these are vertical cross sections. On the x-axis you have time, on the y-axis is height. The blue lines are the different temperature lines. And again, on the left you have reflectivity, maximum reflectivity. On the right side you have minimum differential reflectivity because of the 3-body scattering. We get this minimum. And then these red lines that you see occasionally, these are the times where we have a hail report. And you can see, again, we have a deep column of reflectivity, usually when we have the hail report. You can see in the minimum differential reflectivity, someone showed it this morning, the same thing. You see the signal higher up, and then basically, or the minimum higher up, and then it's proceeding down, and that's basically when we see the hail accumulation report. Next slide, please. Okay, so we were testing various parameters. The best one that we indicated is vertically integrated ice. That we actually move, and again, it's not a surprise as it should be, that really works well with when we see hail accumulation. So on the top, you see areas of hail accumulations where we also have reports, and on the bottom, we have vertically integrated ice, and this is over an entire span of a storm life cycle. And what's also interesting, you see these storms, sometimes they dump hail and then they move on and then dump hail again. So it's really not a continuous swath. But you see on the bottom, you see that when the vertical integrated ice goes up, that's usually when we have hail accumulation. Okay, so then we looked in the plane view. We also looked in this in a time-space continuum. Next slide, please. Oh, no, before we do that. No, go ahead. Oh, can you go back? It's too many cooks here. Then one back. Yeah, this one. Okay. So again, we have these 60 cases. We did these scatter plots for various variables. Again, vertical integrated ice is really the best predictor. So all these different dots are different cases. On the y-axis, you see the accumulation. On the x-axis, you see vertically integrated ice. The colors indicate the accumulation, and the size of these bubbles indicate storm speed. So again, if you look at this big cluster 3, you can see the storms that have a lot of vertical integrated ice produce a lot of hail accumulation at the surface. What is interesting, you see, if they are faster, when the bubble is bigger, they need to have more ice in order to accumulate. If they are slower, they don't need to have as much ice, and they have more time to accumulate. I'm glad the physics works here. Okay, so then the interesting part is also this cluster 2, where you have a great variety of accumulation sizes and also storm speeds. Again, they all have more or less the same vertical integrated ice. Again, here you can see the slower storms don't need to have as much, and then ice, and if they have the same ice as the faster storms, you see that they're actually accumulating more. And then we have this other cluster 1, which is also doesn't really have a lot of ice. So when I submitted the proposal to NSF, again, it came back, I think, twice. And so then one comment was, yeah, what about your null hypothesis? What about your null cases? So I said, okay, how do we get information about no hail accumulation from thunderstorm? How do we get this out in the public? Okay, so what we did is we basically basically have three categories. We have these really deep hailstorms, which are affecting where you need to have a snowplow. We have hail accumulation, which is basically the cluster 2, where we have accumulation, but cars can still drive through. It's not really impactful. And then we have storms where we have individual hailstones on the ground, and that's basically our null cases, because we were struggling with the null hypothesis and actually getting this out to the public. Okay, next slide. Okay, so now I'm coming to because again, the idea was building something that gives us the present state, but also maybe we can do something like with the nowcasting. Okay, so what you see here is these blue lines. That's basically the time where our hydrometeor identification or our algorithm identifies hail accumulation at the surface. And then we are using various parameters. The blue line is storm speed. Red is accumulation rate. Then we also looked at lightning parameters like flash rate or flash extent density, and then we're looking at the outpaced for our vertically integrated ice. So you can see these storms sometimes slow down, and that's when the hail accumulation goes up. Lightning really didn't give us a good indication. Sometimes it did, sometimes it didn't, so it was not really reliable. But again, the vertically integrated ice usually is a good, as vertically integrated ice goes up, then the hail accumulation goes up shortly after. Next slide. Okay, so why is that so difficult? Okay, so most of the times what we have again in the front range is the storm and storm interaction. So here's just an example where you see a time series from the upper left-hand corner to the lower right-hand corner, and you see this outflow boundary. I wish I could. Okay, so this dotted red line on the upper panel, this is the outflow boundary. And then if you look at the end of the line, you see a black cross sign. That's where we have the hail accumulation. And so in the next thing you see, okay, this is this outflow boundary. We have connection initiation very close by to where we have the hail accumulation. Next one down there, reflectivity increased. And then at 2040, we see the hail accumulation. And here you see between 26 and 40, 15 minutes. Okay, 26, there was nothing. And then 15 minutes, we have hail accumulation, which was significant on that day. So you see how difficult it is. So again, modeling might be not even the solution for that. Okay, last slide. Okay, so we haven't really made a lot of progress. So we analyzed most of the observational data. We are waiting for ice chip because we need to have more in-depth data. We also need to have more data about the hail swath, about variation in the depth, and then also starting to do some numerical modeling and sensitivity. And so, but again, I'm trying to push everyone to rethink hail reporting and add hail depth. We were trying to get it into MPing. It's a very slow and painful process. We are trying, again, the Twitter you actually works really well. We have people actually send us pictures instead of reporting hail depth. They're sending us picture, and we are trying to figure out what the hail depth is. But again, hail depth, again, size distribution would be nice. And then hail swath. Again, there were some ideas with using satellites. One thing that we've been using is we have pilot reports. So we have some pilots on this entire network, and they're basically sending us pictures, which is really helpful when they land or take off. So the nowcasting algorithm works decent well. Again, we need to have some more verification data to really nail it down. And so we were looking at a lot of dual polarization parameters, which is difficult if you're working with operational radars. Vertically integrated ice, again, is our best indicator. And then storm stream, yeah, and along the front range, we don't have a lot of melting is not a big issue, but Matt wrote a paper on melting in the storm, hail accumulating thunderstorms in Texas. That's probably a more issue. And then, yeah, I think we can maybe dig down a little bit more in the lightning data, although there was not a lot of skill that we found. Thank you.
Thank you, Katja. In the interest of time, we're going to move on. Sorry. So our next speaker will be Jerome Kopp. Observations from automated hail sensors in Switzerland. Estimations of the hail size distribution and comparison with radar-based and crowdsourced data.
Okay.
Oh, yes, this one's remote. Go ahead. You're here? Yeah.
Okay, so good afternoon, everyone. Yeah, my name is Jerome Kopp. I'm a PhD student from the University of Bern in Switzerland. And today I would like to talk about thank you, the first results we have from the observation of the hail sensor network that we have set up in Switzerland. I wasn't supposed to do that. Did you advance? Okay, sorry. So yeah, this is the same sensor that Michael Kunz introduced in his talk before, and I'm to say I was very impressed by the number of impacts he got on the sensor. So we've never had like 1,400 impacts on a single sensor. We mainly like got 400, which was like the maximum. And so in the beginning, we were very excited with this new data of the sensor, and I wanted to show you estimates of the hail size distribution, the comparison with crowdsourced data and with radar data, as mentioned by Andrew. But it turns out that hail sensors are a new measuring device, and that we have, it's the first time they're exploited in the field in such a large scale during in such a long time. So we encounter some difficulties, some potential issues, and we have to solve before really using the sensor data to their full potential. So we will also discuss some of this limitation today. So if I want to advance, it's working, awesome. So before talking about hail sensor, I wanted to introduce Switzerland to you. So because maybe you're not familiar with this country, so it's located in the center of Europe. And I'm just showing also on the right, a comparison between Switzerland and Colorado. So we are talking about a very small country. It worked before, but not now. Maybe I can ask you to do the next slide thing. Thank you. So if we now have a closer look at Switzerland and the yearly frequency, the hail yearly frequency based on radar data, we can see that we have regions with the largest expected hail frequency. We have on average between 3 and 4 hail days. Those regions are located in the Alpine foothills, so close to the Alpine Ridge, which cross Switzerland. And we have also another region, it's called the Jura. It's not far from the Swabian Jura mentioned by Michael before. So this is where maybe next slide. Thank you. So this is where we decided to install the sensor in those 3 hail-prone regions. So we have 80 sensors, and the network is relatively recent, as you can see. So sensor being operational since 2 to 4 years. And yeah, next, please. So those sensors are part of a project called in German Schweizer Hagelmessnetz, or the Swiss Hail Network in English. And so the objective of the project is to record the impact or kinetic energy, the size distribution, and the precise time of hail. It's a public-private partnership with an insurance company, several industrial partners, the National Weather Service of Switzerland, Meteo Suisse. And here you can see 3 pictures of the hail sensor. So basically it's a macrolon, which is a thermoplastic disc, which starts vibrating when it is hit by a hailstones, upon the impact by hailstones. And those oscillations, they are recorded by a highly sensitive microphone. Next, please. And so what does a sensor actually measure? So first there is like an electric signal coming from the sensor, which is converted to hail kinetic energy to a calibration process. And then from this kinetic energy, we can use different formula to compute the hailstone diameter. So a key step in the calibration is to do this calibration is that we record impacts from 5 different kinetic energies, and we do this linear fits that is shown here on the slides on a log scale. And we relate this output signal to the kinetic energy. We use that. For that, we use masses, known masses with known velocities. So the calibration is done in it's done in the laboratory condition before the delivery by the manufacturer. And we have to do it, to repeat it once a year because the sensors are exposed to weather conditions, such as radiation, temperature, rain, hail, of course, etc. There is also an important parameter, which is there is a minimum signal threshold which is set by the manufacturer to avoid measuring anything small or smaller than 5 millimeter according to the initial calibration, such as large raindrops, for example. And here you can also see that a sensor have to measure like several decades or power of tens energy because like a 5 millimeter hailstones has a 0.003 joule energy, and a 3 centimeter hailstone has like 1,000 times more. Next, please. Next again, so I can, next please. Yeah, thanks. So I know I can show you some preliminary results. First, we can estimate the local duration of a hailstorm. For that, we have to define the so-called hail events. And we do that by defining a series of n consecutive impacts over an individual sensor. And each impact is separated by no more a certain time interval. So here we choose 2 minutes as a time interval, so to eliminate some artifacts such as isolated impacts happening before and after the core of the event. And we choose event with at least 50 impact to focus on significant hail events. I found those values being like a good compromise through empirical visualization, but of course other values could be tested. So we end up with 66 events, and we can see that most of them last no more than 5-6 minutes. So which means that locally hail doesn't last that very long on the average. Next, please. Another thing we could do is that we can look at the distribution over time of single hailstone impacts. So again, if we consider those 66 events that we have, we end up with around 9,000 hailstone impacts. And here the x-axis shows the time elapsed since the start of the event, and the y-axis shows the number of impacts in each beam. So what we can see from this distribution is that the highest impact concentration is reached between 1 minute and 1 minute and 45 seconds after the start of the event. Next, please. We can then add the estimation of the hailstone diameter to the previous distribution. So here again, the x-axis still represents the time since the event began, and now the y-axis as a diameter information. So here we can see that the highest density is shown in dark blue, and it's for hailstone with a diameter between 5 millimeter and 10 millimeter, so relatively small hailstones. We also had a kernel density estimation, the red contours. We can also add information of the time when the largest hailstone was observed for each of the 66 events, and this is represented by the green dots. So here again, we see that we don't have measured like very large hailstones. The largest hailstones was about 3 centimeters. Next slide, please. So finally, I can show you the distribution of the kinetic energy of, again, individual hailstones. the kinetic energy is the most direct measurement of the sensor, while, for example, in other instruments, it is derived with some assumptions. So this distribution could be compared to those obtained from hail pads, for example, or other instruments, and see how far we get. Yeah, next slide, please. So we can now just summarize the advantages of the sensor that we have seen so far. So they record the exact timing of a hailstone impact, which is something not many devices can do. They allow for the estimation of a hail event duration, of the density, diameter as a function of the hail event time. They offer a direct measure of the kinetic energy, and this is useful because we can derive diameters of hailstone based on different models or assumptions. They provide live measurements. They are connected, wireless, so they can we have information. I mean, a few minutes after the hailstone, I see the sensor. However, we are still exploring. They'll be reviewing the field, and we're also actively comparing our findings with APAC studies. And now I would like to discuss two of the issues that we have seen. So the first is that we have to recalibrate the sensor every year in the field. And this, plus the fact that there is the threshold fixed by the manufacturer, means that sometimes we have truncated distribution of in the low end energy. I will show an example after. And also the sensor can be subject to saturation. There is a theoretical practical limits of 15 impacts per second. Next, please. So this is the calibration and threshold issue. So here we have an event in Ticino, an hail district, which hits several sensor, closely located sensor within minutes. The calibration was done 1 month before for all the sensors, so we can suppose that we are correctly calibrated. But what we can see, like in the red circle, is that we have a minimum diameter or kinetic energy that varies between 5.2 millimeter to 7.4 millimeter. And there is a clear threshold below which the sensor doesn't observe anything. So we can, of course, think that we won't measure the exact same distribution at each sensor because they are not exactly at the same place in the hail streak. But yeah, having this clear threshold is really a manifestation of the threshold and the change of calibration. Next, please. Thank you. And now if we look at the hail size distribution, this is how we discovered that by analyzing the hail size distribution. So we compared our estimate from the 66 events, which are represented by the colored lines, and the black line show composites, to a simulation based on the parameters derived from quite a long time ago by Federer and Waldvogel from an experiment in Switzerland involving a radar, a combination of radar and hail pads. We see that the N0, the parameter of the hail size distribution is one of magnitude below what we should expect. Of course, there are many possible explanations for that. So first, this might not be the same storm environment. The theoretical estimates come with uncertainties. There is the impact of melting, also because we are looking here at hail size distribution aloft. But still, we cannot rule out that the sensor is maybe saturated. So we have to explore that. Next slide, please. And so as a conclusion, the first step, so we are doing a comparison with existing Alpine studies. So we have been in contact with Agostino Monzato, which was mentioned as a co-author of the presentation. So because there are many hail pad studies available, but they don't give all the details of the hail pad selection. So here it's really very useful for us to get really the details of how they have selected the hail pad, why they have done that, the really detailed process. For the saturation, we would like to develop a test protocol to assess the extent or the presence of saturation to see if this is present or not, and potentially derive the size intensity dependent correction factor that we could apply to the data. For the issue involving the calibration and the thresholds, we already work with bin data. So we use 5mm bins. We never look at precise diameter from the sensor to account for this uncertainty. And then we would like to recompute the kinetic energy using the manufacturer initial calibration, which is coherent with the threshold set initially, to see what we get. So yeah, we are still exploring this new and provising hail measuring device, but we need more time to get really understand how it works, the limitations, and to use the data to its full potential to do really a number comparison. And yeah, I'm also the sensor are new, but I'm also new in the hail community. So yeah, your feedback is most welcome. Thank you.
Thank you, Jerome. We have time for one question. I have a question. Is this called the Hailsense instrument?
Yeah, it's the Hailsense.
Yeah. One thing I looked at with respect to that instrument is that it's calibrated to go from kinetic energy to diameter using ice spheres, solid ice spheres. So that calibration probably needs to be revised a little bit.
Yeah, I don't know a lot about, because I haven't taken part in the development of the sensor, but they did calibrate with ice spheres, and they even use ice spheres made from water and other made from orange juice to account for different in the density. But this is a very expensive process.
I know it is.
So yeah, this is not easy to do.
Well, direct any questions you might have, David. Thank you, Jerome.
Thank you.
Okay, the next talk is by Jim Bresch, high-resolution WRF simulations of coordinated observations in Northeast Colorado hailstones, hail cases.
All right, thanks, Andy. I'm Jim Bresch. I work with the WRF and impasse modeling team at M-Cubed. And I mainly work with real data, WRF simulations, as opposed to some of the simulations shown yesterday, which are idealized. I work with sub-idealized modeling cases. And we have a self-funded project here with NCAR looking at Northeast Colorado hail in last year. Our objective was to test new observation platforms, modeling tools, and strategies for a future larger hail experiment. And lead PI was Andy, along with Adriana Bailey, who investigates water isotopes, and myself, who does the modeling. We also had several co-investigators who brought their instruments, and many collaborators, many of them volunteering their time for collecting hail and investigating the storms from last year. All right, okay, next, please. So why another hail measurement project? Well, on the left here is shown the CP2 radar located in Grover during the ENRI project 50 years ago in north central Colorado. And on the right is the CSU Chivo radar in the Argentina, a recent experiment. So there's been 50 years of technological progress, and that also can be shown in the difference in the modeling. Back in the 1970s, there was a limited area 5-mesh model with a 190.5 kilometer grid. And now we have a 3-kilometer HER model that's run every hour for convective and aviation forecasting. So there's been a lot of progress. And so there are still remaining questions that we can answer with hail. Next, please. Now, this was a animation. I don't know if this video will show up or not. Anyway, this is just a treat for those of you who stick around until 5 o'clock looking at hail falling. This is actually taken from my neighborhood. This video shows my roof getting destroyed. And maybe 75% of the houses in my neighborhood needed to have their roof replaced. The roofing companies know exactly where hail falls. In this case, the hail swath was 1 kilometer wide by 2 kilometers long. So it's very small, and a wide spectrum of hail fell. So next, please. This is a photograph of the hail right after it occurred. And what I see as a storm chaser and as a Colorado gardener is I see a wide spectrum of hail here. Many pea-sized hail, marbles, there are some golf balls, clear hail, there's cloudy hail, spiked hail, and smooth spherical hail. So from a modeling standpoint, we need to decide what is it we want to show to characterize a hail fall. Even though we have all this different kind of hail, some of it caused damage, some of it didn't. So, and Katja mentioned as well, so how much falls? And if we have all this liquid water falling as tiny pea sizes, it'll accumulate clogged storm drains and such. So this is actually a very interesting problem, and I think it's a very difficult problem as well. Next, please. So as I mentioned, our CONCH 21 objectives are to test new observing systems, combine our measurements with high resolution modeling using WRF ARW to investigate the storms, and to develop tools and strategies that may be used in planning and conducting a larger future field experiment. So the experiment was scheduled for 4 June to 3 July 2021 over Northeast Colorado. Next, please. I'll just talk about some of the observing systems. We had mobile ground teams that would be used to deploy 3 sentinel tile instruments in the path of the hailstorm. These are the folks that are in the hallway showing their instrument. They donated 3 tile sensors, and these teams would deploy them. The idea was to deploy them in front of this hailstorm, and then collect stones for sectioning and isotopic analysis, and attempt to measure the hail swath, which is kind of difficult unless we have a good road network. 3 water vapor analyzers were located over Northeast Colorado, and that measures the water vapor isotopes, and that could be compared with the hailstones to determine where the hail grew and the characteristics of the stones. Next, please. One major component of the experiment was the Raven, the University of Colorado Raven, which is the UAV. This aircraft has been used to sample supercells in the past, just taking in situ measurements ahead of the storm. The goal here was to outfit the Raven with a canister that releases chaff in the updraft region of the hailstorm. The chaff is shown in the right hand photograph. We use various sizes of chaff, and basically it's 2 soda cans in size, and then they're able to release it once we get the aircraft ahead of the storm. This is a very challenging issue for forecasting because we need to put the aircraft team ahead of the updraft, ahead of the hailstorm, have time for the plane to launch and then get to the altitude, release the chaff, come back, be recovered, and then have the team run away before it gets engulfed by the hail shaft. And the idea then is to have this chaff be observed by radar so we can track the motions of the air within the thunderstorm. Next, please. Here's a map of the study region over Northeast Colorado. It's very similar to the ENRI 50 years ago. The Raven flight operations were in the western and eastern Pawnee National Grasslands. That's where they had their operation certificate. Unfortunately, we're close to a very major airport here, so DIA restricts the altitudes with which the UAV can fly. The western PNG was lower altitude restriction than in the eastern PNG. The Chivo radar is located east of Fort Collins. They're in purple on the left side of the map. That was able to observe some of the storms over the Will County region, as well as perhaps the chaff that we release. And the water vapor analyzers were located at CU Boulder, co-located with the chill site near the Greeley Airport. That's where the NCAR analyzer was positioned. And there's another analyzer with the Neon site near Sterling. Next, please. And here's the obligatory WRF configuration description. I ran WRF version 4.3 using a nested domains 15, 3, and 1, using a WRF double moment 7 class microphysics. One of those classes is a Hail. I ran Hailcast on the YSU PBL and the RTMG radiation. This configuration is not completely arbitrary. We are running this kind of configuration operationally in the Taiwan area. Their weather service there is running that operationally. We have lots of experience doing this. So all we did was translate this operational system to Colorado. Now the objectives were to study the overall WRF performance in predicting these high plains storm environment, examined the behavior of hailcast as well as the explicit microphysics. And there were a plethora of microphysics schemes in WRF which can be used. The one I used was WDM7 for what I'll show today, but there's the Ted's scheme that he showed yesterday. The Thompson and P3 also talked about yesterday. We have even newer versions than what was described here. So these schemes are being constantly updated, and hopefully they can do a decent job with hail. Next, please. Now, the experiment was held in June of 2021, and May was a cool and wet month. We had a typical severe weather in Northeast Colorado. As soon as the calendar turned over to June, this is what we got. A giant ridge over Colorado, which ushered in a drought that still extends to this day. So we had a significant pressure deficit, precipitation deficit for this time beginning in June. And the operative word for Conch 21 period was marginal, or MRGL we see in the SPC outlooks. Basically, the Cape and the shear was marginal for severe hail every day. And also included in that marginal forecast is a possibility of triggering or initiating thunderstorms. So even if we did have decent Cape and decent shear, the question of whether we had enough forcing either surface or aloft to initiate storms, which is important. So we had a very difficult time getting cases to observe last year. Next, please. The synaptic conditions led to a limited number of small hail events. We had nothing greater than 2 inches. And so from a forecast standpoint, it was successful. We didn't miss any cases, but that's because there weren't any. The first case was in June, 6th of June, and there was small hail in the Denver area, but no convection was predicted. The models failed on that day, and also as well as the weather service forecast. We did a chaff test release under clear sky conditions. A Cheyenne storm, which is just outside of our observing region. There were no storms in Colorado. And we had 2 cases, one in Weld County that we observed and collected hail. One on 24th June when no hail was observed, and the 25th of June was hail at NCAR. Next, please. And if we can't get to the storms, we'll just have to wait for the storms to come to us. So the Sentinel tile instruments here, there's 3 of them located in the Foothills Lab parking lot. The Foothills Lab is just on the other side of the highway here, about a quarter mile to the northeast of this building. The instruments were set up and deployed in the parking lot, and then they were testing to see if the cell signal was working. And right at that moment, a hailstorm came over, and that got excellent data from that system. We measured up to 1 inch of hail in the area. Most was around 1/2 an inch. Unfortunately, this hail is too small to section. Charlie Knight was going to section some of these hailstones, but unfortunately, they're just too small to work with. Next, please. So here's the forecast using the 1 kilometer WRF, just centered on Boulder County, showing Western Weld County. On the left panel is the forecast initialized with the HER, 3 kilometers, and on the 12 kilometer NAM on the right. And we see very different rainfall forecasts for 2 p.m., which is when the hail was falling. We found that the HER forecasts were extremely dry for the entire month of June, and this led to poor initiation of convection in WRF as well as in the HER model itself. So the HER is too dry. In general, it was too dry over the mountains, and that dry air spread over the eastern plains. And so the HER was not suitable for using as initiation for the WRF forecast. This is what is called a CAM, a convective allowing model. I kind of call it the convective disallowing model because we didn't get any there. And the NAM forecast was pretty decent. Let's go to the next one. And we can see the radar showed the Boulder storm here, just located at 2 p.m. right over. It's similar to what the NAM WRF showed. So the HER was just too dry and was not acceptable for forecasting. Next, please. Here's the 1 hour rainfall with some SPC's hail reports and the terrain as a base figure, showing the storm developing over Boulder and then moving southeastward. There are 2 green dots there you can see. One of them is an SPC report a little to the north, and one is the green dot I added for a 1 inch report in our neighborhood here. So a lot of times the SPC reports will not be available. So the lack of an SPC report does not mean a lack of a severe hail. It just means there is no report. So there should be trying to encourage getting better reports so that we can get an idea of where hail actually fell. Next, please. Here's the hailcast prediction for 20 UTC. This is showing the 1 hour hailcast. And I was pleased to see this because the hailcast was not very far off with the max diameter of the hail. It's showing about 24, 25 millimeters. The position is slightly south of where it was observed, but there's actually a very good forecast. And so the hailcast does seem to do well with getting the size, even for these marginal cases. I think these marginal cases can be important for as either hail accumulation or for even damaging with about 1 inch size rather than just the focusing on the very large hail. Okay, next please. Here's this example from the 10 June clear sky case in which we did a test of the chaff release. We released chaff from the Western PNG region as well as from the Eastern PNG region. And here's this is your plots from 9 minutes apart from the Cheyenne NexRad. And what appears to be the chaff that appears within the base reflectivity and moves to the northwest at the time and location of the chaff release. It's very difficult to see. The amount of chaff is released is very small. And in this case was being lofted in the boundary layer and then directed toward the north. And that little circle there shows where the center of the chaff appears to be as it moves to the north. There was some rainfall to the south, just to the east of the Denver metro area. That was mainly virga and moving toward the northeast. And next, please. And if this will work, this is showing the animation of these same radar images. The arrow points to where the chaff was released, and there's a coherent echo you see in green moving toward the northwest that should not be associated with any biologics that we know of, or it should be the actual chaff that we're seeing. So I think it's very encouraging that we were able to see that with the NexRad. The question I have from this is, can such a small amount of chaff actually be traceable within the convective storm environment? So I think that we still need to do some more testing to make sure that this would be a useful observing system for a hail project. All right, next, please. One thing I added to the WRF system here was a way to inject chaff as a tracer into the model and then plot that as a function of time. Here we're looking at the 1 kilometer forecast where I released a tracer at the same location and altitude and time as the Raven chaff release. Although it looks pretty serious with the red contours there, it is actually very, very dilute and very small amounts of tracer. And that moves toward the northeast in the WRF simulation. So it indicates that the model has a little too strong westerly component to the winds, even though there were no rain systems in this. But I think it's very encouraging. We have a tool now to allow us to put tracers within the modeling system and then use that to investigate the air motion within the forecast. Okay, next, please. Now, I want to show this as well. If with the model, we can relocate to a different location, even though the field experiment can't. So I moved the domain into northern Montana. This is a supercell case that happened in 9 June. The IBHS team was there to sample the hail almost near the Canadian border. And I initialized this at 18 UTC using the NAMS forecast and the 1 kilometer modeling system. Next, please. This is showing the 1 hour rainfall and SPC hail reports on the terrain. I don't know if these SPC reports are actually from the IBHS team or not, but they're a few reports, 2 to 3 inches and some greater than 3 inches, around 2 UTC. The model does a very good job of tracking that supercell as it moves toward the east across northern Montana. Next, please. Here's just this supercell structure that the 1 kilometer simulation, real data simulation was able to get, showing the mesocyclone and the hail microphysical field, just showing the reasonable evolution of the supercell structures. Next, please. Here's the hailcast forecast for that same storm. The placement of the hail was excellent, although forecast sizes were slightly smaller than the few observations. But we can see that there's a very difference in the hailcast producing large hail and for the strong supercell case and for producing small predicted hail for the weak cases over Colorado. All right, next, please. I can also introduce a tracer in the boundary layer ahead of the advancing supercell. I did that here at 0.1 UTC. The reflectivity shown in purple on the left is a cross-section, an east-west cross-section with height, showing the progression of the supercell toward the position where the hail was reported. And by 0210 UTC, the beginning of the tracer was being ingested into the updraft. And if we go to the next slide, we can see that within 10 minutes, that tracer had been advected all the way to the anvil. So it was being lifted in the updraft, going into the page here and wrapping around the mesocyclone and being lifted into the anvil. It's just showing the circulation of how that boundary layer air is being rapidly ingested into the storm. This is encouraging because we can release chaff in that area ahead of the supercell and have it go into the mesocyclone and being lifted. Whether we can release enough chaff and have it be tracked by radar is another question that we need to answer. And then we can see the structure by 0230 UTC. All right, it's possible that large amounts of chaff may be needed to have useful tracers within the storms. Okay, next, please. Okay, to summarize, even with marginal conditions during CONS 21, we were able to collect data for a limited number of events. All the hail was 1 inch or less. The modeling of these cases show that the herd was often much too dry over the region, resulting in poor forecasts of the PBL and convective evolution. However, the field experiments may benefit from having our own customized model runs that are optimized for the phenomenon we're looking for, rather than having the HER, which is kind of a general model looking for wintertime cases and other summertime events, but we can just have our own customized model runs for forecasting. And so now we have some model tools that allow us to track chaff releases and be available to the community. And the hailcast performance was good in the cases that I've looked at so far. All right, thank you very much.
Thank you very much, Jim. Very nice talk. One question.
Okay.
No, go ahead. Anyone has a question? Okay. Thanks very much. And the final talk will be the Becky Adams-Celine will be talking about a possible future experiment. She's co-organizer of this workshop.
Thank you, Andy. All right, thanks for staying. I promise to make it worth your while. This is going to be exciting. I was accused of having a depressing talk yesterday, so this one's going to be optimistic. All right, so the ICE chip, the in situ collaborative experiment for the collection of hail in the plains. What is it and who's involved? I'll answer the who's involved question first, because there were a whole bunch of people working together to put this proposal. So yeah, the group of the who is important here. Yeah, so myself, and then I've got 3 co-PIs, John Allen, Victor Gensini, and Andy, of course. The science steering committee listed there. That also includes folks like Brian Argro, Jeff French, Ian, Karen Kosaba, Matt, really great people who, again, have done a lot of work. And then we have a big list of collaborators. There's a lot of exciting possibilities here. Yeah, all these folks have contributed to making this what it is. All right, so that's the who is it. Who's involved. A very quick summary of what it is this would be a US-focused field campaign. focused on hail, and we have proposed it to NSF, but it is not yet approved. It's currently under review. So I'm going to spend a little bit more time motivating this in the hopes that there's some potential reviewers out there who are listening, and then I'll get into some of the details towards the end. All right, so why hail? Some of this you'll probably know, but maybe I'll introduce you to a few more potential reasons outside your immediate area. Okay, this one I definitely don't need to belabor here, but yeah, we all know hail's expensive. The one point that I did want to bring up that came up during our prep period, there was actually a hailstorm that went through Laughlin Air Force Base, Texas. And so this was a single missed hail forecast, and it cost $63 million. Oh, my mistake. It was only 46 million. They were able to bring that down due to some fancy repairs. But yeah, that's a single forecast, $46 million. That'd pay for a lot of field campaigns. Just point that out. Okay, hail is global. Again, I don't really need to belabor this point because there's people from all over the globe listening in right now and have presented. But there are billion-dollar hail events that happen in Australia. They happen in Canada. Here's in the upper left. Excuse me, upper right. Upper right. That's hail losses in Europe. It's increasing too. We hit the 20 billion mark here in the US. And this is a satellite hail climatology in the lower right that Sarah talked about on the first day. Hail's everywhere. Okay, harkening back to my talk yesterday, hail forecasting is hard. It is particularly hard for large hail. This is a study by Scott Blair on the left, looking at the SPC watches for giant hail, looking at what they said in their watch and what actually happened. You can see quite a difference. And same thing for warnings for giant hail. Again, that's a big difference. We do not know how to forecast large hail. And before I pick on forecasters too much, modelers can't do it either. And I made this point yesterday, but here on the left is some machine learning techniques. In the middle is hailcast and some things like updraft helicity, column integrated grapple, all your usual suspects. On the right is, well, it's just a comparison of WRF hailcast and FE3 hailcast. But the point being, 2-inch hail, we can't do it. To make things even worse. Not only can we not do it, we don't even know really that we can't do it because we can't verify it. If we try to use some sort of public hail reports, you're dependent on the public actually being there. So here's that kind of famous almost figure from John Allen's work, where you can see that hail reports are clustered along roads and in cities. Hail does not follow those, but that's just all that we know where it's happening. And of course, radar-based estimates are much better in terms of you don't have to deal with population biases, but man, they don't distinguish large hail well. This is from Murillo and Homeyer in 2019. The red curve is hail that they had reports between 1 and 2 inches. The green curve is hail where they had reports above 2 inches. And then the x-axis there is what mesh value they had. And you can see that those two practically overlap. Kyle's actually done a lot of work on this with the shave data set. Here again, hail diameter as observed via shave, and on the y-axis is mesh. Not a great relationship there. And this is further complicated by the fact that the radar reflectivity and size relationship is not great when you start getting up to these large sizes. And I'll let Matt go much more into that tomorrow, but rest assured that there's a lot of potential issues there, especially if you're trying to get any sort of larger hail size or anything beyond size for that matter. All right, harkening back to Yuju Lin's talk yesterday, there's a whole bunch of hail characteristics that we just don't know. This is an image from Shed et al. Using a number of IBHS 3D scans of hailstones. Obviously, there are a whole bunch of different shapes. Why do these different shapes form? What kind of environments make these shapes? Are these shapes found in every hailstorm or only in some of them? Who knows? There's also the problem that we do a lot of assuming about smooth, spherical, and non-tumbling hailstones, microphysics parameterizations, trajectory models, radar scattering relationships, public hail reporting. These all assume smooth spheres, and hail is not a smooth sphere. I borrowed this image from Yuju's talk actually yesterday, and these are just showing the different hail size distributions produced if you just change some of those relationships. There's all sorts of problems here, and we just don't know. The generating processes for producing hail, we don't really understand those either. Here on the left is just a quick animation through all the different trajectory cluster pathways that I identified in one supercell. There's a whole bunch of ways the hail can form. We don't know why. On the right is some work of Matt's looking at time-varying max hail size from a simulated supercell. Part of the reason why we have such trouble understanding generating processes is that a lot of our previous, actually all of our previous radar data-driven hail trajectory studies had to assume a steady state storm. They just simply didn't have the wind field or the environmental information for the storm to evolve in time. So we're basing a lot of our assumptions on us assuming a storm. The updraft doesn't vary at all. It's probably not realistic. And yeah, Matt's study would say, no, it's absolutely not realistic. Let's see here. Oh, you mind hitting the next slide for me? Or maybe I'm... Oh, I think I figured out how to push the button now, and okay, here we go. All right, so then we get to the problem of, all right, so not only are our hail size observations not great, if you want an observation of anything other than hail size, good luck. If you want, things like concentration, aerial coverage, hail volume, impact velocity, density, angle of impact, wind effects. I mean, Ian and the IBHS team cannot be everywhere. And things like the total width of the hail swath, the size distribution, this type of information, it's just not out there. Jordan's talk looking at using satellite data from vegetation damage is one of the first times we've looked at hail swaths in 40 years, and that's attempting to use a spaceborne instrument 7 days after or 2 weeks after the fact. Yeah, we just don't have any on-the-ground observations of these things. Okay, so and then if you try to talk about hail impact assessments, we need some updated information there as well. So here on the right are showing relationships for different crops, looking at crop loss with respect to hail diameter. That's a citation from 1971. That's the most recent study there is on that. Here on the lower, or excuse me, the middle left, those are some impacts that IBHS has been doing, studying the impacts of ice spheres on shingles. And they've certainly made leaps and bounds there. But as we know, ice isn't a smooth sphere, variable density, et cetera. Here in the very low left, that's just a notation that this problem will only get worse. This is technically for a tornado track, but just imagine this as a hail swath. And you can see that as your urban area expands, your hail swath is going to affect more and more areas. Not unexpected given the increasing number of claims. All right, and so hail research really, given all this, hail research needs to be prioritized. So let's think about our US hail-focused field campaigns. There was ENRI in 1972 to 1976, and they managed to get over 50 publications out of that. I mean, many of those we still use today, and that was from a 50 by 80 square kilometer domain with a fixed radar and 1970s technology. There was CCOPE in 1981. And then that's it. So that's 40 years since the most recent US hail-focused field campaign. There's been quite a few on, a few other hazards. Oh, this is a little blurry. The yellow is hurricanes there. This is publications if you happen to look in the AMS journals. The yellow is hurricanes, the green is tornadoes, and the dark blue is hail, and you notice the hail increase is much slower. I know that it's increased a bit in recent years, but yeah, certainly the tornadoes have taken off. We need a hail-focused field campaign. So drum roll, please. Victor promised me you were going to do a drum roll. Oh, thank you. Okay. So how can we address this issue? Ice Chip, the first US-based hail-focused field campaign in 40 years. So we have a suite of about 7 different, I'm going to call them measurement themes or measurement objectives, which I'll walk through and explain, some of the different observations that we plan with each one. So number 1, we want to ensure that we have in situ vertical profiles of pre, near, and substorm environment. We want to be able to characterize that environment as well as possible. So that'll include things like mobile sounding systems on a frequent basis, things like dropsondes, things like mobile radiometer, mobile mesonets, UAS profiling using the CU Raven team. And these are, I've listed the organizations that would be involved with those specific observational platforms next to each one. Number 2, radar measurements. Full 4-dimensional full radar measurements in high space time resolution from multiple frequencies, dual polarization. We want to really interrogate these things as much as possible. And it needs to evolve in time. We've got to be able to capture storm life cycle as much as we can. This would include things like NCAR's S-Pol radar, the CSU chill, because we have multiple frequencies there, the mobile DAOs, the deployable COW, C-band, a Ka-band profiling radar, and Wyoming cloud radar. And the goal here is to be able to really interrogate the hydrometeors as much as possible, as well as, so both a very microphysical focus, but then also retrieve wind fields, 3D winds as much as possible as well. All right, 3 would be isotopic characterization. I think that question actually came up earlier. And yes, we want to be able to get isotopic characterization of both in the inflow sector, so in the boundary layer, but then also of the cloud water in the feeder cells. So we can get the isotopic analysis and more directly link the isotopic parameters to the temperature at which we'd expect them. We then pair that with hailstone collection and then isotopic trace analysis and crystallography. Josh's and Matt's really cool layer analysis that was shown earlier. Let's see, some in-field hail collection, cross-sectioning, all these great things. And the isotopic sampling would be done via the King Air. M4, looking at, and Jim kind of touched on this a minute ago, chaff release and hailstone embryo probes in order to try to characterize updraft structure. And thanks to the Conch experiment, we learned that it may not be physically possible to release enough chaff from a UAS. So we're exploring releasing it in feeder cells, interestingly, so that we can explore the wind motions from there without maybe contaminating our radar information of the storm. Also looking at the Josh Soderholm's Hailsonde hail trajectory probe system, just to be able to fully characterize the updraft and how it evolves in time. Next biggie is the hail swath. We want to get as much instrumentation out to observe this hail swath at the same time as we are doing these radar observations, so we can have simultaneous characterization of the hail-producing storm and the hail at the ground. And this is things, as low-tech as hail pads, Sentinel Smart tiles are more high-tech. You get to impact astrometers, laser scanning. You do hail profiling with UASs in order to get a size distribution over an area. Hail collection with cameras in order to, roughly get some fall speeds. I think we talked about maybe the poor man's hail camera. Yeah, we want to get as many different hail characteristics over as large an area across the hail swath as we can in order to fully characterize these features. And this is just a nice image of the Sentinel tile deployed to NCAR. All right. Then moving on to 6, talking about embryo properties and really just microphysical properties above the ground that we can't, or that in addition to radar. We don't want to, radar will tell a lot of the story, but we don't want to rely just on it to tell the story. So this includes in situ sampling and feeder cells. Here's radar again, but King Air airborne radar, Hailstone cross-sectioning in an attempt to get out embryo type. And then moving to microphysical processes, getting back to some of these laboratory studies in the wind tunnel to understand, hey, what kind of tumbling, shedding, melting, what are all these going on? Finally, hail does not exist in a vacuum. It affects people, and it affects, one of the big things that it affects, of course, is ag, and it affects the built environment. So we don't want to just measure all this stuff and then say, oh, yep, this is what it is. We want to be able to translate from hail characteristics that we've observed to how it's going to impact both the ag and the built environment. And so that's going to make use of, well, the hail impact testing lab from IBHS, but also kind of a unique thing that I think is kind of fun from University of Nebraska of Lincoln. It's actually a hail machine. That's in the upper left. That's a modified tractor that has an ice hopper on it that they can blow the heck out of some test crops with ice and be able to simulate whatever hail characteristics we observe. They can simulate damage from a variety of different crops that they're growing in their test plots with the hail machine. And then, of course, same deal down in IBHS. We'll feed them hail characteristics, and they'll be able to translate that into built environment damage. All right, we do have roughly 5 different science themes that we want to do with all these observations. Theme 1 is looking into embryo development, hailstone growth and fall behavior. We propose that hailstone growth and properties of surface are sensitive to the embryo characteristics, but of course we have no idea if that's true or not. And we also know that hail growth microphysical processes, like shape, roughness, wet, dry growth, et cetera, we're assuming that's going to be related to hailstone growth and surface properties. But yeah, we haven't actually been able to observe that in the real world. We also propose that by including all this information, that can improve explicit microphysical hail prediction, as well as simulated cold pool, et cetera, et cetera, et cetera. Theme 2, I guess I should, let's see, maybe, I was going to say I should mention who's working on each one of these, but I know I'm going to forget someone. But this includes Zach Lebo from OU, Jeff French from Wyoming, and Ted Mansell and Andy, obviously. All right, theme 2, looking at in-storm hail trajectory and convective updraft relationships. Kind of following on the idea that hail growth is stochastic, but maybe there's some hope that as we start examining a larger number of cases, we can start to see some statistical trends, particularly with relation maybe to updraft volume. We also propose that storm scale and smaller processes, that those are going to have the largest effect, both on the production of large hail and on changes over the distribution of the hail swath, changes in time and changes in space across the hail swath. And folks working on this is myself, Conrad, Kelly, and yeah, I should have stopped listing people because I'm forgetting. So yeah, just come see me afterward, and I'll give you a full list. Theme 3, so environmental impacts on hail processes and predictability. So while we thought that the smaller scale impacts can have, or smaller scale features probably have a larger impact, especially when it comes to large hail, that's not to say environment isn't going to play a role. It will obviously still. And we particularly think we can maybe establish some environmental controls on updraft volume and supercooled water content, and then see how forecast skill depends on environmental profiles and errors and initial conditions, et cetera. All right, theme 4, that's diving into the surface properties of hailstones. That includes hail swath and hailstone characteristics, and how those vary in response to storm evolution. We're assuming that those can be modeled with respect to radar and in situ and environmental ops, but again, who knows? So need to actually go out and do it to see. And then we also think that these characteristics can be translated to those specific ag and built environment damage profiles. Finally, remotely sensed hail observations. I mean, radar estimated hail characteristics, those are quite important, and specifically for verifying any of these forecasts we're mentioning. So we think that we can improve those by incorporating observed hailstone variability, multiple radar frequencies, multiple radar fields, et cetera. And we potentially think that we can begin to establish some non-size radar relationships. We also think that we were talking about the idea of updraft volume, that possibly radar detected increases in updraft width might precede surface hail production. All right, these are our planned locations and IOPs. This would be in June 2024 and May 2025. 2024 would focus on the Front Range, and 2025 would be mobile across the plains. Based on climatology, this should be a no-brainer to be able to get the appropriate number of hail days per year, and particularly if you consider the fact that while it'd be great to go out there and get, giant hail, I mean, getting small hail is really important too. We need small hail observations just as much as we need large hail ones. So really any hail anywhere is going to be a game changer. Let's see, year 2, we're going to be mobile, so we can go to where the hail is. Post-deployment, exploring the NCAR cold lab, that means vertical wind tunnel, the hail machine, hail impact testing laboratory. I kind of went through this already. Yes, so the goal is to be able to do all this, and then to be able to create these synthesized data sets that we can then share with the public and really just jumpstart hail research, particularly in the US, for another 40 years. So, all right, thank you, and I'll take your questions.
Thank you, Becky. We have time for maybe a question or so. Anybody? Well, Becky's here, and go ahead, John.
know this is like way late in the game, but just for the cost of this project, for something like S-Pol, to bring it to an experiment for just 4 weeks is a fairly short amount of time, especially if you really want to capture whatever events that you'd like to capture. And we could easily extend that for about the same price for another 2 weeks. And so I don't know if you can, I think it's too late now, but if you could extend some of the radar work for another couple of weeks, you may increase your chances of capturing the hail that you want to capture.
Yeah, that's an excellent point. We do really want to also have the surface observations of hail to go with the radar observations, but that is good to know. Thanks. Oh, sure.
So we have a lot of private sector folks in the audience. How can they possibly get involved if they want to?
Oh, thank you. Yes. Yeah. So one of the big things is that we need to know what kind of information you want, what kind of observations are going to be useful. So this one thing that aspect that I realize now I didn't even touch on because it wasn't immediately observation related is that we are working with Stephen Strader at Villanova and Walker Ashley, who have a Monte Carlo method, or excuse me, a Monte Carlo model of hail swaths and predicting hail risk and hail impact and translating that to dollars. So he's going to be doing this, but I know each of you have your own cat risk models. So what kind of information do you want from us? Is it, is it hail size area? Is it peak size? Is it full size distribution? Yeah, we want to know. So please talk to me. Yeah.
Thank you, everybody, and thank the speakers.